Hi everyone, welcome to PrepFusion. So first, before starting this video, let me tell you who should watch this video. So if you are someone who has never studied EMFT, if you are someone who has no idea of EMFT, still you can watch this video. By the end of the session, you will be much comfortable for 2 to 3 marks in your final examination. Okay. Now you would be saying that, sir, I shouldn't be learning anything new, but you can learn it. Here I will just tell you a problem solving skill, that how you can solve the problem in the examination from these particular concept, because these are very high yield topics. There is 90% chances are there that from these topics question will be framed, and if you watch this video with good amount of patience, then by the end of the lecture you will be much comfortable in solving those problems in the examination. So here, as decent problem solving skills, I will tell you a decent problem solving skill we are going to develop, and that will help you a lot in the examination. So if you have completely skipped the subject, then you can watch this video. Secondly, the guy who is not comfortable with this particular topic, like you would be comfortable with impedance, I guess, but if you have someone who has studied EMFT and still you would not be that comfortable with standing wave pattern, right? If you are someone who has studied EMFT, then I know that standing wave pattern is one of the topic where all the gate aspirants struggle. So that particular topic also we are going to see, and a very good problem solving skills we are going to develop. And no single formula I'm going to apply there. In standing wave pattern, there will not be any single formula. I will just tell you a way of solving a problem. Okay. And that would be very intuitive. You will like that particular concept a lot. So just hold on to the video. Just watch it till the end. So now we are going to start the video. But before that, I will take a pause and then I will start. Yeah, so let's start. So first we need to study some wave parameters. Before going into the concept, first we need to study some wave parameters. So you know what is a wave? You must have heard the word light wave, sound wave. This is a wave, right? So what is the velocity of a wave? Let's just say it is light wave only. So what is the velocity of light in free space or in air? It is equals to the speed of light, which is equals to c, 3 into 10 to the power 8 meter per second. But if it is traveling in a particular medium having dielectric constant of epsilon r, then what is the velocity? That is equals to c divided by under root epsilon r. The velocity reduces. This is the maximum velocity it can have. If it is traveling in a particular dielectric medium, then velocity will reduce. These things you have studied in elementary classes. So I hope you remember it. If you don't remember it, then you can learn it now. The velocity, actual velocity is c upon under root epsilon r. For free space, epsilon r is equals to 1. For air or for free space, epsilon r is equals to 1. So the velocity becomes equals to c only. One thing, okay. The second one, there is a term called wavelength. So wavelength, what is the formula of wavelength? Lambda is equals to Vp by f, velocity divided by the frequency. F, frequency of what? Frequency of wave. F is the frequency of wave. Are you getting this point? So lambda is equals to Vp by f. This formula also you need to remember. I hope you would have studied f equals to Vp by lambda. Usually we remember this formula. In 12th class, you would have studied this formula. F equals to Vp by lambda. So now you can see lambda is equals to Vp by f. So this is one formula you need to remember. And then there is something called phase constant. So formula of phase constant is 2 pi by lambda. So just these things you need to remember. I am not going deeper into the concept that from where this formula came, what is the meaning of this formula. That concept we are not going to see. So if you are just watching this video, then these much things you need to know first. Velocity of wave in air, c. In a particular dielectric medium having dielectric constant of epsilon r, that would be c upon under root epsilon r. Wavelength, the relation between wavelength and the frequency of wave, that is lambda equals to Vp by f. And what is the phase constant? That is beta, which is equals to 2 pi by lambda. So beta, lambda and Vp, these things, basically we have seen the relation between Vp, beta, lambda and f. So just see this slide and try remembering these terms. Even if you forget it, by the end of the video you will be remembering it, because we are going to use it again and again. Okay, let's start our topic now. So impedance on transmission line, this is our topic. So what is the transmission line first? So transmission line is nothing but these are two wires only. Have we seen these kind of wires? Yes, in network analysis we have seen these kind of wires. So what do we do with these kind of wires in network analysis? Here let's just say I connect a resistance R. I am calling it a load. What I am doing, I am connecting a resistance R. So here also what I will do, I will connect a load. Just one sec. Yeah, so what I was saying, in network analysis, this was my, wire. At the load of the wire, I am connecting a resistance R. So here also these are two wires only. But this wire and this wire both are different. What is the difference? That I will tell you. So here also I am collecting a load. That load I am calling as ZL. This is ZL load I am connecting. So here at the end of the transmission line, I have connected a load. Okay. In this particular network analysis, what do? Here we give a supply. We apply a voltage source, right? It could be like it could be AC source as well. It could be DC as well. It could be step as well. It could be anything. Like here in place of this, I can apply AC source as well. So here also I will do the same thing. I will apply a source. So there are two wire. These two wires are known as transmission line. What I am doing, I am applying a source at the input side, and at the load side I am connecting a load, that is ZL. Is that clear? Very simple thing. Now in this particular question, if this question is from network analysis, if I ask you what is the input impedance looking from here, what is the impedance looking from here, what you will say? Sir, R only. Now next question I ask you, what is the impedance looking from here, what you will say? Sir, R only. What is the impedance looking from here? Sir, it is always R only. But that is not the case with transmission line. In transmission line, at every point impedance changes. If I ask you what is the impedance looking here, basically if I ask you what is the impedance looking here, right here I am asking, then you will say, sir, it is ZL. But what if I start working on transmission line? I am starting working on transmission line. That means if I ask you the impedance here, what you will say? What will be the impedance? You cannot say, sir, it will be ZL. Here if I ask you what is the impedance, you will say, sir, it is R only. Because these wire has nothing to do. But if it is a transmission line, then you cannot say the impedance will be ZL. It will be something else. Okay. So what that impedance would be? These kind of questions are asked. So let's what I'm going to do is that, let's just say the length of this transmission line is L. Okay. Then there is a term characteristic impedance. Characteristic impedance. So for all the transmission line, characteristic impedance are defined. That is known as Z0. Like for a different transmission line, characteristic impedance value could be 50 ohm. For some it could be 70 ohm. For some it could be 80 ohm. So just remember that it is just a characteristic of your transmission line. Whatever the transmission line is given, the characteristics of that transmission line is defined by its characteristic impedance, that is Z0. For different kind of transmission line, it could be different. Now there are two wires, no? One wire and another wire. So between the wire there could be any medium. It could be air as well, it could be water as well, it could be glass as well. Between the wires there could be any medium, and that medium can have its dielectric constant. So epsilon r. Don't feel like that, sir, there are too much information. There is nothing. Two wires are connected. At the load you are having ZL. You are applying a voltage source Vs. That's it. And from where you are starting? Now I will start working from the load. Whatever the analysis we are going to do in transmission line, we will do from the load only. Okay. So this is my y equals to 0. What I am saying, this is my y equals to 0. So what this will be? Y equals to L. So if I am at load, then my impedance is ZL. But if I am y distance away from the load, if I am y distance away from the load, if I am someone who is here, if I am y distance away from the load, then what will be the value of my impedance? What will be ZY? So that ZY is given as Z0 into ZL plus JZ0 tan beta Y. Now, like, don't get afraid that, sir, how we will remember the formula. Slowly you will remember. Just watch the video till the end. After that you will be very comfortable. But don't give up in between. Okay. So this will be the formula. What is the formula? Getting started with Z0 into ZL plus JZ0 tan beta Y upon Z0 plus JZL tan beta Y. This will be the formula. Even if you forget it, then also there is very high chance that you will be able to solve the problems. Okay. But eventually you are going to remember it, because I am going to write down this formula again and again. Look, there is symmetry. Getting started with Z0, then ZL plus JZ0 tan beta L. Then in the downward, here you are having ZL. So now you are having Z0 plus J. Here you are having Z0, you are having ZL tan beta Y. Okay. Z naught into ZL plus J Z naught tan beta y divided by Z naught plus J ZL tan beta y. What is y? Y is the distance from here. I should have made y clear. Y is the distance from load. What is y? Very important point. Distance from load. Distance from load. Now let's see something. If I am at load, if I am standing at load only, then what is the value of y? Y is equals to 0. At load, the value of y is equals to 0. Now what is my zy? Again, let's write down the formula. The formula is z naught into zl plus jz naught tan beta l divided by, it's not tan beta l, sorry, not l, y, because I am taking a random distance, no, a random distance from load. I'm not talking about the input. I'm taking a random distance from the load. So that's why I'm writing time y divided by z naught into, sorry, z naught plus jzl tan beta y. This is the formula. And what I'm putting, y equals to 0. If I put y equals to 0, what I will get? What will be the value of tan beta y? That will be equals to tan 0. So tan 0 is equals to 0 only. So this will be gone, this term will be gone. Z naught and Z naught will be cancelled. Basically, z at y equals to 0. What we are getting? Z naught into ZL plus, this will be 0 only, this will also be 0 only. So ZL plus 0 divided by Z naught plus 0. So what you are getting? Z at y equals to 0 is ZL only, and which is pretty obvious, right? At the load, you should have got the impedance to be equals to ZL only. This is pretty obvious. If you are at y equals to 0, your impedance is ZL only. But at a distance y from the load, your impedance is Z naught into ZL plus JZ naught tan beta y upon Z naught plus JZL tan beta y. Is that clear to you? Okay. Now if you are at the source, that means what will be your length? Y equals to L. That means you have covered y equals to L length. If you are at the source, if you are someone who is here. So a lot of time this impedance is shown as Z in. Okay. Because this is the complete input impedance of the transmission line, no? So sometimes this impedance is shown as Z in. So here, if I am saying I am at y equals to L, then the impedance will be called as Z in. So what will be the value of Z in now? Z in will be equals to Z naught into ZL plus JZ naught tan beta y equals to L I need to put, divided by Z naught plus JZL tan beta L. So usually this formula is taught everywhere, but no, this is not the case. They can ask the impedance on any point of the transmission line. It is not necessary that they will ask only at the input. I can ask here as well. Here as well I can ask. So you just need to know that how much away you are from the load. That will be your y value. So that y value you can put. Now we will take some special cases. Okay. So what we are doing, at a particular distance y from the load, we are writing down the impedance. Now let's just say this y is equals to odd multiple of lambda by 4. That means it could be lambda by 4, 3 lambda by 4, 5 lambda by 4, or any odd multiple of lambda by 4. Then first let me know the value. What will be the value of tan beta y? So that will be equals to tan beta. What is beta? 2 pi by lambda. And what is y? What is y? Let's just say y I am taking lambda by 4 only. For now I am taking y equals to lambda by 4. So what I am getting? This and this get cancelled. So what you are getting? Tan pi by 2. And what is the value of tan pi by 2? Infinity. Right? Tan pi by 2 is infinity. Say yes or no? Now, instead of lambda by 4, if I put 2n plus 1 lambda by 4, like it will not only work for lambda by 4, it will work for 2n plus lambda by 4. That means at any odd multiple of lambda by 4, it will work. So tan beta L I need to find. So what is the value of beta? 2 pi by lambda into 2n plus 1 lambda by 4. So lambda lambda got cancelled. So what you are getting? Tan 2n plus 1 into lambda lambda got cancelled into pi by 2. Now if I put n equals to 0, what I am getting? Tan pi by 2. If I put n equals to 1, what I am getting? Tan 3 pi by 2. If I put n equals to 2, what I am getting? Tan 5 pi by 2. Value of all these are infinity only. This is also infinity, this is also infinity, this is also infinity. All these are infinity only. Right? So what I am getting? I am getting infinity only. So tan beta y is infinity for with this particular case. So what will be my z at y equals to lambda by 4, or you can say z at y equals to 2n plus 1 lambda by 4. That will be z naught into zl plus j z naught tan whatever it is beta y divided by z naught plus j zl tan beta y, right? Now I know one thing. What do I know? That this term is very larger than zl. Tan beta y is already infinity, so this term is very larger than zl. So I can ignore zl, no? I can ignore the zl, and in the denominator I can ignore z naught because this term is very larger. So what I'm gonna do, in the upper side I'm gonna ignore zl, in the downward I'm gonna ignore z naught. So this z naught will be there as it is because that is in the multiply. This is in the plus. Like infinity plus anything will be infinity only, no? Right? So this is what I am doing. So this z naught remains there as it is. J z naught tan beta y divided by j zl tan beta y. So tan beta y is getting cancelled. J is getting cancelled. So what you are getting? Your impedance when your length is, that means the distance from the load is odd multiple of lambda by 4, then the impedance will be z naught square by zl. So whatever the load is there, it is inversely proportional to that load. Whatever the load is there, the impedance is inversely proportional to the load. The impedance at lambda by 4 will be inversely proportional to the load. In the upper side, what will come? Z naught square will come. And what is Z naught? Z naught is the characteristics impedance of the transmission line. So this should be there in your mind, and we will again and again use it. Eventually you are going to remember it. So what do you see here is that your zy is zy at lambda by 4 or at different odd multiple of lambda by 4, it is inversely proportional to zl. So just your zl is getting inverted. Let's just say here I was having short circuit. Short circuit means zl would have been equals to 0. If your load was shorted, that means zl would have been 0. Then what would be the impedance at lambda by 4? That would have been z naught square divided by 0, that means infinity. So if load was shorted, then at lambda by 4 you would get open circuit. If it was open circuit, then at lambda by 4 you would have got short circuit. If it was inductive, then at lambda by 4 you would have got capacitive. What do I mean? If your ZL was inductive, let's just say my ZL was some J5 ohm. This was my ZL. So at lambda by 4, at the distance lambda by 4 from the load, what I would be getting? Z naught square divided by J5. So this J goes upward. So minus J Z naught square by 5. So what is this quantity? This is capacitive only. So inductive becomes capacitive. Capacitive becomes inductive. Open circuit becomes short circuit. Short circuit becomes open circuit. So at lambda by 4, you are seeing a inversion, right? Whatever that was there at the load, at lambda by 4, you are just getting the opposite of that. A very important point, right? Now let's take the case of lambda by 2. So in the same manner, we can do the analysis. What will be the value of? And here I am taking any multiple of lambda by 2. Any multiple of lambda by 2 will work. So what will be the value of tan beta y? So tan beta 2 pi by lambda into n lambda by 2. Okay, lambda got cancelled. What we are getting? Tan n pi. And what is the value of tan n pi? That is 0. Even if you put n equals to 0, 1, 2, 3, 4, that is 0 only. So what do we get? What will be our formula? Y equals to n lambda by 2. The formula would be z naught into zl plus j z naught tan beta y, that is 0 only, divided by z naught plus j zl tan beta y, that is 0 only. So 0 0, this is gone, and z naught will get cancelled. What I am saying, zl into 0, that is 0, z naught into 0, that is 0. So what you are left with? Z naught into zl upon z naught. So what you are getting? Your impedance at lambda by 2 away from the load is equals to ZL only. That means if this is your transmission line, if this is my transmission line and here I am having any load ZL, now I start working on this transmission line. If I have worked for lambda by 4 distance, then there will be inversion. Basically, if I have worked for lambda by 4 distance, then there will be some inversion. That inversion would be Z0 square by ZL. But if I work for another lambda by 4, that means total if I work for lambda by 2, total if I have worked for lambda by 2, then the same expression I will be getting. That means after lambda by 2, the D2 same thing is repeated. And after every lambda by 2, this will be repeated. Basically, at lambda by 2 it is repeated, then at lambda also it will be repeated, at 3 lambda 2 by also it will be repeated, at 2 lambda it will be repeated, 5 lambda by 2 it will be repeated. And this is pretty obvious as well. Why is that so? Let's just say I am standing here. I am standing at this particular point. Now where will be this point? This point will be lambda by 4 away from this particular point. This point is lambda by 2 away from the load. I am calling this point as B. So this point B is lambda by 2 away from the load, but this point B is lambda by 4 away from point A, right? At point A, what is the impedance do you see? Z0 square by ZL. Now on the transmission line, if I have worked for lambda by 4, if I have worked for lambda by 4 on the transmission line from the load side, then what should be the impedance? The impedance should be Z0 square divided by whatever the impedance that I get here. Are you getting this point? What I am writing? I am writing down the impedance. I am writing down the impedance at point B. But this time I am not working from the load. This time I am working from the point A. From where I am working? I am working from the point A. So what will be the formula? If I work from the point A and I need to reach at the point B, that means I need to work for lambda by 4 distance. And when we work for the lambda by 4 distance, then this is the formula. Z0 square by ZL. So Z0 is the parameter of your transmission line divided by ZL. That means whatever the load you see at lambda by 4 distance, whatever the load you see, this load I see. So what is that load? Z0 square by ZL. So what you are getting? If you solve this, what you are getting? ZL only. So basically here your impedance is, at n lambda by 2 is proportional to ZL, no? So what is happening in the transmission line? Let's just say this is my load. This is my load. So at lambda by 4 there will be inversion. Then again from here to lambda by 4 again there will be inversion. So inversion, two inversion will make the same thing. Are you getting this point? ZL. Then after lambda by 4 there is inversion. Then again after the lambda by 4 there will be another inversion. So that means at lambda by 2, from the load at lambda by 2 you are getting the same thing. Is that clear to you or not? You started from here. After lambda by 2, you are getting the same D2 thing. A very good point. This is how you need to understand the impedance of transmission line. We just write down the formula and we write down the special cases. We don't even understand anything. But this is how you need to utilize. You just, the thing is, I am not gonna analyze with respect to only load. Now in the examination, what if I give you a transmission line and then I say that at a particular point in the transmission line, at any random point, I see the impedance of ZA. Then at lambda by 4 distance away from this particular point, what will be my impedance? Will you be able to write down? Yes. What will be the impedance? The impedance will be, sir, Z0 square divided by at lambda by 4 away, what we are seeing? ZA. That would be the answer. Because if I work for lambda by 4 in my transmission line, then my impedance will be changing by Z0 square divided by whatever the impedance that was there. That's it. So at any random point they can ask you the impedance. Usually they have always asked at the input, but it is not necessary in the examination. If they want to frame a good question, then they will frame these kind of questions that at a particular point they will give and then they will make you work. Are you getting this point? So let's write down the summary of all these points. Okay. So only till now, what all things you need to remember? Only two formula are there. Which formula? This one. That at lambda by 2 you will get the same impedance. At lambda by 4 you will get the inversion. Z0 square by ZL, and here you will get the ZL. And since we are applying this formula again and again, so you can remember this one as well. Because we are applying it again and again. So if you remember this one, then it will be also very good for you. Okay. So let's see the conclusion. So at lambda by 4 distance away from the load, what will be your impedance? Z1Y I am writing. That would be Z0 square by ZL. Then lambda by 4 away, lambda by 4. That means total lambda by 2 away. This is your total lambda by 2 away. So without even deriving, I can write down. What I will say? That sir, Z2Y will be equals to Z0 square divided by Z1Y. Right? So what is by Z1Y? Z1Y is sir Z0 square by ZL. And if I solve it, what I am getting sir? Z2Y is equals to ZL only. Or directly I have derived it as well. That at lambda by 4, at lambda by 2, at any multiple of lambda by 2, I will get ZL only. Now, from here to lambda by 4 away, from this particular point to lambda by 4 away, what will be the impedance? Z3Y. So that would be Z0 square from here to lambda by 4, or you can say total 3 lambda by 4. Total 3 lambda by 4. So sir, from here to lambda by 4 away, if I need to write down Z3Y, so what that would be sir? Z0 square divided by Z2Y. Z0 square divided by Z2Y, because from lambda by 4 there is always an inversion. So what I will get? What is my Z2Y? That is ZL only. So Z0 square divided by ZL. There is another way of writing Z3Y. What that would be? What do I know? After lambda by 2, there is the same thing repeated. If it was ZL here, here also it was ZL. So after lambda by 2, same thing is repeated. Now here if it is Z0 square by ZL, then after lambda by 2 the same thing will be repeated. That means the distance between these two guys is lambda by 2. So if you are getting Z0 square by ZL here, that means after lambda by 2 the same thing will be repeated here. So Z3Y will simply be equals to Z1Y. And what is that equivalent to? Z0 square by ZL. So now instead of mugging up the formula, are you understanding the concept now? That what is actually happening in the transmission line? Now from here to lambda by 2, you are getting this point. So whatever the impedance that you got here, the same impedance you will get here as well. So your Z4Y will be equals to Z2Y, and that will be equals to ZL only. Or you can say it will be the, what will be the total distance? The total distance from the load will be lambda. So it's not necessary that you will always do the analysis from the load. You can do the analysis from any random point to the next point. And this is what I'm going to teach you in the standing wave pattern as well. That will be the next topic. These are very important topics. So usually in EMFT, what happens is that people go with the formula. I'm not only talking about transmission line, I'm talking about the complete chapter. But this chapter is not dependent on formula. Those who have studied the comprehensive course, it is uploaded on YouTube only. Then you will realize that without understanding the formula, we can understand the concept as well. And this is the way we need to proceed. Is that clear to you? Okay. So now all things are clear. Just you understand one thing, that after every lambda by 4, the things are being inverted, and after every lambda by 2, the same things are repeated. Well and good. Let's go to other cases. Like this is not a special case. You don't need to remember the final result, but this is something that might be asked in the examination. Like it would be helpful for you. Okay. This is not a special case. Other cases it is. So no need to remember. Just see the analysis. So again, I need to write down ZY only. ZY I need to write down. So what is the value of Y? Lambda by 8. So what will be the value of tan beta Y? So tan beta Y will be 2 pi by lambda into lambda by 8. So that will be 10 pi by 4. So here what is the value of 10 pi by 4 you are getting? That is 1 you are getting. Here the value you are getting 1. So what will be your Z at Y equals to lambda by 8? That will be equals to Z0 into ZL plus J Z0 tan beta Y, and that is 1 only, right? Divided by Z0 plus JZL tan beta Y, that is also 1 only. So this is what we are getting. So Z equals to Z at Y equals to lambda by 8, you are getting Z0 into ZL plus JZ0 upon Z0 plus JZL. Now let me know one thing. This is the formula which you don't need to remember. I am just telling this analysis because this is famous. A lot of time the length in the examination will be given lambda by 8. Okay, it is famous, that's why I have written down the example. There is no other reason behind that. Because here tan pi by 4 is becoming 1. So calculation becomes a bit easier. That's why. But just let me know one thing. Is that true only for lambda by 8? No. It is true for lambda by 8. And after lambda by 2, everything is repeated. So lambda by 8 plus lambda by 2, or lambda by 8 plus lambda by 8 plus 3 lambda by 2. Basically, after every lambda by 2, things are being repeated. After every lambda by 2, things are being repeated. Lambda by 8 plus lambda. After every lambda by 2, things are being repeated. After every lambda by 2, things are being repeated. So this is true not only for lambda by 8. This is true for lambda by 8. Then if you add this thing, what you are going to get? 5 lambda by 8. If you add this thing as well, then what you are going to add? 9 lambda by 8. Here you can do the calculation. So in that manner, it is applicable. I guess it will be increasing by 4 only. So it should be 13. Yeah, 13 lambda by 8. 13 lambda by 8. 17 lambda by 8. 3 lambda, here it should be 2 lambda because it is increasing by lambda by 2. Yeah. So 17 lambda by 8. So it is applicable for all these points. Okay. 5 lambda by 8, 9 lambda by 8, 13 lambda by 8, 17 by lambda by 8. So it is applicable. This formula is applicable for all these points. Again, you don't need to remember it, but in the examination, sometimes these length can also be mentioned. So there it should be coming into your mind that there will be some very simple formula. Okay. Let's see this case as well. If my load is open circuited, here I am not talking about any length. I am taking another random length. So load is open circuited, that means ZL is infinity, right? So what will be my ZY? ZY is Z0 into ZL plus J Z0 tan beta Y upon Z0 plus J ZL tan beta Y. ZL is infinity. That means this load, this guy is very large. So I can ignore this guy. If my ZL is infinity, then this guy can go to 0. And if ZL is infinity, that means this guy is very large. That means this guy can go to 0. Right? So what I am left with? Z0 into ZL upon JZL tan beta Y. Okay? ZL get cancelled. So what we are getting? ZY. I should not write down ZY. I am writing Z open circuit Y. Z open circuit Y we are getting as minus J Z0. ZL get cancelled. Minus J Z0 cot beta Y. Again, it's not necessary to remember all these things. Okay? But these are the special cases. Any day you can derive in the examination as well. Very simple calculation it is. Just if you remember this formula, you will be able to get to this particular expression if it is required in the examination. Okay, same goes for short circuit as well. You can derive the same thing for short circuit as well. ZL is equals to 0. So put ZL equals to 0 in this expression. If you put ZL equals to 0 here, ZL equals to 0 here, then what will happen? Z0 will get cancelled. So what will be the formula you will be getting? So Z open circuit Y, open circuit expression will be equals to J Z0 tan beta Y. Okay, so this will be the expression that you will get. Again, I am writing now open circuit. Sorry, this is the case of short circuit. This is the case of short circuit. Sorry, this was the case of open circuit. That means ZL was infinity here. This is the case of short circuit. That means ZL is 0 here. So if I put ZL equals to 0 here, then what I am getting? Z0 get cancelled. So J Z0 tan beta Y I will get. Okay. So what you have got? Open circuit and short circuit. The formula for open circuit was minus J Z0 cot beta Y. And here for short circuit it was J Z0 tan beta Y. How do I remember? I remember that cot beta Y will be there, tan beta Y will be there. And with cot, usually we study tan. Cot we rarely study. So if I am writing down cot, that means there will be minus sign as well. So minus J Z0 cot beta Y and J Z0 tan beta Y. Now confusion will be, sir, which formula is for open circuit, which formula is for short circuit. So open circuit, it has O. And in cot as well there is O. Open circuit, CO. In tan there is no CO. But in open circuit and cot, open circuit and cot. So minus J Z0 cot beta Y, short circuit will be J Z0 tan beta Y. So this is how I remember because I have enough practice. But your examination is after 11 days only. So you might not be having enough practice. So you can derive it in the examination. Very easily you will be able to derive it. But if you are deriving it, that means you need to remember the formula of ZY. That is Z0 into ZL plus J Z0 tan beta Y upon Z0 plus JZL tan beta Y. So this is the formula of ZY. At lambda by 4 length, what happens? Z0 square by ZL. And at lambda by 2 length, the same thing are repeated. So this is the conclusion of our 35-minute discussion. What is the conclusion? This all things are the conclusion. This is the conclusion, nothing else. And another conclusion is, after lambda by 4, things are being inverted, and after every lambda by 2, the things are getting same. This is the complete conclusion of last 35 minutes. And with that, you will be certainly able to solve 2 mark question in the examination. It can come for 1 mark as well, 2 mark as well, but certainly it will come. And in this 35 minutes of discussion, you will be able to solve that. Just see one of the solution from my side. Okay, this is a basic question. Then I will solve this problem. After that, you will solve all the problems on your own. And all these are gate PYQs only. Okay, all these problems you will solve. I will just solve this problem and this problem. After that, you can solve on your own. Now in the examination, let's just say this question comes up in front of you. You can see that this load is short circuited and they are asking Zin, and Zin is lambda by 4 away from the load. So here will you be thinking that, sir, what is the formula of Z open circuit, Z short circuit? No. What you will see? Lambda by 4. If lambda by 4 and lambda by 2 are coming, these are my priority. If lambda by 4 and lambda by 2 are coming, I just know that at lambda by 4 things will be inverted. So if I need to write down the impedance, so at lambda by 4 away from load, the transmission line could be anything. It could be this much larger as well. I need to write the impedance after lambda by 4. Whether it is input impedance or it is anything else, I don't care. But I need to write down the impedance after lambda by 4. That would be Z0 square by ZL. Z0 square divided by ZL, that is 0. So what I am getting? Infinity. That's it. But in the examination, if the length is lambda by 8, so now you will see that, sir, this is not a standard length. So better now I can go with Z open circuit formula, because this is not a standard length, lambda by 8. Lambda by 4 and lambda by 2 are the standard length, but lambda by 8 is not the standard length. So now I can go with the which formula? Now I can go with the formula of open circuit, because here you are having open circuit. Open circuit quote, and quote we don't use usually, so that's why minus sign will be there. So J Z0 quote beta y, beta y. Then I will see the length. What is the length? J Z0 quote beta. What is the value of beta? 2 pi by lambda. And what is y? Y is lambda by 8. Lambda lambda gets cancelled. 2 pi by 8 is pi by 4. Quote pi by 4 is 1. Quote pi by 4 is 1. Look, 2 pi by 8. 2 pi by 8. This is very simple thing. Pi by 4. Quote pi by 4 is 1 only. So what I am getting? Z open circuit is minus J Z0. There you go. Z0 value will be mentioned in the examination. Okay. So answer will be minus J Z0. So here I did not think of that short circuit formula or open circuit formula, but here I thought of it because the length was not standard. In the examination, 99.999999% I am saying that length will be standard only. It could be lambda by 8, lambda by 4 or lambda by 2 or any multiple of that. Like in the examination, it might happen that they can give you the length of 5 lambda by 4. But you know that it is equivalent to lambda by 4 only, because it is odd multiple of lambda by 4. So I am saying 99.99% chances are there that from this particular, like till now, whatever the question has been framed, those questions have been framed on the same particular values. Okay. So let's see the gate PYQs. This is a gate PYQ only. You need to find the impedance here. So from where I will start solving? From here I will start solving. So first is this particular scenario. The length is lambda by 2. So if I write down the impedance here, between these two nodes, if I write down the impedance, what value I will get? 2 R naught. After lambda by 2 distance, it will be repeated. Say yes or no. And if I write down the impedance here, after lambda by 4 distance, R naught by 2, it will be inverted. So what will be the impedance? Z0 square by ZL. That means R naught square by ZL. That is R naught by 2. So what you are getting? 2 R naught. Are you getting this point? What I am solving, I am looking at this node. What is happening here? There is a transmission line. Then at the load of the transmission line, 2 transmission lines are connected. If I call this point as A and this point as B. So between point A and B, this transmission line is connected. If this point is A, then this point is also A. If this point is B, then this point is also B. So between A and B, there is one transmission line connected. Between A and B, there is another transmission line connected. So this transmission line at the input will give you this much impedance because it is lambda by 4. What is the formula? Z0 square by ZL. So R0 square divided by this R0 by 2. So what you are getting? 2R0. And here also what you will get at lambda by 2, same thing is repeated. So 2R0. So what you see here is that whatever the circuit is there, I don't care. But here you are having A and B. Here you are having A and B. Right? So between A and B you are getting 2R0. And between A and B you are getting 2R0. Between A and B you are getting 2R0. Between A and B you are getting 2R0. So what is the equivalent? 2R0 parallel with 2R0. What I am getting? R0 only. So now how my circuit is reduced? My circuit is reduced somewhat like this. This is my one transmission line having a length of lambda by 8. Having a length of lambda by 8. At the load, this point is A. If this point is A, that means this point is also A. This point is already B. So this is my load AB. And between AB, what is connected? R0 is connected. And what is the impedance of this line? That is R0 only. And what do you need to write down? Zin. So what will be my Zin for lambda by 8 length? You don't remember, you can derive it in the examination. But we have already written down the formula for lambda by 8. We just remember that for lambda by 8, tan beta y will be 1. For lambda by 8, my tan beta by y will be 1. This is what I remember. That my tan beta y, that will be 1. So what will be my Zin? Zin will be Z0. What is my Z0? R0. Z0 into ZL plus JZ0 upon Z0 into ZL plus JZ0 upon Z0 plus JZL. Basically ZL and Z0 both are equal now. Both are R0 only. ZL is also R0. Here my ZL is equals to R0 only and Z0 is also equals to R0 only. So this and this term is getting cancelled. So what is the value of Zin? Zin is equals to R0. That's it. That's the answer. This is the answer. Very simple. Input impedance looking from here is R0. This is not tough at all. You just need to keep on solving the transmission line. Try doing this question on your own. Try doing this question on your own. You would be able to do it, believe me guys. So this is one transmission line. From here I need to find the impedance. So first I need to keep on solving these lines. So between A and B, this transmission line is connected, which is having Z0 2. Between A and B, this transmission line is connected. This is having Z0 3 and load is 50 ohm, load is 50 ohm. Z0 2, Z0 3 both are 100 ohm only. The length is lambda by 4. This length is also lambda by 4. So what do you see between A and B? What all resistance you will see? So first resistance, let's just say it is coming from this transmission line. From transmission line 2, because here Z0 2 is there. So from transmission line 2, what will be the impedance? From transmission line 2, the impedance will be Z0 2 square by ZL. What I am saying, if I write down Zin 2, that would be Z0 2 square by ZL. Z0 2 square is 100 into 100 divided by 50. That would be equals to 200. So from here, looking at this side, I will get 200. Similarly, downward as well, the same circuit is there. The length is also same, load is also same, everything is ditto same. So here also you will get 200 ohm. Then again you will get 200 ohm only. So what will be the equivalent? 100 ohm. Right? So add the load between A and B, what do I see? 100 ohm. So what will be my Zin? So my Zin will be again at lambda by 4. Basically this is the scene now, that you are having your transmission line which is having a length of lambda by 4, and here you need to find out the impedance, and at the load you are having 200 ohm. 200 ohm, sorry, you are having 100 ohm because equivalent is 100 ohm only. Are you getting this point? So now you need to write down Zin. What will be your Zin? Zin will be Z0 1 square. What is the value of Z0 1 square? Z0 1 square. Z0 1 square divided by ZL, which is 100 only. So what is Z naught 1 square? 50 into 50 divided by 100. So what we are getting? Z in is equals to 25 ohm. That's the answer. Very, very simple thing. There is nothing here. There is nothing that can trouble you. Are you getting this point? Right? Lambda by 4, lambda by 4, lambda by 4. You just remember all the formula. If you are not able to solve this one on your own, then try doing this one on your own. This is a bit different actually. Here I can call this point as A and this point as B. So in between there is another point AC. So between AC there is this transmission line and between CB there is this transmission line. So how much impedance this guy will give you? CB. Lambda by 4 distance is there. So the impedance, let's just call it Z in 3. So Z naught square by ZL. 100 square by 100. So from here you will get 100 ohm. And what about from here? The length is lambda by 2. So after every lambda by 2, the same thing is repeated. After lambda by 2, the same load is repeated. What is the load? 100 ohm only. So between A and B, this is 100 ohm. And A, this is C. Okay. Between C and B, another 100 ohm is there. Between C and B, there is another 100 ohm. So this time they are not coming in parallel, they are coming in series. C and B. And then there is transmission line. This is your lambda by 4 length, 100 ohm, and you need to write down Z in. So what will be the total impedance? That would be 200 ohm, right? So what will be your Z in? That would be Z naught square by ZL. Because length is lambda by 4. Z naught square 100 into 100 divided by ZL, that will be 200 ohm, right? So what you are getting? 50 ohm. Not tough at all. Very easy question. Very smartly, very easily you can do these kind of problems. Are we having another problem? Yeah, this is also very easy only, but this is just another way of representing the transmission line. Till now we were representing our transmission line with 2 wires, right? We were representing it with 2 wires. But in the examination it might happen that they can represent it with 1 wire as well. Because downward it is symmetric only, no? Downward, here downward it is symmetric only. So sometimes they can represent it with 1 wire as well. So what do you think, what will be your Z in? Length is lambda by 2. So what will be this impedance? Looking from here, length is lambda by 2. So the same 50 ohm will be repeated. So what will be your Z in? Here you are having 100 ohm. The same 50 ohm is repeated here. So here you are having 50 ohm. What they are asking? Z in. Z in will be 100 parallel with 50. So 100 into 50 divided by 150. That will be equals to 100 by 3 ohm. Okay, that's the answer. Very simple it was. It was just another way of representing the transmission line. That's why I asked you to solve this problem. Now solve this question. Magnitude of open circuit and short circuit impedance on transmission line are 100 ohm and 25 ohm respectively. Characteristics impedance of the transmission line. Think about it. Magnitude of open circuit and short circuit. What is your Z open circuit? That is J minus J Z naught cot beta L. And what is your Z short circuit? That is J Z naught tan beta L. Tan beta Y I can write down. Tan beta Y I can write down. If I multiply both of them, what I get? If I multiply both of them, Z open circuit into Z short circuit. J into minus J will be 1. Z naught into Z naught will be Z naught square. Tan beta Y into cot beta Y, what that would be? 1. J into minus J, 1. Z naught into Z naught square. Tan beta Y into cot beta Y into tan beta Y, 1. So what I am getting? Z naught is equals to under root Z open circuit into Z short circuit. So what will be the value of Z naught? They are asking the characteristics impedance. So 100 into 25. Okay. Whatever we get, 5 into 10, 50 ohm. 50 ohm. That's it. Now next concept is impedance matching. So I will teach this, but let me take a break because it's been 50 minutes. So you can just revise it. I don't think there is anything to revise. Okay, you can just revise it, and then I will restart. Okay, let me take a break now. Yeah, okay, so I am back. I hope you would have already revised whatever that we have studied. Okay, now there is one concept that is named as impedance matching. This is important as well, and this is very simple. So in transmission line, our target would always be to match this Z node to ZL. What is our target? That our Z node should be equals to ZL. Okay. Now why do we do so? So that you will understand in the next video. In the next video, where we study about standing wave pattern. So there you will understand why do I want to achieve this condition, that why I want Z node should be equals to ZL. But this is my target, that my Z node should be equals to ZL. But now let's just say by any means this ZL could be some coming from any further stages, and this Z node is also a parameter of a transmission line. So it might happen that Z node is not equals to ZL. So how I will make both of them equal? That I need to see. That is my target. That my target is that Z node and ZL should be equal. So for that, what I'm gonna do is that I will take this transmission line. I have this ZL as well. I have this transmission line as well. I have this transmission line of Z node characteristics impedance. I have the ZL as well. But what I'm gonna do is that in between I'm gonna insert another transmission line that has a characteristics impedance of Z naught dash. Okay, and then I will connect the same ZL here. I will connect the same ZL here. I will keep the length of this transmission line. I will keep the length of this transmission line as odd multiple of lambda by 4. So what will be the minimum length? Minimum length will be lambda by 4. So length could go as lambda by 4, 3 lambda by 4, 5 lambda by 4. In that manner it can keep on going. So what did I say? I have a transmission line. I need to match ZL. What did I do? In between I inserted another transmission line having characteristic impedance of Z naught dash. Now this Z naught dash depends on me because I am gonna insert it. So let me know one thing. What will be the impedance here? The impedance here will be Z naught dash square divided by ZL. And what is my target? My target is this Z naught should be matched with the impedance that I look from here. This Z naught should be matched with the impedance that I look from here. So this is my target. So what I need to do? That my Z naught should be equals to Z naught dash square divided by ZL. So what should be the value of Z naught dash? So Z naught dash should be Z naught into ZL under root. There you go. So in the examination, what do they ask? They ask this thing. Or they can ask the length of the transmission line as well. They can ask the length of the transmission line as well. What would be the length? Lambda by 4, 3 lambda by 4, 5 lambda by 4. So whatever the option is mentioned, that you will pick. If they are asking the minimum one, then you will pick lambda by 4. If it is coming in MSQ, then lambda by 4 could be there, 3 lambda by 4 could be there, 5 lambda by 4 could be there. Okay. Or what they ask? The quarter wave transformer. So this is known as quarter wave. Why quarter wave? Because we are using the length to be odd multiple of lambda by 4. 1 by 4 is quarter. So quarter wave transformer. What it is known as? Quarter wave transformer. So the next question that they ask is, what should be the characteristics impedance of the quarter wave transformer? So that should be the geometric mean of Z naught and ZL. Why that happens, like how we do it, that process is also clear to you, right? Z naught should be matched to ZL. What did I do? In between I inserted another transmission line having Z naught dash as characteristic impedance. My load is ZL. So input should be equals to Z naught dash square by ZL. So Z naught dash should be equals to under root Z naught into ZL. So this kind of question can be asked in the examination. A load impedance of 200 ohm is to be matched with 50 ohm transmission line using quarter wave transformer. The characteristic impedance of quarter wave transformer is. So what should be the characteristic impedance? That should be the geometric mean of Z naught into ZL. So what will be the answer? We will be getting 100 ohm. So that should be the answer. That's it. Now this is not the only way of doing the impedance matching. This was one of the way of doing the impedance matching. The other way is using stub. Now what is this stub? So what do we do? Let's just say I am having a transmission line. I am having a particular transmission line. So at any random distance from load, I will connect another transmission line. What I am doing, I am having a transmission line at any random distance from the load, I will connect another transmission line. I will connect another transmission line. Now the load of that transmission line, either it would be shorted or open circuited. What you are doing, from the load at a random distance, you are connecting another transmission line, and the load of that transmission line is either open circuited or short circuited. So that is known as stub. So this particular structure, this particular circuitry is known as stub. Okay. So what we will do then, we will find the equivalent of this one, and then we will try to match the equivalent of this one to this guy. How do we do that? That is not important for you. In the examination, what will happen? This circuitry will be given, and then they will ask you what all the impedance you can see, what kind of admittance you can see, these kind of questions they ask. Usually they ask impedance, but now what they are asking? They are asking you about the admittance. So what they have said, from the load at random distance lambda by 2, you have connected a stub. This will be written in the examination. So don't get confused with the name stub. What do you mean by stub? A transmission line where load is either open circuited or short circuited. So you have connected a stub which has a length of lambda by 8. This transmission line is having a characteristic impedance of Z0. This transmission line is having a characteristic impedance of Z0. That value is 50 ohm. What you need to find? You need to find the admittance looking from here. So at this particular point, this is A, this is B. So AB will see two kind of transmission line. One is this one, other one is this one. So if we work, let's first find out that what will be the impedance because of this transmission line. AB will see two kind of transmission line. One is stub, another one is this one. So at lambda by 2 distance, what will happen? The same ZL will be repeated. So at AB, what do I see? At AB, wait a second, यार कौन मैसेज कर रहा है भाई इतने? At AB, I see 100 ohm. Why 100 ohm? Because after lambda by 2, everything is repeated. Now, what about lambda by 8? So what do I know for lambda by 8? For lambda by 8, I just know that my tan beta y will be 1. Tan beta y will be 1. And this is short circuit load. Short circuit load. So what will be the formula? That would be J Z0 tan beta y. Are you getting this point? First thing I will see is that this is short circuit. This is shorted. And for shorted, I have a certain formula, that is J Z0 tan beta y. And since the length is lambda by 8, so for lambda by 8, I know that my tan beta y will be 1. So what I am getting? Z short circuited is J Z0. Z0 is 50 ohm. So at AB, one I see J 50 ohm and another one I see is 100 ohm. J 50 ohm. Okay. So from here, I need you to find the admittance they are asking. But can I write down the impedance? Yes. What will be the impedance? That's our impedance will be 1 by Z. If I say what will be the impedance? So impedance will be 1 by Z equals to 1 by 100 ohm plus 1 by J50. 1 by Z equals to 1 by 100 ohm plus 1 by J50. What is 1 by Z? 1 by Z is Y. 1 by Z is Y only. So 1 by 100. What is 1 by 100? 0.01. And what is 1 by 50? What is 1 by J? That is minus J. And what is 1 by 50? 0.02. So whenever they ask you the admittance in the examination, always write down the formula. Let's just say there is this circuitry R1, R2, R3. And they ask you from here what will be the admittance. If they ask you the resistance, if they ask you the impedance, then you will be very comfortable. But what if I ask you the admittance? So do nothing but write down the formula of parallel impedances. What is the formula? 1 by R is equals to 1 by R1 plus 1 by R2 plus 1 by R3. 1 by R equivalent. Okay. You write down the formula, then what will be your 1 by R equivalent equals to? So 1 by R equivalent will be equals to your Y equivalent. So there you go. So that answer will be 1 by R1 plus 1 by R2 plus 1 by R3. So usually what people does is that first they will find Z equivalent, then they will take the reciprocal. But no, go with the basics. 1 by R equivalent to 1 by R1 plus 1 by R2 plus 1 by R3. That's why I picked this question, so that I can tell you this concept of network analysis as well. Whenever they ask the admittance, then rather than going by finding Z equivalent, go with the basics. First thing, that your 1 by Z equivalent will be equals to 1 by Z1 plus 1 by Z2, and 1 by Z equivalent is equals to Y. So from there 0.01 minus J 0.02, very easily you are getting. Otherwise I would have gone into complex calculation, but that calculation I need to avoid. So how will I avoid that calculation? That I have told you. So that would be the answer. This would be the value of Y. So how you are doing the impedance matching, that you don't need to care about. Just in the examination they will ask you these kind of questions, then you should be able to solve. So this will be the last question of our topic, and if you are able to solve this one, then you are good to go. You will be able to solve the problem in the examination, 100% I am telling you. Okay, and yeah, this was considered as a decent question. It came in gate 121, so this was considered as a decent question. So try doing it. What they are doing, there are two stubs. This stub has a length of lambda by 2. If the length of lambda by 2 is there, that means open circuit will be replaced with open circuit only. This is here open circuit. So at lambda by 2, what will happen? Open circuit will be replaced with open circuit only. And what is this? This length is lambda by 4. So short circuit will be replaced with open circuit. Are you getting this point? Here the length is lambda by 4. Here the length is lambda by 2. So they have connected two stubs here. But those two stubs are of no use. The user connected two stubs, but both are of no use. Why is that so? Because this is the length of lambda by 2. Open circuit will be replaced with open circuit. This is the length of lambda by 4. Short circuit will be replaced with open circuit. So what is your equivalent circuit now? In your equivalent final circuit, what do you see? This is my point P. This is my point Q. P, Q. Here Z naught was 50 ohm. Then I am having a length of lambda by 4. And then at the load I am having ZL. And this your Z is 75 ohm. Right? This ZL value I need to know such that impedance matching is there. So what I will do? Here I am using lambda by 4 quarter wave transformer. So here he is using both kind of impedance matching. Quarter wave transformer as well, and stub matching as well. But stubs were of no use. So what will be the impedance he will be getting here? Let's just call it ZX. That will be Z naught square by ZL. And that should be equals to Z naught, which is your 50 ohm. So ZL would be 75 into 75 divided by 50. Did you get this point? Our target is that this transmission line should be matched with whatever the impedance it sees at PQ. So what impedance it is seeing at PQ? Z naught square by ZL. So 75 into 75 divided by ZL should be equals to 50 ohm. So what ZL you are getting? 75 into 75 divided by 50. So 112.5 ohm. There you go. Almost we have done all the PYQs. Not all the PYQs, like roughly you will be now, if the question is coming from this particular topic, which I feel it will come, then you will be able to solve certainly in the examination. So this was our first topic. The next topic is standing wave pattern on transmission line. So I will try to keep this video short only because MOSFET video went for 3 hours. If I include that particular topic which we say standing wave pattern, then it will go for 3 hours as well. So first you need to study this particular topic, then you can go to the standing wave pattern. So I will upload this video today itself. I guess it is 7 PM. So I will try to upload it by 8 PM so you can watch it. And tomorrow we will go to standing wave pattern on transmission line. This is also very, very important, and very good questions can be framed from this particular topic. And a lot of guys who have studied it, you can ask anyone who have studied EMFT from anywhere. He will say the toughest topic is this one only, because he mugs up the formula here. But without even using any single formula, without even using any harsh equation, without even using those equations, we are going to solve these kind of problems. Okay. So certainly we will meet in the next lecture. We will talk about what do you mean by traveling wave, what do you mean by standing wave. All these topics we will talk about. So till that, you revise this 1 hour of lecture. I guess in 1 hour of lecture, everything is clear. And let me know in the comment section that how you are finding this kind of initiative, because this is a bit different initiative that we are, without even starting the chapter, we are right going in between of a particular topic and covering that from scratch without even knowing the previous thing. So I tried to bring something different because rest all the initiatives are already coming on other channel. So the same initiative I never wanted to bring. I wanted to bring something different because you can certainly follow their lecture as well. They are also doing good thing. So if I bring the same thing, that means that will be of no use. No, I tried to bring something different because these are the high yield topics and certainly the question would be coming from here. So if someone who has skipped this, then at least you should have a clear idea, like basic idea or more than basic idea you are getting. Like, I should not say this, but in 90% of the comprehensive course, you will not get this idea. This is just one video. This is not even comprehensive course, okay? But in 90% of the comprehensive courses, you are not even getting this idea. So here it is crash course of crash course. This is not even crash course. This is crash course of crash course. So in that as well, you are getting a decent idea, and certainly you will be able to solve the problem in the examination. So next, our video will be on standing wave pattern on transmission line. Thank you very much. Happy learning. Yeah, hi everyone. Welcome to the second part of transmission line. I hope you have already seen the first part. So even if you haven't studied EMFT, you don't know anything about EMFT, still you can watch this video. This particular video first you need to watch, then you need to watch this video, standing wave pattern on transmission line. So both are very important. If you, even if you don't have any idea, still you can watch it. Now this standing wave pattern, this is one of the topic. Even if you are comfortable with EMFT, still you might be facing problem in this particular topic. But after this particular video, you will have a very clear idea that how to attempt particular questions from this particular topic. Okay, so let's get started. So first you need to watch this video, then only you should come here, right? So yeah, let's get started now. So here we are going to study about standing wave pattern. So first we need to study what do we mean by standing wave. Here we are going to see the problem solving technique only, but first we need to study what do we mean by standing wave. So there are two terms, traveling wave and standing wave. So both seems like the same thing only, but this is a picture at a certain time. This is a picture of a wave at a certain time. But what do I mean by traveling wave? That means if I click on the time button, then this wave will start traveling. It is traveling. Let's just say I call this axis as z axis. I am calling this axis as z axis. So now this wave is traveling in positive z axis, right? So this is a traveling wave. What do you mean by standing wave? So this is a picture at a certain time. But now if I click on the time button, what is happening here? If you clearly observe what is happening. So you will see one thing, that this particular node, just keep your eyes on these nodes, okay? Keep your eyes on these nodes. Now what will happen? These nodes will be staying at their own point. These nodes will be staying at their own point. This node will also stay at their own point. So first let's see these nodes, these three red nodes that I have marked, okay? So you see the wave is going up and down, but these are at their same point. Wave is going up and down, but these red, this one and this one, these are at their same point. Again, going up and down, but they are at the same point. Now let's see these peaks. Which peaks I am talking about? These guys. Now let's see these green dots now. Now what will happen? These peaks will move up, down, up, down, up, down, up, down, up, down, up, down, up, down. In that manner it will move. Okay, let's see it. Up, down, up, down, up, down. So this is known as standing wave. So this wave is standing at that own point only. That's why we call it standing wave. It is standing. But this is your traveling wave. Have you done the string experiment? Like at 2 volts, you can there is one guy standing in front of you, and you are standing here. You take a rope and you give a pulse in that particular rope. Like you give a pulse in that particular rope, then what will happen? That pulse will travel and then it will come back. So after that it will feel like that after some time that it is standing only. You might have observed standing wave in real life as well. But even if you haven't observed, then still you can see here. The traveling wave feels like that it is traveling in a particular direction. But standing wave is standing at their own point. It is going up, down, up, down, up, down. But what did you notice here? That these points are fixed. These are at their own point only. This point did not even move. Only the green points are moving. Now if I ask you one thing, just a second. Yeah. If I ask you one thing, will you call this point as minima and this point as maxima? What I am asking, will you call this point as minima and this point as maxima? If someone says yes sir, this is the minimum magnitude, this is the maximum magnitude, so this is my minima and this is my maxima. But after some time what will happen? After some time this point is going to maxima and this point is going to minima. Let's just say I say that this distance is, let's just say, lambda by 2. So can I say at lambda by 2 I am having maxima? Sometimes it will be maxima, sometimes it will be minima. right? So I know that this point is toggling, but I know one more thing, that this point is going to peak. What I am saying, that here you can either have the positive maximum or you can have the negative maximum. Same goes for this point as well. Either you will have the negative maximum or you will have the positive maximum. But these points are fixed at 0 only. Let's just say this is plus 5 volt, this is minus 5 volt. So sometimes it can have plus 5, sometimes it can have minus 5, sometimes it can have in between values as well. But these points will always be at point 0 only. So these points are known as minima. Are you getting this point? Which points are known as minima? This point, this point, and this point. These are your minima. And this point here and here. Let me make it again clear. Okay. So this is the cycle. So this point and this point, these are known as maxima. So is that clear? Like in this chapter, we will study that what is the location of voltage maxima, current maxima, voltage minima, current minima. So is that clear, that what do you mean by maxima? What do you mean by minima? Now, how do we show a particular standing wave? How do we show a particular standing wave? Okay, forget about it. We will talk about how do we show standing wave, but how standing wave is generated, that is the more important part. How traveling wave is generated? So any wave that you see, that is a traveling wave only. Light wave, it is a traveling wave. EM wave, in this chapter we study about EM wave. So EM wave is also a traveling wave. That means wave, energy of the wave will travel. Here, energy of the wave is traveling. Let's just see at this peak. So this peak will keep on moving. Just keep your eyes on this particular peak. This peak will keep on moving in that manner. So actually peak is not moving, the energy is moving. So you will see that the energy will keep on moving. Look, this peak is moving ahead, right? It is following the green path. So energy will keep on moving like that. So this is a traveling wave. So this traveling wave, we can call it as forward traveling wave, because this wave is traveling in this direction. This wave is traveling in this direction. Now let's just say there is some boundary. Here there is some boundary. So assume my hand as a boundary. So a wave was coming like this. Now when it strikes the boundary, what will happen? It will be reflected back. Some part will be transmitted, some part will be transmitted, but some part will be reflected back. So this particular wave is traveling in this direction, right? This particular wave is traveling in this direction. Now this wave will travel in this direction. So one wave was coming like this, then some part was transmitted, some part will be reflected back. Now both combined, this was the forward traveling wave, this is the backward traveling wave. So forward traveling wave and backward traveling wave, both combined will make the standing wave. Combined means superposition. So this is how you get a standing wave. So while going deeper into the chapter, first you need to know that how standing waves are generated, because people just study it, they don't even know how it is generated. That's why the topic become complex for them. Are you getting this point? There is a boundary, came, reflected back. Both combined are making standing wave pattern. Well and good. So this is how we get the standing wave. Now how we can show the standing wave? How do we show the traveling wave? We show the traveling wave in this manner only. In this manner only we show that, and then we say that this is a picture at a certain time. When we click on the time button, this energy will start moving. But how do we show a standing wave? Because the point here is that sometimes this is at negative peak, sometimes it will be at positive peak, sometimes this is at positive peak, sometimes this will be at negative peak. So how do we show it? We generally show the magnitude. So generally what do we do is that this is how we show it. Let's just say this point is this point. Here, this point I am showing like this. Are you getting this point? What I am saying, let's just say this is your y equals to 0 and this is your y equals to L. This is your y equals to 0. So this I am calling as y equals to 0 and this will be my y equals to L. So here how much magnitude I am having? 0. This will be at 0. After some time here also I will have a 0. After some time again I will have a 0. Right? At y equals to L again I am having a 0. And let's just say it is somewhere in between. So 0, then again 0 and then again 0. Okay for you? Okay. Now I know that this can go to the negative peak as well and this can go to the positive peak as well. So here I will show you the magnitude only. So this will be the magnitude of this pulse, right? Same goes for this one as well. So this will be the magnitude. So the point is between two minima, there will be one maxima. I will only show the magnitude. Between two minima, there will be one maxima. That's why the waveform should be made like this. That means there should be like, it should not come something like this. In a lot of textbook as well and even in the gate examination as well, you will see this kind of waveform. But what we are doing, we are showing the magnitude, right? We are showing the magnitude. So here it is not differentiable. On this particular point, it is not differentiable. What if I tell you to draw the graph of sine omega t? So that will go like this. So there is a smooth transition, right? But what if I show you, I tell you to draw the graph of mode of sine omega t? So it will go like this and then directly like this. So there is no smooth transition. It is not differentiable at this point, no? Before this point, the slope is negative. After this point, the slope is positive. So it is not differentiable at this point. So usually the standing wave pattern is shown like this. There should not be any sharp turn. The turn should not be sharp. It will be the turn will be sudden. It comes here, then it should be going like this. But even in the examination, if you see the standing wave pattern made like this, somewhat like this, then also you should not be confused. Okay? In the examination, sometimes the standing wave pattern can be made somewhat like this. They can make the standing wave pattern. Let's just say initially here we are having minima, but it's not necessary that always you will have a minima here. Let's just say initially you are having maxima. So in the examination, they can make the waveform like this as well. They will say that this is maxima, this is minima, this is maxima, this is minima, this is maxima, this is minima. But actually this is not the correct way. This is the correct way of showing it. Okay, the correct way would have been maxima, minima, maxima, minima, maxima, minima, maxima, minima. But even if you get the waveform in this manner, then also you should not be getting confused. So this is the concept of our standing wave. I hope you would have understood what do we mean by standing wave, what do we mean by traveling wave, and yeah, now we are going to relate it with our chapter. We did not start our chapter as of now. So now we are going to relate it with our chapter. So first you should know what is a transmission line, that we have already seen in our previous video. So transmission line is nothing but two wires. Transmission line is nothing but two wires. At the load of the wire, we will connect a load resistance. And at the source of the wire, we will give a supply. This is what we do in network analysis as well. Here we are doing the same thing. Here we are giving this supply. So what I am saying is that this supply will have a particular frequency, right? The supply will have a particular frequency. What do I mean by that? The input could be Vm sine 20 pi t. So what is the value of omega? 20 pi. What will be the value of f? 10. So this is what f I have written. Understood? So we are giving a supply which is having a particular frequency. If you know the value of f, can you let me know the value of lambda? Yes. What is the value of lambda? Vp by f. So let's just say this medium is having a permittivity of epsilon r. This medium is having a permittivity of epsilon r. If you have watched the previous video, then you will be able to relate what I am saying. If this medium is having a permittivity of epsilon r, then what will be the value of Vp? C upon under root epsilon r. And then f will be given. So can you find the value of lambda? Yes. So if there is f, that means certainly there will be associated lambda as well. If there is lambda, then can you let me know the value of beta? Yes, 2 pi by lambda, right? So if there is lambda, then there will be beta as well. So all these parameters will be used in your analysis. Okay. So I am just writing down the formula. The formula are lambda equals to Vp by f, okay, and beta equals to 2 pi by lambda, and Vp is equals to C upon under root epsilon r. So only these formula I am asking you to keep in your mind, and those you already might be knowing from your higher secondary classes, right? Now what will happen here? How standing wave patterns are observed on transmission line? Why standing wave pattern will be observed on transmission line? So let's get started with that. So what will happen? Just as I close this switch, so here a voltage wave will be generated. Just as I close the switch, a voltage wave will be generated. Now this voltage wave will travel. It is traveling. It will be a traveling voltage wave. It is traveling. Now what will happen? It will strike to this load. The voltage, just as you close the switch, the voltage wave is generated, that is traveling. Now that traveling voltage wave will strike to the load. What load will do? Some power it will observe. Some power load will observe. So this is how I am showing the observed power. Some power load will observe, and some power it will reflect back. So wave came, some power load have taken, and some power is reflected back. Some power is reflected back. Some power will be reflected back. And these two superimposed, forward traveling wave and backward traveling wave, these two superimposed will make a standing wave. So this is how standing wave pattern is observed on transmission line. Now what kind of questions will be asked? That on transmission line at y equals to 0 and at y equals to L, or in between anywhere, what will be the location of voltage maxima, what will be the location of voltage minima, how many maxima will be observed, how many minima will be observed, what will be the maximum value of resistance, all these kind of questions will be asked. So those questions we are certainly going to see. So now you are able to relate what we are going to study in this particular chapter. Now you are able to relate why we studied all these things, right? All clear? Now what did I say? That some power will be coming into and some power will be reflected back. So before power, let's talk about the voltage magnitude. So let's just say the incident voltage was V0 plus and reflected voltage is V0 minus. So the ratio of reflected voltage to the incident voltage is given by a particular expression. What I am saying? Y equals to 0. What I am saying, there is a particular expression that is defined, that is known as gamma L. What is this? This is your reflection coefficient at load. Reflection coefficient at load. And what is the value of reflection coefficient at load? That is ZL minus Z0 upon ZL plus Z0. Will that be easy for you to remember? ZL minus Z0 upon ZL plus Z0. A very important formula. If you don't remember it, then your things will not work. Only this formula you need to remember. ZL minus Z0 upon ZL plus Z0. Reflection coefficient at load. Very, very important. And the important line is this. This is reflection coefficient at load. That means this is the reflection coefficient at y equals to 0. Reflection coefficient will change with respect to y. Everything changes with respect to y. Do you remember? Z of y. So at load, the impedance was ZL. But when you walk into the transmission line, the impedance was getting changed. Same goes here. The reflection coefficient at load is ZL minus Z0 upon ZL plus Z0. But when you walk along the transmission line, the reflection coefficient will be getting changed. And what do you mean by reflection coefficient? The magnitude of reflected voltage, ratio of magnitude of reflected voltage to the incident voltage. This is your reflection coefficient. And this formula I have written, reflection coefficient at load. And what we are talking about? We are talking about voltage. So this is the reflection coefficient at load for voltage V. Okay, reflection coefficient at load for voltage V. For voltage we are talking about. We will talk about current as well, but first let's talk about voltage. And how standing waves are shown that I have already told here. Okay, so here I am not gonna write down how standing wave are shown. So this is how the standing waves are shown. Okay, so again I am not going to write down the same thing. So let's just remove it off. So from this slide, what all things you need to remember? There will be a transmission line, there will be a load. I will give a supply. It will have a frequency. It will have a particular frequency. If frequency is there, that means there will be lambda. If lambda is there, that means there will be beta. There will be a load. Just as you close the switch, voltage wave will be traveling. It will be reflected back. Both combined will make standing wave. Okay. The reflection coefficient at load is given by ZL minus Z0 upon ZL plus Z0. And that is the reflection coefficient at y equals to 0. Well and good. Okay. Now let's solve a question. For a transmission line, Z0 value is given, ZL values are given. You need to find the value of a reflection coefficient at load. Then you need to plot it on gamma plane. What is this gamma plane? That I will tell you. Okay. And you will understand as well, on your own as well, you can understand. What do we mean by this gamma plane? You will understand, but let's get started. What we need to find? We need to find the reflection coefficient at load. At load. Again and again, I will say the same thing. This is the reflection coefficient at load. So first question, part A. Gamma L, reflection coefficient at load, and this is for voltage only. So formula is ZL minus Z0 upon ZL plus Z0. If you apply the formula for 3 times, you will be able to remember it. What is the value of ZL? 50 plus 50J. ZL minus Z naught upon ZL plus Z naught. So 50J upon 100 plus 50J. That is J plus 2J. That is equals to 1 by under root 5. Let's write down the angle. Okay, let me do the calculation by pausing the video and then I will write down the angle. Yeah, so the angle is 63.43. I hope you know how to write down these angles, because if gate examination is 12 days apart and you don't even know how to write down these angles, then I don't think you should watch this video, right? I hope you know how to write down these angles. So this is the reflection coefficient at load. Okay, now you need to plot this reflection coefficient on gamma plane. So basically, what is this reflection? This is a complex quantity, no? This reflection coefficient is a complex quantity. So I need to plot it on a complex plane. So gamma will have a real part as well and gamma will have a imaginary part as well. So this is what I am doing. This is gamma real and this is gamma imaginary. In which form I have written it? I have written it in polar form. So you know how to plot all these things in a plane, right? Let's just say this is a quantity 2 plus 3j. How will you plot it? We plot it in Argand plane. 2 plus 3j, 2 plus 3j. Here we will plot it. Or how you could have done? I would have found the magnitude. What will be the magnitude? 9 plus 4, 13. And then there will be some positive angle. So angle is always taken in anti-clockwise direction. So this will be the positive angle. So same thing I am going to do here. What is the magnitude? That is 1 by under root 5. So let's just say this shows my magnitude 1 by under root 5. And angle is positive. The angle is 63.43. So let's make it a bit better. Angle will be 63.43. So somewhat it is like this. So this will be 63.43, this angle. So this is the gamma value. Magnitude is 1 by under root 5. So this is how I will show it in the gamma plane. Okay. So this is coming with respect to ZLA. Let's call it ZLA because this was option A, no? So I am calling it ZLA. So with respect to ZLA, this is my point. This is not the value of ZLA, but with respect to ZLA, this is the line I am getting. Are you getting this point? What do I mean by that? With respect to ZLA, this line I am getting. So this is how I will plot it on the complex gamma plane. Why we are doing so? All the points will be related. So just hold on to the video, just watch the video with good amount of patience. You will understand everything. Why we are doing all these things. Okay. Let's go to the second question. Same, we need to apply the formula ZL minus Z naught upon ZL plus Z naught. So what will happen? You start doing the things on your own. Okay. Now you don't need to watch the complete solution. You can do it on your own. ZL minus Z naught upon ZL plus Z naught. I should have already done the calculation actually. Okay, I will pause the video and then do the calculation. Here, am I doing something wrong? ZL minus Z naught. Yeah, I forgot to. ZL minus Z naught. It will be minus 50J, you know. Because my ZL is 50 minus 50J minus 50 minus 50J upon ZL plus Z naught. So 100 minus 50J. 100 minus 50J. So minus J. I will do this calculation. Yeah, so what you will get? The magnitude will be 1 by under root 5. And certainly the angle will be just negative of this one. That is this thing. Okay. So this is what you are getting for second question for option B. So can I plot it on complex gamma plane? Yes. So let's do it on the next page. Let's do it on the next page. I will plot all the points on complex gamma plane now. So our ZLA came somewhere here. ZLA, this was our ZLA, 63.43. Now ZLB will be making minus 63.43, right? This is your ZLA. This was your ZLA. This will be with respect to ZLB. The magnitude is same, 1 by under root 5, 1 by under root 5, but the angle is minus 63.43. Angle is minus 63.43. Both are two different questions, okay? But I am plotting it on one plane only, so that we can relate the things. Option C. ZL is 100. So what will be your gamma LV? ZL minus Z naught upon ZL plus Z naught. So what you are getting? 1 by 3. Angle 1 by 3. Angle is 0, right? So 1 by 3. 1 by 3 angle is 0. It will be plotted somewhere here, right? 1 by 3 angle is 0. So this is your ZL C. What about D? Gamma LV 25. So ZL minus Z naught 25 minus 50. 25 upon ZL plus Z naught 75 minus 1 by 3. Minus 1 by 3 means angle is 180 degree, right? Can I write it down in this manner? 1 by 3 and angle is 180 degree. And what about the 180 degree angle? This is somewhere here. So this is my ZLD. ZL equals to 50. So this is the case of ZL equals to 50, that is equals to Z naught. So what will be your gamma L? ZL minus Z naught upon ZL plus Z naught. So what will be the answer? 0. So now are you able to understand why did we study impedance matching in the last lecture? Here we were studying impedance matching, stub matching and this impedance matching in the last lecture, and I told you our target should be to make ZL equals to Z naught. If I make ZL equals to Z naught, then my reflection coefficient will be equals to 0. If I make ZL equals to Z naught, then my reflection coefficient, this coefficient will be equals to 0. That means all the power that is coming here, all power will be absorbed by the load. So this is my target, no? Whatever the power that I am giving from here, my target is that my load should take all the power. No power should be reflected back. All the power should be taken by the load. So if I want the load to take all the power, I don't want any power to be reflected back. I want load to take the whole power. Then my ZL should be equals to Z naught. So that's why we were studying impedance matching. Now this is clear to you. So what will be my reflection coefficient now? Reflection coefficient will be 0. 0 means here. EF. F is ZL equals to infinity, ZL equals to 0. Then ZL equals to infinity. So what is the reflection coefficient? ZL minus Z naught upon ZL plus Z naught. ZL is infinity. That means ZL is very larger than Z naught. So Z naught can be ignored. Here also Z naught can be ignored, right? ZL is infinity. That means ZL is very larger than Z naught. So what will be the answer? 1. So reflection coefficient is 1. Reflection coefficient is 1. So somewhere here, that will be my ZLF. EFG. ZL is equals to 0. That means what will be your reflection coefficient? ZL minus Z naught upon ZL plus Z naught. So what will be the answer? 0 minus Z naught upon 0 plus Z naught. So that will be minus 1. Minus 1 means 1 but with the angle of 180 degree. So this will be your ZLF. Why we are doing so? Just have the patience, you will understand. Okay. Don't like lose in between that, sir, why we are doing all these things. You will certainly understand. It will just make the problems very easy. Otherwise the problem on this what do we call it, this standing wave pattern, these problem become very complex if you don't have your concepts clear. Okay. EFG, there is no H here, there is no H, right? But let's build some H. EFGH. So let's take H as 50J. Yeah, EFGH I. Let's take I as minus 50J. Okay. So what will be your H? Reflection coefficient V. ZL minus Z naught upon 50J I have taken, yeah. No, 50 plus 50J I took, no. 50 plus 50J, yeah. ZL minus Z naught upon ZL plus Z naught. So magnitude I can see will be 1 only. J minus 1 upon J plus 1. So magnitude will be 1 only, there is no doubt. But what will be the angle? Minus 1 J. Minus 1 here, J here. So this angle will be 135 degree. Minus this angle will be what? This angle is 45 degree. So angle will be what? 90 degree. So for this case, angle will be 90 degree. Magnitude is 1, angle is 90 degree. This much like basic of mathematics you should know, because I cannot teach all this basic mathematics in these particular lecture. In comprehensive course, we certainly teach this mathematics, but here you should know this much of basic mathematics. So 1 at angle of 90 degree. 1 at angle of 90 degree. This will be your ZL H. Okay. EFGHI, what will be your ZLI? That is minus 50J. Minus 50J minus 50 upon minus 50J plus 50. So here also you can see that this angle minus J and minus 1. So this will be minus 135 and minus J plus 1. Minus J plus 1. That will be minus 45. So angle will be minus 90. So magnitude is 1. Angle will be minus 90. Okay. So this will be your ZLI. So from here, what do you see? What was this impedance? If my load was purely inductive, then it is coming on gamma imaginary axis, but on the positive part. Coming on gamma imaginary axis, but on the positive part. If my load is purely capacitive, then also it is coming on imaginary axis only, but on the negative part. What was this? This was complex load, but it was inductive. This was our first example. Complex load but inductive. So if it is complex but inductive, then it will come on the upper hand part, right? If it is a complex load but inductive, then it will come on the upper hand part. That means it will come here. But if it is a complex load but capacitive, then it will come on the downward part. Here on this part, resistive element came. Let's talk about ZLC. This was resistive. ZLC is resistive. This is also resistive. But here this ZL was greater than Z0. This is ZL less than Z0. So on the real axis, resistive part will come. But here the condition will be ZL greater than Z0. But here the condition would be ZL less than Z0. And it will be the resistive part. What it will be? It will be the resistive part. Now you will say that, sir, ZLF was infinity. So it can be neither, you cannot call it neither resistive, you cannot call it neither inductive, you cannot call it capacitive, you cannot call it complex, because it is infinity. So impedance is infinity. So if the impedance is infinity, then you can understand it as a resistive only. So certainly this is ZL is greater than Z0, no? Here ZL is greater than Z0. Certainly this is ZL less than Z0, right? And this is the condition of ZL equals to Z0. So what do you see here? This is your ZL equals to Z0. If you go to this side, that will be ZL greater than Z0. If you go to this side, that will be ZL less than Z0. Is it tough to remember? No. Because how do we show the inductive part? This is how we show the inductive part. How do we show the capacitive part? This is how we show the capacitive part. So here we show plus J. Here what do we see? Here what do we show? Plus J. Here what do we show? Minus J. So whenever there is a capacitive part, it will be coming downward. Whenever there is a inductive part, it will be coming upward. If it is purely inductive, that means it will be coming on imaginary axis only. And if it is resistive means, so if it is ZL greater than Z0, if value is higher, that means it will come on the positive side. If the value is lower, then it will come on the negative side. Is it tough to remember? No, it is not tough to remember. And again, a very important point, here we are not plotting the impedances. We did not plot the impedances. What did we plot? We plot the gamma L value. What we plot? We plotted the gamma L value. Again and again I will say the same thing. In the examination, you will plot the impedance. What you will say? Okay, my impedance is 50 plus 50J. Make the complex gamma plane. Okay, impedance, sorry. ZL is 50 plus 50J. Make the complex gamma plane and plot this 50 plus 50J. Magnitude will be 50 under root 2. Angle will be whatever you find. So impedance you don't need to plot. What I am plotting? I am plotting the value of gamma L. Because what plane it is? It is the plane of gamma. So what value you will plot? You will plot the value of gamma, no? Not the impedance. So what we are plotting? We are plotting the impedances. So is the conclusion clear? That what is happening? Upper part will be inductive. Downward part capacitive. Resistive. ZL greater than Z0. ZL less than Z0. Middle part ZL equals to Z0. If purely inductive, that means on imaginary axis positive part. Purely capacitive, on imaginary axis negative part. Well and good. Okay. These kind of questions can also be asked in the examination. And a lot of students fail in this kind of analysis. This is nothing but Smith chart. We are studying Smith chart, but I did not name the topic. If I name the topic that we are studying Smith chart, then you would have understood that Smith chart is very difficult, how we will understand. But without even taking the name of Smith here, all this analysis I did not do. Smith did. We are just understanding it. So without even taking his name, I am just telling you that how to study his particular chart. So we are studying Smith chart only here. Okay. Now we are going to see important things. Some important things regarding gamma plane. So first you need to see what kind of questions will be asked. So this kind of questions will be asked. That your Z node will be 50 ohm. On a transmission line, your characteristic impedance is 50 ohm. Your ZL is 50 plus 50J. The load is 50 plus 50J. Standing wave pattern will be observed on the transmission line because there will be some reflections and both combined will make the standing wave. Then they will ask, find the distance from the load at which voltage maxima is occurring. That means this will be your y equals to 0 and this will be your y equals to complete length. So on the complete length, at which distance your voltage maxima will occur or voltage minima will occur or current maxima will occur, current minima will occur. You need to find the standing wave ratio. What is the standing wave ratio? We will talk about. And then these kind of questions. These are like very typical to solve, but we will develop good problem solving skills and you will have a very good aptitude to answer these kind of problems. Then they will ask, on transmission line, what is the maximum value of resistance and where it will occur, or what is the minimum value of resistance where it will occur, and at what distance from the load you will get the purely inductive impedance, and at what distance from the load you will get purely capacitive impedance, right? So how we will solve these kind of problems? So first what we are going to do, first we are going to find the value of gamma L. Then it will have a magnitude and it will have an angle. Okay, it will have an angle. So let's take this example only. Let's take this example only. With respect to the example, we can understand. So let's take the first example. So this is my load and this is my Z0 value. So what will be my value of gamma L? Gamma L at load. That will be ZL minus Z0 upon ZL plus Z0. So ZL minus Z0 upon ZL plus Z0. So we have already found it. What did we get? Arey yaar. So magnitude was 1 by under root 5. Angle was 63.43. So just as I have got this thing, I will plot it on our gamma plane. Okay, this is my gamma real and this is my gamma imaginary. So I will plot it on my gamma plane. So first what I'm going to do, this is how I have plotted it. Magnitude is 1 by under root 5 and this is the angle. Now taking this as a radius, I will draw a circle. Taking this as a radius, I will draw a circle. Okay, just listen to my points very carefully and keep your full concentration high. Taking so taking this point at radius, I have drawn a full circle. So this is my point y equals to 0. That means I am at load. What I have plotted? I have plotted the reflection coefficient at load. What did I plot? Reflection coefficient at load. That means I am at y equals to 0. Now I will keep on walking. Here there is my transmission line. Here there is my transmission line. This is my transmission line. This is my y equals to 0 and this will be my y equals to L. So now I will keep on walking on this transmission line. So this circle is my transmission line. So how you need to walk? Either you can walk anti-clockwise as well and clockwise as well. So where you will walk? You will need to walk clockwise. I am writing down this point. Always walk clockwise. Okay? Because time is money. Time runs us. So we need to walk with respect to time. That means we always need to walk clockwise. So after drawing this circle, I will make this arrow. That means I will walk clockwise now. Okay. Now I am working on transmission line. This is your y equals to 0. That means I have drawn my reflection coefficient at load. Then with respect to that, I have drawn the circle. So now, as of now, I am at this point and this point is my load. Right. Now if I start walking clockwise, so after some time I will reach here, then I will reach here, then I will reach at this part. If I keep on walking, I will reach at this part as well, then slowly here as well, and then I will come back. So if I come back here, I have started walking here, and if I have come back here, then what do you think how much distance I have covered? Use your brain and answer me. I started walking on circle and I came back. If I am walking on the circle, what does that mean? That I am going in this direction. On transmission line, I am going in this direction. So if I am starting and I have came back on the same point, that means how much distance I have covered. Think about it. The distance I have covered is lambda by 2. Why is that so? Because on transmission line, after every lambda by 2, the same things happen, right? So if I have covered the complete thing, if you remember the ZY value, what did I tell you? After every lambda by 2, the same impedance is repeated. So here you were, and if you come back, that means the same impedance you have got. This distance could be lambda as well. This distance could be 3 lambda by 2 as well. This distance could be 2 lambda as well. It could be anything. So covering one complete circle, that means if you have worked for 360 degree, that means you have covered the distance of lambda by 2. So walking 360 degree on this particular circle is equivalent to walking lambda by 2 on transmission line from the load. Is that point clear? Very, very important point. Okay. You are studying one of the craziest thing of not even EMFT. You are studying one of the craziest thing of complete electronics, Smith chart. When you go to the masters, these things you will find very complex. So is that point clear? One by one we will go with like good amount of patience we will go. I'm not in hurry anything, but I'm pretty sure this year the question is coming from this particular topic. That's why I thought of making this video. So have the patience. Did you understand this point? If I'm working on the Smith chart, not Smith chart, don't even take the name of Smith chart. If I'm working on this circle for 360 degree, that means I have covered the distance of lambda by 2. So 360 degree is equivalent to lambda by 2. If I say I have worked for 90 degree, that means how much distance I would have covered? Lambda by 8, right? 1/4 of this one, lambda by 8. Basically, if I am working for 360 degree, that means I have covered the distance of lambda by 2. That means if I work for 1 degree, I would have covered the distance of lambda by 2 divided by 360, that means lambda by 720. And if I am working for 90 degree, that means I would have covered the distance of into 90, and that is equivalent to lambda by 8. Is that point clear? Okay. Now another thing. If you keep on working, and you reach here, you reach at this point, what do you think, what kind of point it will be? Resistive? Say yes or no. What did I tell you? On this particular axis, you get a resistive load. So this point will be resistive. What are you understanding? On a transmission line, this is my transmission line. On a transmission line, if I am standing here, that means my load is this thing. That is complex inductive. My load is complex inductive. Now, when I walk on transmission line, what will happen? My impedance will change. This we have already studied in our previous chapter. In previous video. That when you walk on the transmission line, your impedance will change. So now your impedance is changing. Here the impedance was like this. When you reach at this point, your impedance became resistive. So somewhere here, after covering this much of distance, after covering 63.43 degree, on transmission line, your impedance is becoming resistive. So this point will show the resistive. Nature. And this is the point of voltage maxima. Can you remember this thing? Why maxima? Because towards this hand side, what we are getting? ZL greater than Z0. Here we plotted ZLC. What was ZLC? 100 ohm. So here you are getting R maximum. This is the point of R maximum, and this is the point of R minimum. So here you are getting the maximum value of resistance. And what is resistance? Resistance is voltage by current. So if it is maximum, that means here voltage is maximum and current is minimum. So this is the point of voltage maxima, current minima, and R maxima. Is it tough to remember? It might be tough to remember, but how you will remember it? So you just let me know. In the word, there are more righty or more lefty. You might be a lefty, you might be a righty as well, but in the word, there are more righty or more lefty. More righty, right? There are more righty. So in the word, there are more righty. When we started studying the transmission line, did we start with voltage or current? We started with voltage. When you study network analysis, how do we start? With voltage. When we study diode circuit, when we study analog electronics, how do we start? With voltage. In whole electronics, we keep voltage at higher priority than current. I don't know why, but we keep voltage at higher priority than current, right? So who is my priority? Voltage. How many people are there which are righty? More people are there which are righty. So on right hand side I will get voltage maxima. My priority is right hand side and voltage. So on right hand side I will get voltage maxima. So what do you think, what will be this point? So this will be the point of voltage minima. If voltage is minimum, then current is maximum and resistance is minimum. Say yes or no. Are all these points clear to you or not? Are you having fun studying all these things? Like if you would have studied it in comprehensive course, those who have studied EMFT completely, and after gate examination they can come back and watch the video of Smith chart, or at least watch transmission line, because that will help you a lot in masters. So I have taught in that manner only, so that you don't find any difficulty in masters. So you can go and come back if you want to study it comprehensively. But as of now, you need to understand this much analysis, and believe me, you will be able to solve every single problem. The problem which are considered as the toughest problem of gate examination, those also you will be able to understand. And in this lecture only, those problems we are going to solve. So just have the patience and watch the video with good amount of patience, right? So what did we do? We started with plotting the impedance. Then we are working clockwise on this particular circle, and working clockwise means I am working from the load on transmission line. When I cleared the distance of this theta angle, I reached to this point. When I have reached to this point, that means this is my location of V maxima, I minima and R maximum. And this, and then I will again work. I will again keep on working, 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 and then I will reach at this point. So this will be the location of voltage minima, current maxima and R minimum. Now let's just say I was at this point. At this point I was getting my voltage maxima, right? So this was my transmission line. So let's just say I needed to walk x distance. I needed to walk x distance to get my voltage maxima. Okay, this is I am saying that from the load you needed to walk x distance. That means you needed to walk this theta angle, and what this theta angle will be equivalent to? This theta angle is equivalent to x distance. This is what I am saying. Then you answer me one thing: to reach from this voltage maxima till the voltage minima, how many distance I need to walk in terms of lambda? From this voltage maxima, if I need to reach to the voltage minima, then how much distance I need to walk? How much angle I need to walk from here to here? How much angle I need to walk? 180 degree, right? I need to walk 180 degree. 360 is equivalent to lambda by 2. 180 will be equivalent to lambda by 4. So that means this is your voltage maxima. If you need to go to voltage minima, so you need to cover a distance of lambda by 4. And is this thing related? Yes. Related to what? Impedances. So in the previous video, what did we study? That after every lambda by 4, the impedance will be inverted. Say yes or no. Are you getting this point? Are you able to relate the thing? Right? So after every lambda by 4, so this much distance in radian, this in the angle, this distance is 180 degree, but actually this distance is equivalent to lambda by 4, right? And then from this point, if I come back to this point again, from voltage maxima I am coming back to voltage maxima again. That means I have covered the total distance of lambda by 4 plus lambda by 4. That means I have covered the total distance of lambda by 2. So after every lambda by 2, the same thing will be repeated, and after every lambda by 4, there will be inversion. So let's just say I started with this particular point. I started from here. Then after a distance of x, what I am getting? Voltage maxima. Then after lambda by 4, I will get voltage minima. Then again after lambda by 4, I will get voltage maxima. Then minima. Then maxima. Then minima. Is your brain now getting these things? And you can believe me, this is the most complex thing you are understanding of whole electronics. And you are able to relate everything now. From last lecture point 1 to this point, you are able to relate every single thing. Right? So what if I ask you, what is the distance between two conjugative maxima? What is the distance between two conjugative maxima? What will be the answer? Lambda by 2. What is the distance between a maxima and a minima? Lambda by 4. Right? And one more thing, wherever there is voltage maxima, there will be current minima, and whenever there is voltage minima, there will be current maxima. and similarly there will be R minimum and R maximum. Okay, so all these are just points are related. We will solve a lot of problem and you will build one good problem solving technique as well. Okay, yeah. So now let's understand another thing. So there will be one term that will be known as standing wave ratio. What this is known as? Standing wave ratio. So sometimes they can ask you voltage standing wave ratio, or sometimes they can ask you current standing wave ratio. Voltage standing wave ratio, current standing wave ratio, both are the same thing and both are denoted by S. So there is a formula of that. What is the formula? 1 plus mod of gamma divided by 1 minus mod of gamma. Okay, standing wave ratio, this is the formula. What does it represent? This represents the V max divided by V min, or I max divided by I min. What do I mean by that? When I make the standing wave pattern, when I make the standing wave pattern, so let's just say this is how I am getting the standing wave pattern. So what is this? This is my V max. And what is this? This is my V min. So the ratio of V max to V min is my standing wave ratio. So the formula is 1 plus gamma upon 1 minus gamma. Will you be able to remember it? Another formula. Two formula only I am asking you to remember. Right? ZL minus Z0 upon ZL plus Z0. 1 plus gamma L up, 1 plus mod of gamma L upon 1 minus mod of gamma L. So this quantity can never be complex. Standing wave ratio can never be complex because here you are putting the mode. Right? Well and good. So we will use this thing. We will use this thing somewhere. Now we will try to solve this problem. Here I will write down the point. Distance between two maximas, lambda by 2. Distance between two minimas, lambda by 4. This is the minimum distance. But other distance could also be there, no? Lambda, 3 lambda by, oh sorry, 2 minimas, really sorry, lambda by 2 only. Or 2 lambda anything. This is lambda, 3 lambda by 2, 2 lambda anything. Distance between a maxima and minima, conjugative maxima and minima, lambda by 4. This is the minimum distance, other can also be there because after every lambda by 2 the same thing will be repeated, right? So these points we have written. Let's start solving this problem. You will understand a lot of points. You might not be able to solve all these question in one go, but after that, after going through this whole analysis, you will understand every single thing regarding transmission line, regarding standing wave pattern on transmission line, and that is a very complex topic and a very important topic that we are going to cover. So let's get started. First, what we need to do, we need to make the same thing. What we will do, we will first we will get the value of reflection coefficient, that is 1 by under root 5 angle. So I will get that value and then I will draw a circle with respect to that. So how much is this angle now? 63.43 degree. And if someone asks me what is the magnitude of gamma, that is 1 by under root 5. Angle is this 63.43. So here you are at y equals to 0. Now what they are asking? First question, find the distance from load at which voltage maxima occur. So one thing I know that voltage maxima will be equals to current minima and voltage minima is equals to current maxima, right? So I am at y equals to 0. Where is the point of voltage maxima? This is the point of voltage maxima. Right hand side voltage. There are more IT and voltage is our priority. So this is the point of voltage maxima and this is the point of voltage minima. Don't think sir okay, resistance part, nothing like that. Just understand right hand side voltage maxima, left hand side voltage minima. That means this will be the point of current minima and R maxima. So this will be the point of current maxima and R minima, right? So you are at this point. Now you need to reach, how you will walk? Clockwise. Now you need to reach at this point. How much degree you need to walk? From here to I need to reach to this point, 63.43 degree. How much degree I need to walk? 63.43 degree, right? 360 degree is equivalent to what? Lambda by 2. 1 degree is equivalent to what? Lambda by 720. 63.43 degree is equivalent to what? To this thing. So what will be the answer? 63.43 divided by 720. 63 0.63.43 divided by 720. So 0.088 lambda. 0.088 lambda. So this is the point of voltage maxima, current minima, and R maxima. Now those who have already studied this topic, comment down in this video that how complex it was to calculate this value. Like people will mug up the formula there, they will say that okay, n equals to positive you need to put, negative you need to put that, then they will check 2 beta theta max, these kind of formula they remember. In the examination, first thing, it is very tough to recall those formula, and they will frame, if they frame a conceptual problem, then you will be messing up there in the examination. But if you solve by this method, then there is no chance you are going to mess up. Are you getting this point? So just if you walk 0.088 lambda distance from load, at that point you are going to get your voltage maxima. What will be the point of voltage minima? This will be the point of voltage minima, right? This is the point of voltage minima, current maxima, and R minima. So what do you think where I will get my first voltage minima? Do I need to calculate? I can calculate with respect to angle as well. How much angle I need to work to reach this point? 180 degree plus 63.43 degree. How much angle I need to work? 180 degree plus 63.43 degree. When you solve it, what you are going to get? 243.43 degree. And that will be equivalent to what? Lambda by 720 into 243.43 degree. So this calculation you can do and you will get your answer. Or what you can do? That sir, this is the point of voltage maxima. Now I need to go to voltage minima, then I need to work another lambda by 4. If I need to reach at this particular point, then I need to work another lambda by 4. So this is my point of voltage minima, voltage maxima. So if I need to reach at voltage minima, then I need to work another 0.25 lambda, right? So what will be the point of voltage minima? So 0.088 lambda plus 0.25 lambda, right? So how will you make the standing wave pattern now? How will you make the standing wave pattern? Before making the standing wave pattern, first let's find the value of standing wave ratio. What that would be? Divided by 1 minus mode of gamma. So what is your mode of gamma? 1 plus 1 by under root 5 divided by 1 minus 1 by under root 5. So what you are getting? Under root 5 plus 1 divided by under root 5 minus 1. 5 under root 5 under root value. What is the value of 500? 2.236. 2.236 plus 1 divided by 2.236 minus 1. That is coming out to be 2.62. So this ratio is coming out to be 2.62. So this ratio is not infinity. Let's just say this is my, at y equals to 0. At y equals to 0, I am not getting any maxima. Neither I am getting minima. So I am somewhere in between. After that, what I will get? Maxima. Then what I will get? Minima. Then what I will get? Maxima. Then what I get? Minima. Then maxima. Then minima. In that manner I will go. But the minima will not be equal to 0. Why is that so? Because if minima was 0, so what is my S? That is V max divided by V min. If my S was infinity, let's just say S was infinity, or I say if my V minima was 0, then only I would have got S to be infinity, no? But I am getting S to be finite. That means my minima value is not equal to 0. Okay? Actually, the maximum value is always V0 plus, you don't need to remember it, okay? This is the maximum value and your minimum value is, this is your minimum value, but you don't need to remember it. You just remember the standing wave ratio. So what is this point? What is this point? So this point is y equals to 0.088 lambda. What is this point? This point is y equals to 0.088 lambda plus 0.25 lambda. What you are getting? 0.088 plus 0.25. So this point is 0.388 lambda. So that's about voltage. That's about voltage. But current will be opposite, no? What did I say? That's about voltage. Voltage maxima you are getting at 0.088. But what about current? If I draw the standing wave pattern of current. So for current, what will happen? First you will get minima. Where you are getting voltage maxima, there you will get minima. In that manner, we will get for current as well. This is for what? Current. So I'm not showing the locations and all these things. You can show it on your own. But I hope you would have got the point, right? So did you get the answer of first four questions? At what point voltage maxima will occur? At what point voltage minima will occur? At what point current maxima will occur? At what point current minima will occur? So let's write down here. At what point voltage maxima will occur? So voltage maxima will occur 0.088 lambda. What will be this point? Voltage maxima. What will be this point? So after every lambda by 2, the things will be repeated. After every lambda by 2, the things will be repeated. So 0.088 lambda, 0.088 lambda plus 0.5 lambda plus 0.088 lambda plus lambda. In that manner we will go. So this is the point of voltage maxima, or you can say current minima. So this is the answer of A and D, right? The answer of both of them is this. What about C and B? Both will have the same answer. So first we will get started with where we are having the minima. So 0.388 lambda. This is the point of minima. After that 0.388 lambda plus 0.5 lambda. 0.388 lambda plus lambda. In that manner we will go. Okay. So this is the answer of ABCD. What next they are asking? Find the standing wave ratio, current standing wave ratio. So A, B, C, D, E, F. So where is the standing wave ratio? This is the answer of E and F. Because I told you current standing wave ratio and voltage standing wave ratio both are same. Actually the maximum value of current is I naught plus into mod of gamma L. And minimum value of current is I naught minus, sorry, I naught plus only. Here did I write down minus? Sorry. It is V naught plus only. Sorry. I naught plus 1 minus mod of gamma L. Okay, so this is the ratio. So answer is same for current standing wave ratio and current voltage standing wave ratio. Both are the same thing. But this formula that I have written, gamma L equals to ZL minus Z naught upon ZL plus Z naught. So this is the formula for voltage. This is the formula for voltage. The formula for current is just the negative. If someone asks you, this is very rare in the examination. But what if in 1 mark the question is coming, what is your reflection coefficient at load for current? What is your current reflection coefficient at load? This is very rare, but even if it comes, what you will find? The voltage reflection coefficient you will find, but the negative sign. Just I'm asking, just I'm writing down here. You don't need to mug it up. You don't need to watch it again and again. Voltage standing wave ratio, sorry, not standing wave ratio, sorry. Voltage reflection coefficient and current reflection coefficient are different. They have the negative sign. If voltage reflection coefficient is 0.5, then current reflection coefficient will be minus 0.5. But standing wave ratio for both of them are same. Because here what we are taking, here we are taking the magnitude. So minus 0.5, 0.5, both will have the same magnitude, no? So just I am asking you to remember this thing. Just keep it in mind. What if they ask the problem on current standing wave ratio? Very rare, but still if they ask. But we will solve all the problem if specifically if they are not asking about standing wave, sorry, reflection coefficient, then we will solve the problem of standing wave with respect to voltage reflection coefficient. So whatever that we are solving as of now, that is we are solving with respect to voltage, right? Next, what they are asking on transmission line, what is the maximum value of resistance and where does it occur? So where does it occur? Maximum value of resistance, where does it occur? So at this point you are having voltage maxima and current minima. So where will be the maximum value of voltage will be maximum value of resistance will be occurring? EF G. R maximum occur at the same point of V max and I min. Now what is the value of R max? So there are two values. on the whole transmission line, this is my transmission line. If I start working from y equals to 0 to y equals to L, I will get only two resistive element. What do I mean by that? That on the whole transmission line, what I will do, I will plot the gamma value, then I will make the gamma plane, then I will make this, first I will get the value of gamma, then I will make this particular circuit, sorry, this particular circle. So let's just say this was my value of gamma. Here in this question, this is the value of gamma, no? This is how I am plotting the gamma, 63.43 degree. But it's not necessary that you will get this value only. It might happen you get value here, or here, or here, or here. So I am saying anywhere the value could be. Let's just say the value was here. I am starting my journey from this particular point. I am assuming it. So what will happen? I will work on the complete circle. If I am working on the complete circle, that means I am working on the transmission line like this. So if I am working on the circle, what is the value of impedance at this point? Capacitive complex. What is the value of impedance at this point? Capacitive complex. What is the value of impedance at this point? Inductive complex. What is the value of impedance at this point? Inductive complex. What is the value of impedance at this point? Inductive complex. What is the value of impedance at this point? Inductive complex. What is the value of at this point? Purely inductive. What is the value of impedance at this point? Purely capacitive. What is the value of impedance at this point? Resistive, right? And what is the value of impedance at this point? Resistive. So on the whole transmission line, only two kind of resistance you can get. Are you getting this point? All these are inductive. Inductive element you will get infinity. Capacitive element you will get infinity. But resistive element, only two element you can get. One of them will be maximum, one of them will be minimum. What is this point? R minimum. And what is this point? R maximum. So this is the point of R maximum, this is the point of R minimum. So value of R minimum is defined as Z naught, R maximum is defined at Z naught. One will be multiplied with S, one will be divided by S. So let me know where I should multiply by S and where I should divide by S. Where I should multiply by S, where I should divide by S. So R minimum will be Z naught by S and R maximum will be S Z naught. Why is that so? Because S value will always be greater than 1. So for minimum value I need to divide it, for maximum value I need to multiply it. So R maximum occurs at the same point of V maximum and V minimum, and R minimum occurs at the same point of V minimum and I max. But you need to remember these values. What I feel is that this time the question will be framed from this particular portion. They will ask you the value of R minimum and R maximum on the transmission line. So first thing is that on transmission line, when you work on the transmission line, always maximum you can get two resistive element, R maximum and R minimum. That's it. Okay. What is the value of R minimum? Z naught by S. What is the value of Z naught? 50, right? What is the value of S? 2.62. And here 2.62 into 50. Whatever the value you get, 2.62 into 50. So 131 ohm. And 60 कर दिया गया यार, 2.62 into 50 करना था ना, 131. okay, 2.62, so this is 90. So when you work on the transmission line, the impedance, two resistive element you can get, one is 19, one is 131, right? So this is actually not our y equals to 0 in this problem, this is our y equals to 0. So when I work for 0.088, after working for 0.088, I will get here and I will get this value, R max 131. And when I work for 0.088 plus lambda by 4, I will get this value, R minimum. Is that clear to you or not? Now next what they are asking. Yeah, sorry for the interruption. So next what they are asking, at what distance from load you will get purely inductive impedance and at what distance from load you will get purely capacitive impedance. So what you will think? By the scenario that I have taught, what you will think that, sir, I am starting my journey from here. Sir, this was my y equals to 0. This was my y equals to 0. So here I taught that, sir, I will always work clockwise. And if I reach this point, this will be my purely capacitive. If I reach this point, this will be my purely inductive. This is what, sir, you have taught. So what that I have taught here, that your this point will be purely inductive and this point will be purely capacitive. That was actually wrong. This will not be always true. What I said that upper part will be complex inductive, that is true. the lower part will be complex capacitive, that is also true. This part will be resistive, basically this part will be complex inductive, that is true. This part will be complex capacitive, that is also true. This part will be resistive, ZL greater than Z naught, that is also true. This part will also be resistive, ZL less than Z naught, that is also true. But here I said that the imaginary part, the imaginary axis will give purely inductive and purely capacitive. So I am really sorry for that mistake. That is not always true. This was true luckily in this case only. That was true only in this case. But it is not always true. So this is not certain. So I will remove this. You should also remove that concept from your mind. What you need to keep in mind, that sir, certainly upper part will be complex inductive, that is true. Lower part will be complex capacitive, that is also true. This is resistive, ZL greater than Z naught, ZL less than Z naught. All these are true. But what you said that on imaginary axis, the real part, sorry, on imaginary axis, the positive part will be complex, the positive part will be purely inductive and negative part will be purely capacitive. That thing is wrong. Okay, that will not always be true. So now, what about this question? Now, what about this question, sir? So what about this question, sir? How we will solve it? That at what distance from load you will get purely inductive impedance and purely capacitive impedance? So I will just tell you one line, that unless your S is equals to infinity, unless your S is equals to infinity, that means unless your standing wave ratio is equals to infinity. For getting standing wave ratio equals to infinity, what do I need? That my mode of gamma L should be equals to 1. Because what is the formula? 1 plus mode of gamma L divided by 1 minus mode of gamma L. So if it is 1, then my standing wave ratio will be infinity. So either you can remember that unless my standing wave ratio is infinity or my mode of gamma L is equals to 1, unless these two conditions are there, I will never get purely inductive impedance on my transmission line. I will never get purely capacitive impedance on my transmission line. There is 0.00001% chance that they will ask this question in the examination. But even if they ask, okay, I randomly framed this option and I matched it up. To be very honest, I matched it up here. Here I should not even have said that, where it is gone. At this point, I should not have said that this will be purely inductive and this will be purely capacitive. That is not the case. It will not always be true. Luckily, in this case, it was true, and I said that, and I matched up there. I am really sorry for this conceptual mistake, but you need to eradicate this thing from your mind. The point is, upper part will be complex inductive, lower part will be complex capacitive, resistive, ZL greater than Z naught, ZL less than Z naught. All these are true, and this middle point is ZL equals to Z naught. All these are always true, but this thing is not always true. Luckily, in this case, it was true, but this is not always true. So then how will you solve these problems? So you just need to remember one thing, that if S is equals to infinity and mode of gamma L is equals to 1, unless this condition are occurring, in your transmission line, when you work on the transmission line, what I mean to say, when I work on this transmission line, from here I will start working. So when I work on the transmission line, I will never get purely inductive impedance, I will never get purely capacitive impedance. I will get purely resistive impedance for sure. Here I am getting. I will certainly get purely resistive impedance for sure. Where I will get? At this point and at this point. What is this point? This is the point of V maxima. So when I work for the distance of 0.088 lambda, so at that point I will get R maximum. That means my impedance will be purely resistive. And when I work for the distance of 0.388 lambda, at that point I will get R minimum. That will also be purely resistive. But I will never get purely inductive or purely capacitive. So those who are watching this concept for the first time, for them they can remember this line. But those who have studied Smith chart, they would be able to understand the reason as well. Why is that so? Because in Smith chart, where is our R equals to 0 circle? This is our R equals to 0 circle. In Smith chart, right? This is our R equals to 0 circle. And what is our mode of gamma equals to 1 circle? This is our mode of gamma equals to 1 circle only. So if my mode of gamma L equals to 1, then only my resistive part will be equals to 0, no? Let's just say if my mode of gamma L is equals to 0.5, then what will be my circle? This will be my circle. Now on this circle, this R equals to 0 circle will never cut. If my mode of gamma L is 0.5, this I am telling only for those students who are revising it. If you are studying it new, then you can skip this part. You can just remember this thing, that unless this is the condition, my purely inductive and purely capacitive load will never occur. Okay, or you can forget this part as well, because you don't need to remember all these things. But those who have already studied it, for them I am telling, those who have already studied the Smith chart, For them I am telling this thing. What I am telling, that if your mode of gamma is 0.5, if your mode of gamma is 0.5, then this will be your constant VSWR circle. And what is your R equals to 0 circle? This is your R equals to 0 circle. And this circle will never cut this circle. That means on this particular circle, on this gamma equals to 0.5 circle, your R can never be equals to 0. And if your R is never equals to 0, that means you will never get purely inductive part, you will never get purely capacitive part. Is that clear to you? So that was a big blunder from my side. At that point, I said that this point will be the on imaginary axis. The positive part will be purely inductive and the negative part will be purely capacitive. When I said that point, that was pretty wrong from my side, and I am really sorry for that mistake. Okay, it should not have happened. That thing is not true at all. Okay, that was luckily we got in one case, and I thought that that is the case, but not. But that is not the case always. What is true is that upper part will be complex inductive, lower part will be complex capacitive. This part resistive, this part also resistive. ZL greater than Z0, ZL less than Z0, and middle part ZL equals to Z0. That is true. Okay, let's go to the next question now. So this you will solve on your own. You will be able to do it. What I am asking, what will occur first? What do I mean by that? That first voltage minima will occur or current minima will occur. Then I am asking you the standing wave ratio as well. Then you can draw the standing wave pattern as well. Then you can tell me what will be the value of R max, what will be the value of R min, and where all these R max, R min will be occurring. All these points you can tell. Okay, and certainly here as well you can find one more point. What is that? What will be your standing wave ratio? Here also your standing wave ratio will not be equal to infinity. And if it is not equal to infinity, what does that mean? That your purely resistive and purely capacitive, purely resistive or purely inductive condition will never occur, right? Then we will solve these problems, and then we will solve this question. Okay, and after that we will make this table. So you can do everything on your own. Okay, these are just very simple concept. I hope you are enjoying the concept in a very good manner. So try doing it on your own. So let's start. I will start now. So what will be the value of reflection coefficient? You can calculate it on your own. So ZL minus Z0, ZL minus Z0 upon ZL plus Z0, ZL plus Z0, right? ZL minus Z0 upon ZL plus Z0. So we are getting 0.59 with an angle of minus 133.14 degree, right? So what is the first task? Always the first task is to draw it. Magnitude 0.59 and angle minus 133 point. Angle is greater than 90 degree, no? Angle is greater than minus 90 degree. So it will be like somewhere here. Basically, this is your minus 90. I am going clockwise, that means negative angle I am going. So this will be your 133.14 degree. Then what is the next task? The next task is to draw the circle. Circle taking this as radius. So taking this as radius, I have drawn the circle. Now I know one point where I will walk. How I will walk? Clockwise. I will walk clockwise. What will be this point? This will be the point of V minima. Left hand side, less priority, V minima. This will be the point of V maxima. So always I need to walk clockwise. So I will walk clockwise. So what will occur first? When I started walking from here, this is my y equals to 0. When I started walking from here, okay, walking, here I encounter voltage minima and current maxima and R minima. So what is occurring first? Voltage minima is occurring first. So what will occur first? Voltage minima will occur first, right? Or you can say current maxima will occur first. And at what distance from load your voltage minima will occur? At what distance from load voltage minima will occur? So what will be the answer? So I need to walk this much of angle. How much angle I need to walk? I need to walk this much of angle to reach to the voltage minima. So what is this angle? This angle is, let's just say this angle is theta. So here my theta is 180 degree minus 133.14 degree. 180 degree minus 133.14 degree. So this angle is 46.86 degree. So I need to walk for 46.86 degree to reach to my voltage minima. All good? So lambda by 2, or you can say 360 degree is equivalent to lambda by 2. So how much 46.86 degree will be equivalent to? So divided by 720, so 0.065. Okay, I forgot to multiply. No, 46.86, right? 46.86 divided by 720. Yeah, so 0.065. 0.065 lambda. I hope the calculation is correct only. Yeah. So this is the point of my first voltage minima. First voltage minima. Is that the only point where voltage minima will occur? No. If I talk about voltage minima, you can say voltage minima, or you can call it current maxima, or you can call it R minima. So first it is occurring at 0.065 lambda. Then next it will occur at 0.065 lambda plus lambda by 2. Next it will occur at 0.065 lambda plus lambda. In that manner it will keep on occurring. And what will be the location of voltage maxima? Or you can say current minima, or you can say R maxima. What will be the location? After this lambda by 4, right? At 0.065 lambda, what you are getting? Maxima. Sorry, at 0.065 lambda, you are getting voltage minima. So where you will get maxima? After lambda by 4 more distance. Basically, from from here to here, I will work for lambda by 4 more. If I work for lambda by 4 more, where I will reach? Here I will reach. So plus lambda by 4. Then next will be, so let's calculate it, plus 0.25. So this will be 0.315. 0.315. 0.315 lambda. So next will be 0.315 lambda plus 0.5 lambda. Next will be, in that manner it will keep on going. So this will be the location of V maxima, right? Now what will be the standing wave ratio? So first let's find the standing wave ratio. What is standing wave ratio? 1 plus mode of gamma L divided by 1 minus mode of gamma L. So 1 plus 0.59 divided by 1 minus 0.59. So 1.59 divided by 1.59 divided by 0.41. So 3.87. So if my standing wave ratio is not equal to infinity, this is not equal to infinity, what does that mean? That my minimum value will not be equal to 0. If standing wave ratio was infinity, what does that mean? Vmax divided by Vmin. That means minimum value will be 0. But that is not the case now. And now I am going to draw the standing wave pattern of voltage only. So first what we will get, voltage minima will get, but here there is nothing, neither maxima nor minima. But first we will get minima, 0.065 lambda. Then we will get maxima, minima, maxima. What will be the minimum value, what will be the maximum value, that I don't know. But I just know one thing, that first my minima is occurring. First my minima is occurring, that is at 0.065 lambda. Then after the distance of lambda by 4, after that distance of lambda by 4, maximum will occur, then minimum will occur, then maximum will occur. This is the standing wave pattern, right? Now what is the value of Rmax and where I will get it? I will get Rmax here and R minimum here. What is the value of Rmax? S into Z naught. 3.87 into Z naught is 100 this time. That will be 387. And what will be the value of R min? Z naught by S. 100 divided by 3.87. So it is coming out to be 25.78 ohm. Okay, so these are the maximum and minimum value of resistances. But one conclusion you can see from here. What is that conclusion? Let's make the graph again. Okay, so in every question, what I'm gonna do, first I'm gonna draw the circle only, right? First I'm gonna draw the circle, taking that gamma L as radius. Now the thing is, where will be your y equals to 0? Let's just say my y equals to 0 is here, or my y equals to 0 is here. That means it is inductive part. It will be complex inductive. If my load is complex inductive, then I will be working somewhere on this part. This example I have already taken, so let's take the example of here. If my y equals to 0 is here, what does that mean? That means that my load is complex inductive. Now where I will walk? I will always walk clockwise. So if I walk clockwise, if I am walking clockwise, so what I will reach first? What is this point? This point is V maxima. And what is this point? This point is V minima. So if I am walking clockwise, what I am reaching first? Voltage maxima. So if my load is complex inductive, or it could be purely inductive as well. So if my load is inductive, then I will encounter voltage maxima first. And that you can see here as well. When your load was inductive, you encounter voltage maxima first and current minima, you can say. And if your voltage is capacitive, sorry, if your load is capacitive, if my load is capacitive, I can be somewhere here as well. If my load is capacitive. So where I will start my journey from? Here I will start my journey from. So if my load is complex capacitive or purely capacitive, then what I will start? I will start working in clockwise direction. So what I am encountering first? Voltage minima. So when your load is complex inductive, then first you will encounter voltage maxima, and when your load is complex capacitive, then first you will encounter voltage minima, right? And how you can remember it? What is the voltage for inductor? V equals to I into j omega L. So in case of inductor, who leads? In case of inductor, voltage lead, but in case of capacitor, voltage lag. Because for capacitor, this is the scene. So in case of capacitor, current is leading, and in case of inductor, voltage is leading. So when your load is complex inductive, then first your voltage maxima will occur or current minima will occur, and when your load is complex capacitive, then first your current maxima will occur or voltage minima will occur. Is that clear to you or not? In the examination, will you be able to answer this thing or not? Just you will draw the circle, you will take a random point, and then you will see first voltage maxima is occurring. There you go. And then first voltage minima is occurring. Will you be able to answer this thing? Is that point also clear? Why this is happening? That is also clear. Well and good. Okay. Right. So yeah, let's write down in a decent manner 0.065 lambda. Right. Okay. Let's go to the next one. Voltage location of voltage maxima minima you need to find. Standing wave ratio you need to find. So let's get started with the first one. ZL is equals to 50. So what will be your reflection coefficient? ZL minus Z0 upon ZL plus Z0. So that will be 1 by 3. What will be the standing wave ratio? 1 plus 1 by 3 divided by 1 minus 1 by 3. So standing wave ratio will be 2. So what do you see here? How will I draw the circle? So this is how I will draw the circle. The radius is 1 by 3. The radius, taking the reference of radius as 1 by 3, I will draw my circle. Sorry. From here, 1 by 3. And then I have drawn the circle. So this will be the circle. Now what do you think where I am starting my journey from? Here I am starting my journey from. This is my y equals to 0. And what is this point? This is the point of R maxima only. Say yes or no. This is the point of R maxima or V maxima or current minima. I am starting my journey from here. This is my y equals to 0 point. I will start working clockwise. So at y equals to 0 itself, I am getting my voltage maxima. Basically, this is my transmission line. This is my transmission line. And my load is 100 ohm. My load is 100 ohm. My load is 100 ohm. So at y equals to 0 itself, I should get the value of R max. What is R max? R max, if you remember, R max is equals to S into Z0. What is the value of S? S is 2. What is the value of Z0? Z0 is 50. 100 ohms. So you are saying that your R max should be 100 ohm. And you are also saying that your R max should be occurring at 0, lambda by 2, lambda, and 3 lambda by 2, and so on. Let's check in the circuit if it is possible or not. Yes. When I see the transmission line at y equals to 0, I am getting 100 ohm. After lambda by 2, what I will get? 100 ohm. After lambda, what I will get? 100 ohm only. So is that point clear now? Why this formula came? Is that clear now? How this formula came? S into Z0. Now let's find the value of R minimum. R minimum. First, let me know where should R minimum occur. R minimum should occur where? So R minimum should occur after lambda by 4 distance, right? Because this is the point of R max, V max, and I min, and this is the point of R min, V min, and I max. So R min should occur after lambda by 4 distance. Say yes or no? Right? So after lambda by 4 distance, R min should occur. So from load after lambda by 4, R min should occur. So after lambda by 4, what should be the impedance? From load at lambda by 4 distance, what should be the impedance? If you remember yesterday's lecture, what did I say there? Z of phi will be Z0 square by ZL. That means 100 square, sorry, Z0 is 50. Z0 square by ZL. So because after lambda by 4, impedance are inverted. So Z0 square, 50 square by ZL. Right? So what will be the answer? 50 into 50 to 25 ohm. So you are saying that after lambda by 4 distance, I will get 25 ohm impedance. Now I am not sure whether it will be R minimum or R maximum. I am not sure. Okay, I am sure as well, because after lambda by 4, I am saying that my R minimum will occur, and that value is 25 ohm. Let's go by the formula. What is the formula that we have studied? Z0 by S. What is the value of Z0? 50. What is the value of S? 2. What you are getting? R minimum equals to 25 ohm. Is that clear to you or not? Are you able to relate the things? This is equals to this one. This is equals to 100 ohm, this one. Are you able to relate the things or not? After lambda by 4, you are getting minima, R minima you are getting, or you can say I am getting voltage minima. Everything is being related now. Every single thing you can relate, all the dots you can relate, whatever that we studied yesterday, all the dots you are able to relate now. So what kind of standing wave pattern you will get? I am only drawing for voltage. Okay, I am drawing for voltage. So starting with maxima, then minima, and minimum value is not equals to 0 because standing wave ratio is not infinity. Okay, so this is how it will go. Starting with maxima, at 0 you are having maxima, then you are having minima, then you will have maxima and minima. So 0 lambda by 2, this is the point of voltage maxima, right? And what is this case? This case is ZL greater than Z0. So when ZL is greater than Z0 and your load is purely resistive, then at the load itself you are getting voltage maxima. Now for the next case, what will be the scene? ZL less than Z0. What I am talking about? I am talking about B. ZL is equals to 25 ohm, which is less than Z0. So ZL minus Z0 upon ZL plus Z0, that is minus 1 by 3. So angle is 180 degree, right? Angle is 180 degree. Angle is 1 by 3 and angle 180 degree. So where I am starting my journey from? I am starting my journey from this point. What I will do? I will draw the circle. I am starting my journey from this point, y equals to 0. So I will go clockwise, right? I will go clockwise. This is the journey I am starting from. So here I will reach, what is this point? This is the point of R maxima, V maxima, I minimum. And what is this point? This is the point of V minima, I maxima and R minimum. Say yes or no? Right? Okay. So what is the scene here? This is your transmission line, and your load is having 25 ohm resistance, right? And you are starting your journey from R minima only. That means at load you should get, here you should get what? V minima you should get, I maxima you should get, and R minimum you should get. So as per you, the value of R minimum is 25 ohm. But let's check according to our formula, what our formula says. So for applying the formula, I need to get the value of S. What is the value of S? S is 1 plus mod of gamma L divided by 1 minus mod of gamma L. So S is 2. The same circle I am getting. The value of S, 1 plus mod of gamma L. Here I am not going to put minus 1 by 3. I will put plus 1 by 3. S plus mod of gamma L. So what is the value I am getting? S is equals to 2. So what will be my R minimum? R minimum is Z0 by S. So what is the value of Z0? 50 divided by S. R minimum you are getting 25 ohm. And that you should get at y equals to 0. Are you getting this thing? Yes. What about R maximum? R maximum is S into Z0. S into Z0. So what is the value of S? 2. What is the value of Z0? 50. 100 ohm. And where you should get R maximum? R maximum you should get at y equals to lambda by 4, 3 lambda by 4 and so on. Right? So after lambda by 4 distance, after lambda by 4 distance from load, what will be the impedance you will get? Z0 square by ZL. That means 50 square divided by ZL. What you are getting? 100 ohm. Are you getting it? Yes. Are you getting 100 ohm? Yes, I am getting. Are you able to relate the things now? 100, 100. Say yes or no. So this is how things should be studied, right? Not by the formula. Theta beta 2 theta x pi by 4, nah, nothing. Just a diagram and a soul. There you go. This is the pure concept here. And how these all concept came, why this became R maximum, why this became V maximum. So that we study in Smith chart actually. But even if you don't know this, still you will be able to solve the problem, right? Let's go to the third one. ZL is equals to 0. So what is the value of gamma L? ZL minus Z naught upon ZL plus Z naught. So gamma L is 1, minus 1 actually, 180 degree, right? This thing, and then from here we will start, then we will draw the circle, right? This is the point. We will draw the circle then. So where I am starting my journey from, here I am starting my journey from. This is my y equals to 0. So this is the point of voltage minima, right? Because already I know this is the point of voltage minima, this is the point of voltage maxima. So when I am having my short circuit load, at short circuit load, basically this is the condition that my load is shorted. My load is shorted. So let's go to the next page. My load is shorted. So here only I am having my minima, because impedance value is low, no? If ZL is less than Z naught, so here you will have your minima, or you can say current maxima, or you can say R minima. Well and good. Where you will have your maxima? So location of minima are 0, lambda by 2, lambda, and so on. What will be the location of maxima? 0, sorry, not 0, lambda by 4, 3 lambda by 4, and so on. Say yes or no. Well and good. Everything is crystal clear, right? What we need, what else we can find? We can find the value of R min and R max. So R max should occur after lambda by 4 distance, right? After lambda by 4 distance, R max should occur. So here R max should occur. What will be the value of R max? If it is shorted, then at lambda by 4 it will be inverted, it will be open circuited. That means impedance should be infinity. So let's find the value of R max first. What will be my R max? R max should be S into Z naught. Now what is the value of S here? Let's find the value of S. So 1 plus mode of gamma L divided by 1 minus mode of gamma L. So 1 plus 1 divided by 1 minus 1. So what is the answer? Infinity. What is the answer? Infinity. So S is infinity, Z naught is whatever it is. So what is the value of R max? That is infinity. Are we relating the things? This is infinity and this is also infinity. What should be the value of R minimum? That should be Z naught by S. What is the value of Z naught? Whatever it is. S value is infinity. So R minimum is 0. R minimum is 0. And are we able to rate the thing? Yes. Here what is the value of your load? ZL is 0. And where we are expecting to be, where we are expecting it to be minimum, here we are expecting it to be minimum. Are you able to relate it now? Right? Now another thing. Here your S is equals to infinity. So now the thing comes. Which thing comes? What did I tell you? If your S is equals to infinity, or you can say mode of gamma L is 1, then you can have your inductive and capacitive load, purely inductive and purely capacitive load. So at this point, what is the scene? The resistance is infinity. And at this point, what is the scene? The resistance is 0. Now at this point, you will always get purely inductive. Okay? Purely inductive. Although no one will ask you this thing, okay? Just for the information I am telling. And here you will always get purely capacitive. Look, you know that on the upper part, I will expect inductive load. It could be complex inductive. And at the lower part, I will expect capacitive load. It could be complex capacitive or purely capacitive. If your S is equals to infinity, then this load will be purely inductive and this load will be purely capacitive. And if your S is not equals to infinity, then never you will get purely inductive, never you will get purely capacitive. Now is that clear? If your S is equals to infinity, then always inductive, always purely capacitive. And if S is not equals to infinity, then never purely inductive, never purely capacitive. All good. So that real image, that real axis, that thing is not that imaginary axis positive part, imaginary axis negative part, that thing was not true. That was a blunder from my side, and that I eradicated in this video only. Well and good. Okay. So last part, ZL is equals to infinity. D. Point D is ZL equals to infinity. So can I leave it up to you? What will be the value of gamma L? Mode of gamma L. ZL is equals to, not mode of gamma L, sorry, mode of gamma L. ZL is equals to infinity. ZL minus Z naught upon ZL plus Z naught. So if it is infinity, that means Z naught can be ignored. So it will be 1. Can I draw the circle? Yes, I can draw the circle. What will be the reflection of, what will be the standing wave ratio? 1 plus 1 minus 1. So that will be infinity. Yeah, here I forgot to draw the standing wave pattern. So for this particular circuit, what will be the standing wave pattern? So initially what I am having voltage minima. So I am drawing it only for voltage. So initially voltage minima. Now what will be the minimum value? What will be the minimum value? Since S is equals to infinity and that is equals to V max divided by V min. That means V min has to be 0. So minimum value will be 0 here. So this is how the pattern will go. Here your minimum value in these cases, ZL was 25 ohm. Here also you are getting minima, but S is equals to 2 here. Here your S is equals to 2. Here S is equals to 2. So if you draw the standing wave pattern for this particular circuit, so minimum value cannot be 0. You start from minima, but it will not be 0. So if I give you this particular standing wave pattern and then I ask you what will be the nature of load, what you will say? That's why it cannot be inductive. Why it is not inductive? Because in the inductive nature, in the inductive load, if it was inductive, let's see this example. If it was inductive, then at y equals to 0, we will neither get maxima nor get minima. If it was capacitive, then at y equals to 0, we will neither get maxima nor get minima. So it has to be resistive. Now the point will come whether it will be ZL greater than Z0 or ZL less than Z0. Then you will say that, sir, first what is occurring? First my voltage minima is occurring. This is the graph of voltage. So sir, first my voltage minima is occurring. That means it has to be ZL less than Z0. Then third you will say ZL will be equals to 0 or not. If ZL was 0, then my minimum value would have been equals to 0. When my ZL was 0, then my minimum value was 0. All these you don't need to mug up. This is there in your mind. Even if you forget anything, just draw the circle, everything will come onto you. That here you are having minima. These kind of questions we will solve as well. So no need to worry. So first I am starting with minima itself. If I am starting with minima itself, what is the value of minima? Minima is 0. That means my load will be certainly short circuited. Right? So this is how you need to think. So we will solve the problem. Do not worry. In the examination, just once you draw the circle, everything will come into your mind. And this is one of the complex topic which you are going to solve in a very easy manner. So no need to worry. Okay. So yeah, S is equals to infinity here. So first what will occur? First voltage maxima will occur. You can draw the circle as well. If I draw the circle, first my voltage maxima will occur. First voltage maxima will occur. So this is the condition. Here my voltage maxima will be occurring. Okay. Why is that so? Because where I am starting from? I am starting from here. I am starting from here because gamma value is 1 with the angle 0. So this is my starting point, y equals to 0. Here voltage maxima is occurring, then voltage minima will occur. And how much distance I need to walk? I need to walk for lambda by 4 distance to reach here. Right? I need to walk for lambda by 4 distance to reach here. So this will be the point of voltage minima. This is the point of voltage maxima already. So can you draw the standing wave pattern? Yes, I can draw the standing wave pattern as well. So how I can draw the standing wave pattern? So first what will occur? Voltage maxima will occur. Then voltage minima will occur. Right? So here voltage, this I am drawing for voltage. Then at lambda by 4, this will be 3 lambda by 4. This will be in between, this will be lambda by 2. And if someone asks you R maximum and R minimum, so you can directly say that Sir, here only I will get R maximum and that will be equals to infinity. And for R minimum will be equals to 0 and that I will be getting at lambda by 4 and 3 lambda by 4. Is that clear to you? All analysis is crystal clear. Let's see this option. Let's see this particular ZL equals to 100J. So what we will get? What will be the reflection coefficient? ZL minus Z0 upon ZL plus Z0, right? J minus 1 upon 2J minus 1 upon 2J plus 1. Certainly the mode is 1 only, but what will be the angle? As far as I remember, it was 53.13 degree. So angle will be 53.13 degree. What is the next task? Next task is to draw the circle. Draw the circle taking what radius? Taking the radius as gamma L. Gamma L angle is 53.13. So this will be your 53.13. So this is your y equals to 0. So look here, y equals to 0. At y equals to 0, that means you are at load. At load, what impedance you are having? Purely inductive. So what did I say? Here only purely inductive will be. That is wrong. Here also you can get purely inductive. So you are having purely inductive load. What will be the value of what will be the value of S? Standing wave pattern. Sorry, standing wave ratio. So 1 plus mode of gamma L. What is the mode of gamma L? 1 only. Divided by 1 minus 1. So what you are getting? Infinity. So sir, here also my minimum value. What does that mean? That my V minimum and I minimum will be equals to 0. What does that also mean? That all this part will be purely inductive and all this part will be purely capacitive. Purely capacitive. Right? It will be purely inductive. So these are the conclusion we can make, and also we can make the minimum value will be 0. But what is the difference between this guy and this and this? What is the difference? The difference is here at y equals to 0 only you are getting either maxima or minima. But here at y equals to 0 you will not get neither maxima neither minima. At y equals to 0, that is the main difference. At y equals to 0, what you will get? So what do you think? At y equals to 0, are you getting maxima, minima? No. What is the location of maxima? This is the location of maxima. So this is the location of V maxima. This is the location of V minima. So where will be my maxima occurring? So I need to work for the 53.13 degree. If I work for 53.13 degree, then I will get my voltage maxima. So lambda by 2, or you can say 360 degree is equivalent to, basically for V maxima, or you can say for R maxima, or you can say for I minima. How much I need to work? So 53.13 degree I need to work, which will be equivalent to, so 53.13 divided by 720 into lambda, which will be equivalent to 0.073 lambda. So I need to work for 0.073 lambda. That means at this point I will get my V maxima. Okay. And what about minima? What about minima? So for minima, 0.073 lambda plus 0.25 lambda. Then 0.073 lambda plus 0.75 lambda and so on. This will be the minima, this will be the maxima, right? What will be your R max? R max will be equals to, R max is Z0 by S, right? Z0 by, sorry, Z0 into S. So what is the value of S? Infinity. So R max is infinity. So maximum value of impedance is infinity. And what is your R min? R min is Z0 by S, that is equals to 0. Okay. So if someone asks you that at 0.073 lambda distance from load, what will be the value of what will be the value of impedance? At 0.073 lambda distance from the load, you will get R max, and that value is infinity. So in the formula that we have written, Z0 into ZL plus J Z0 tan beta L, tan beta Y. In place of Y, what you can put? 0.073. Then you can solve this thing and you will get to know that it is becoming equals to infinity. Okay. You can try solving this thing. You will get to know that at 0.073 lambda, if you put Y equals to 0.073 lambda in this formula, you will get that your impedance is becoming infinity, right? And that is pretty obvious as well. By the diagram we can certainly tell. So I hope you are able to relate all these things, right? Let's solve for the second case as well. So for that I need to add a page. This is the blank page that I am having. which I can carry downward. Yeah. So let's solve for the second case as well. So ZL is equals to minus 100J. Okay, so what will be the reflection coefficient? ZL minus Z naught upon ZL plus Z naught. Z naught value is what? 50. Upon ZL plus Z naught. So minus 2J minus 1 divided by minus 2J plus 1. So certainly this is one. Angle will be just negative of this, no? Minus 53.13. Are you sure about that? Let's check it. Minus minus 1 minus 2J here, and plus 1 and minus 2J here. And previously what was the scene? This was the scene, that plus 1 plus 2J and minus 1 plus 2J. So this angle we calculated, this angle now we are calculating. Yeah, angle will be just negative. Angle will be just negative, minus 53.13 degree. So this will be the value of gamma L, right? Can you calculate the standing wave ratio? Mode of gamma L is 1 only. So 1 plus 1 divided by 1 minus 1. Standing wave ratio is infinity. Okay. Yeah, here did I draw the standing wave pattern? No. So for the previous case, I forgot to draw the standing wave pattern. That is important actually. So what if I draw the standing wave pattern? How it will look like? I know that my minimum value will go to 0. My minimum value will go to 0. But at y equals to 0, I am neither having maxima nor I am having minimum. Maxima is occurring at 0.073 lambda. So I will start from here. Then at 0.073 lambda maximum will occur, and then it will go like that. So when you see this kind of pattern, what you will understand, that minimum value is going to 0. Minimum value is going to 0. What does that mean? That S is equals to infinity. If S is equals to infinity, then S equals to infinity you can get in only 4 cases. What is that? If ZL is equal to infinity, ZL equals to 0, ZL is purely inductive, and ZL is purely capacitive. Now you need to think which of the following option is your final answer. So if ZL was infinity or ZL was 0, then at y equals to 0 you would be having either voltage maxima or voltage minima. But you are not having anything at y equals to 0. These options are gone. Now, at if your ZL was purely inductive, then first what will occur? Voltage maxima will occur. So yes, this is the answer. If ZL was purely capacitive, then what will occur first? Voltage minima would occur first. So that is not the answer. So this in this one, if I ask you what is the nature of load, what you will say? Sir, purely inductive. So in that manner you need to think. They can give the standing wave pattern and then they can ask you what will be the nature of load. Okay, well and good. So S is equals to infinity, we are getting here. S equals to infinity, we are getting, yeah. So let's draw the diagram first. Angle negative I need to take, and then I need to draw the circle. So first I am drawing the circle, but first you need to show this particular line. The angle is negative only. So now this is my y equals to 0. What I will do? I will start working. I will start working. Where I will reach? I will reach at this point, which is my voltage minima, and then I will reach at this point. This is my voltage maxima. Right? How much distance I will have to cover? This much angle I will have to cover. This is already 53.13 degree. So I need to work for this much angle. What will be this much angle? 90 minus 53.13. Minima. Minima angle is 90 minus 53.13 degree. Sorry. 180 minus, really sorry. 180 degree minus 53.13. 53.3. So I need to work for 126.87 degree. So what will be this equivalent to? This will be equivalent to lambda by 720 into 126.87 degree. So divided by 720. This is 0.176 lambda. Okay, so that's the answer. So this is the location of voltage minima. Voltage minima you can say, current maxima you can say, and R minima you can say. What about voltage maxima? that will be occurring at 0.176 lambda plus lambda by 4. This is your lambda by 4 plus lambda by 4. 0.176 lambda plus 3 lambda by 4. In that manner it will keep on occurring. Say yes or no. Well and good. Okay. So you can draw the standing wave pattern. This was the case for, here only I am drawing. This was for ZL equals to 100J. Now I am drawing for ZL equals to minus 100J. So this I am drawing for ZL equals to minus 100J. So what will happen? First voltage minima will occur. So I will start from here. Voltage minima is occurring. Then maxima in that manner. All good? So you must have understood all the points. Let's write down the summary. Now just the summary is there. If ZL is greater than Z0, if ZL is greater than Z0 and it is resistive load, so what do you think what will occur first? So in the examination you will not think that I remember this thing, that thing, nothing you are going to remember. First thing you can do is that you can take a random example. ZL is greater than Z0. You will take Z0 equals to 50 ohm, ZL equals to 100. You will find that the value of reflection coefficient is 1 by 3. So from where I will start the journey? Here I am starting my journey from. So what is this point? This point is Vmax. And what is this point? This point is Vmax. This point is Vmin. So I am already starting my journey from Vmax. So Vmax at y equals to 0. What will be the standing wave ratio? It will not be equals to infinity. Will not be equals to infinity. So standing wave ratio can be there from 1 to infinity, anything. Not equals to infinity. It will not be equals to infinity. It will neither be equals to 1, it will nor be equals to infinity. So will that be okay for you? Yes. If ZL less than Z0, then you will say, okay, ZL less than Z0, then here I will start my journey from. So Vmin at y equals to 0. What about standing wave ratio? It will be somewhere in between. What about if your load is R plus JXL? If your load is R plus JXL, that means somewhere you will be somewhere here. Let's just say I am somewhere here. R plus JXL. If your load is complex inductive, that means you are somewhere here. You will start your journey anti-clockwise. Sorry, clockwise. Really sorry. You will start your journey clockwise. So what will occur first? Vmax will occur first. Vmax occur first. Right? And what should be the standing wave ratio? It will also be somewhere in between. It cannot be equals to, like you can take the example as well, 50 plus 50J you can take, and then you will get to know that it will be also somewhere in between. If it is inductive, that means you will be somewhere here. So what will occur first? You can say that voltage minima will occur first. So V minima occurs first, somewhere between 1 to infinity. If it is purely inductive, then what will you understand? That angle could be anything. I can start my journey from anywhere. If it is purely inductive, here what did I do? You can take any example. You will get to know that you can start your journey from anywhere, but first V maxima will occur. V maxima occur first. But here the interesting point is your standing wave ratio is infinity. If Z is equals to minus JXC, then you can start your journey from anywhere. Did I draw the diagram for you? Yes. I can start my journey from anywhere, but I will be starting from the downward. From here I will be starting. So what will occur first? V minima will occur first. But the important point is, if it is equals to minus GXC, that means my mode of gamma L will be 1. My reflection coefficient will be equals to 1. Sorry, mode of reflection coefficient will be equals to 1. So my standing wave ratio will be equals to infinity. If ZL is equals to 0, standing wave ratio will be equals to infinity. If ZL is equals to infinity, standing wave ratio will also be equals to infinity. Right? But if ZL is equals to 0, that means ZL is less than Z0. So V minima at y equals to 0. And in this case, if ZL is equals to infinity, so V maxima at y equals to 0. What about ZL equals to Z0? No standing wave pattern. Why is that so? Because what will be the value of gamma L? For ZL equals to Z0, here I need to write down. Okay, let's remove it off. For ZL equals to Z0, what will be the value of gamma L? ZL minus Z0 upon ZL plus Z0. So gamma L will be equals to 0. So this is how the circle will look like. The circle is at origin itself, and there is no reflection. Gamma L is equals to 0. That means this is my forward traveling wave. There is no reflected back wave. There is no reflected back. There is nothing that is being reflected back. So there is no standing wave pattern. Or what is the standing wave ratio? Standing wave ratio will be equals to 1. Standing wave ratio will be equals to 1 because what is the definition? 1 plus mode of gamma L divided by 1 minus mode of gamma L. So standing wave ratio will be equals to 1. R max will be equals to R min only. Because what is the formula of R max? R max. Formula of R max is S into Z naught. And what is the formula of R min? Z naught by S. So if S value is 1, then R max will be equals to R min, and that will be equals to Z naught only. So everything is Z naught. If your load is matched, then everywhere you will see Z naught only. Everything is Z naught. Well and good. So this is the conclusion. There you go. And this is one of the finest problem of your GATE examination. This problem and this problem we will see, then this problem we will see, and then these questions we will see. So these are the questions of your GATE examination that we are going to solve. Shall we solve it in this video or in some other video? Because it's been like this video is already of 2 hours. So let's start. In this video only we will solve. So voltage standing wave pattern is shown of a lossless transmission line with Z naught value is given, and voltage standing wave pattern is shown. Although I told you that standing wave pattern should be shown like this, but they are showing like this. It was given in the examination in this manner only. What do you see? At load, what is occurring? Voltage minima is occurring. At load, voltage minima is occurring. So what will be your first target? First target will be that, sir, I will draw the circle. Sir, forgetting everything, first I will draw the circle, sir. Because here I don't know the value of gamma L, but I know that my journey is starting from voltage minima. And where is my voltage minima? Voltage minima. So where my journey is starting from? My journey is starting from here. So this is my y equals to 0. So sir, from here my journey is starting from. So I am already at V minima. If I am at this point, so with respect to V minima, I am having R minima as well. And along with that, I am having my, what do we call it? I maxima as well. And one more thing I forgot to tell here, really sorry. If you attempted it on your own, then you might not be able to solve it now, because this value should have been given. This was 4, this was 1. 4 1 it was kya? Or it was 3 1. 4 minus 1 upon 4 plus 1. Yeah, it was 4 1 only. Okay, it was 4 1. So if from here I am starting, what does that mean? That my load has to be inductive only. Sorry, my load has to be resistive only. Because if it was purely inductive, or if it was anything, then you would have been starting from here, no? If it was complex inductive or purely inductive, you would be starting from here. If it was complex capacitive or purely capacitive, you would be starting from here. But if you are starting from this point, that means it has to be resistive only. So load is resistive. What is the nature of load? Resistive nature. And what is the value? So here what you will get? R minima you will get. At this point, what you are going to get? R minima, right? And what is the value of R minima? Z naught by S. What is the value of Z naught? 50. What is the value of S? What did I tell you? What is your S? V max divided by V min. That is 4 by 1. So value of S is 4. So what we are getting? 12.5. There you go. This is the answer. So your load impedance is, this is the load. What we are getting? Load impedance is, equals to 12.5 ohm. Did you understand the nature of load? And did you understand the value as well? Yes. Reflection coefficient. What about the reflection coefficient? Reflection coefficient. First, let me know what will be the angle of reflection coefficient. 180 degree. Because where I am starting my journey from? Here I am starting my journey from. That means my reflection coefficient would have been this. This would have been my reflection coefficient. And what is the angle of this reflection coefficient? 180 degree. Right? So what would have been my reflection coefficient? 180 degree. That means reflection coefficient would have been -1. So reflection coefficient is my -1, right? So sorry, ब्लंडर यार, मैं 2 घंटे से पढ़ा रहा हूँ ना, तो मेरा दिमाग थोड़ा सा सैचुरेट हो गया अभी. Really sorry. What will be the magnitude of reflection coefficient? That you don't even know, no? What will be the magnitude of reflection coefficient? That you don't know. What is the angle? 180 degree. So how will you find the magnitude of reflection coefficient? What is the formula you know? S is equals to 1 plus mode of gamma L divided by 1 minus mode of gamma L. This formula I already know, right? And if you adjust it, then mode of gamma L will come out to be S minus 1 upon S plus 1. You can try adjusting it on your own. Okay, mode of gamma L will come out to be s minus 1 upon s plus 1. So 4 minus 1 upon 4 plus 1. So that will be 0.6. Angle you got to know, it will be 180 degree, because this is how my reflection coefficient will look like. So angle is 180 degree. So angle is 180 degree, but magnitude is 0.6. So answer will be 0.6. Okay. Really sorry for that blunder. I need to take a break now because answer is minus 0.6 degree. Yeah. So that's the thing. Okay, we will solve, let's solve this question as well. The reflection coefficient of load is 0.2 angle with 30 degree. What will be the reflection coefficient at lambda by 8 distance away from load? Okay, so what they are saying, what did I tell you? This, in this transmission line, what did I tell you? That whatever that you have found out, that is the reflection coefficient at load. You have find out the value, that is ZL minus Z naught. This is the reflection coefficient at load only, at load. When you walk along the transmission line, your reflection coefficient changes. And how it changes? How it changes? So what I am gonna do? At y equals to 0, at y equals to 0, what is my reflection coefficient? 0.2 30 degree, 0.2 30 degree. This is my y equals to 0. What I will do? Draw a circle. Draw a circle, taking this as radius. So this is the my point of y equals to 0. Now how much I need to walk? I need to walk for lambda by 8 distance. This is the angle, this is the magnitude 0.2, angle 30 degree. How much I need to walk? I need to walk for lambda by 8 distance. What is lambda by 8 distance? And how I will walk? Always clockwise. I will walk clockwise. And what do you mean by lambda by 8 distance? Lambda by 2 is 360 degree, right? So lambda by 8 will be, lambda by 2 is 360 degree. That means lambda is equals to 180 degree. So lambda by 8 will be 180 degree by 8. क्या कर रहा हूँ यार मैं? Lambda by 2 is equals to 360 degree. So this will be 360 by 4. Very simple thing what I am doing. So this will be 90 degree basically. Very simple thing it is. So lambda by 8 should be 90 degree. So you need to walk for 90 degree from here. From this point I need to walk for 90 degree. So where I will reach? What do you think? From here in clockwise direction I need to walk for 90 degree. So where I will reach? Here I will reach, you know. I need to walk from this point, I need to walk for 90 degree. So this complete angle is 90 degree. This complete angle is 90 degree. That means how much angle I am making from x-axis? That is 60 degree, no? And it will be negative 60 degree. Are you able to understand this point? So what will be your reflection coefficient at y equals to lambda by 8? So your reflection coefficient at y equals to lambda by 8, what that would be? The magnitude will always remain same. The magnitude of reflection coefficient on the complete transmission line, the magnitude of reflection coefficient will be always 0.2. Just the angle will change. Now the angle has become minus 60 degree. Did you understand this point? What happened here? A very good question, very important question as well, and very important concept as well. That your reflection coefficient at load is 0.2 with the angle of 30 degree. You need to walk lambda by 8 distance away from the load. That means I am walking lambda by 8 distance away from the load. So where I have reached? I have reached here. Lambda by 8 distance means I need to walk for 90 degree. And I walked for 90 degree. That means I am at minus 60 degree now. So my reflection coefficient at y equals to lambda by 8. My reflection coefficient at y equals to lambda by 8 became 0.2 with the angle of minus 60 degree. So the magnitude of reflection coefficient on the complete transmission line remains always the same. Well and good. So this was a good question. Let's see this one. Try this on your own. So try this one on your own. And this is the best question of GATE examination. This was asked in GATE 2023. And you can go to the solution videos of GATE 2023. Just type GATE 2023 solutions by different coaching institute. They gave like, some take 25 minutes to solve it. Some did not even solve it. Okay. And some just gave the answer that this would be the answer. And now we will solve it on our own. You can also try it. I hope you will be able to do it. Think about it, what the user is doing here, what we are supposed to do, just think about it. Okay. And then we will solve this problem. Then here also I need to teach one concept. Okay. Here I will have to teach one concept, that the value of reflection coefficient is given. Then what is the ratio of reflected power to the incident power? This is just one formula that I am going to teach. So with that we will end the session. So first you try solving this question. Think about it. You have the ability to solve this question. The length is given of transmission line. Then find the total number of current minima on transmission line. This is what they are asking. So first you let me know where we will start from, what will be the condition. So yeah, just try solving it. Then I will come back and solve it, and we will proceed in the session. I am taking a break now. Okay, so did you solve this problem? What was the answer? I guess as far as I remember, the answer was 7. But yeah, let's get started. So what we need to do, we need to find the current minima. So first let's find the reflection coefficient. Reflection coefficient at load, ZL minus Z0 upon ZL plus Z0. That would be minus 1 by 3, right? So then what I will do, I will draw my circle. So where I am starting my journey from? I am starting my journey from y equals to 0. That means I am starting my journey from here. With this, I will make a circle now. I will make a circle. So this is the journey I am starting from. This is my y equals to 0. Then this is my y equals to 0. And what is this point? This point is your current maxima. Voltage minima you can say, or current maxima you can say. What do you need? You need current minima. So how much you need to walk? You need to walk and reach here. So at lambda by 4, what will be the location of current minima? Current minima will be occurring at lambda by 4, then lambda by 4 plus lambda by 2. That means 3 lambda by 4, then 5 lambda by 4. So these are the location of current minima. Just 1 second, I need to put that on. Yeah, so these are the location of current minimas. Now we need the value of lambda, right? We need the value of lambda. So what is the value of lambda? F I am having, and epsilon r is 4 here. So what I need, lambda is equals to Vp by F. And what will be Vp here? C upon under root epsilon r into F. So lambda will be equals to, C is 3 into 10 to the power 8. What is your F? F is 3 into 10 to the power 7 divided by under root epsilon r. Under root epsilon r is 4. So 10 by 2, 5 centimeter, right? Lambda is 5 centimeter. So first minima is occurring at 1.25 centimeter. Second one will occur at 3 lambda by 4. So 1.25 plus 2.5. That means that will occur at 3.75 lambda, 3.75 centimeter. In that manner, it will keep on occurring. But we have a total length of 17 centimeter only. We have the total length of 17 centimeter. So this is what we need to find, that how many minimas will occur. 1, 2, in that manner you can count. Right? But I know that after every lambda by 2 it will occur. That means next, I don't know, like next where it will occur, 3.75 plus 3.75 plus 2.5. Basically 1.25. Then what is the value of lambda by 2 now? 2.5. So after every 2.5 centimeter, the minimas will keep on occurring. So 1.75, then 2.5, then another 2.5. What that would be? So that would be 5. So 6.25. Right? Then another minima will occur. I don't know where. Then next minima will occur at, I will add 5 here, 11.25. Then another minima will occur, that I don't know at which location it will occur. You can calculate as well. How you will calculate? Plus 2.5. You just need to add 2.5 here. If I add 2.5, what I will get? 8.25 centimeter. Right? No, 2.5, 8.75. 8.75. 2.5. Then I need to add 2.5 again. So 11.25. Then I need to add 2.5 again. What I will get? 13.75. Then I need to add 2.5 again. So I will get 15.25. Right? Next I need to add 2.5 again. So what I will get? 17.75. Right? So basically, am I doing the calculation correct? Here I added 2.5. What I'm gonna get? 14.75 here I'm gonna get, no? 14.75. There is some calculation error by 1.25 plus 5. Okay, 3.75. 3.75 plus 5, 8.75. 8.75 plus 5, 13.75. Here plus 5, 11.25. Here plus 5, it will be 16.25. What this will be? Here it will be 16.25. Next, where it will be occurring? 18.75. So, but I have the length of 17 centimeter only. So this will not occur. So how many minimas are there? 1, 2, 3, 4, 5, 6, 7. So total minimas are total 7. So that's the answer. Okay. Total minimas are 7. Before going on to the next question, just solve a revision problem. It is just like a revision problem. So what they are asking, find the reflection coefficient at lambda by 4 distance away from load. At lambda by 4 distance away from the load. This is what you need to find. So let me just tell me one thing. What is the reflection coefficient at load? That is ZL minus Z0 upon ZL plus Z0. So that is equals to minus 1 by 3. So what I will do? This is what I will do. Minus 1 by 3. So this is the circle. I am starting from here. This is my minus 1 by 3 because this will be the line I will be starting from here. This is my y equals to 0. How much I need to cover? I need to cover the distance of lambda by 4. Lambda by 4 is equivalent to what? Lambda by 4 is equivalent to what? 180 degree, right? So I need to reach here. Where I need to reach? Here I need to reach. So in this complete circle, the value of what is the scene that at reflection coefficient at y equals to lambda by 4. So magnitude will not change, only the angle will change. And how much is the angle now? If I have reached at this point, what is the angle? Angle has become 0 degree. So what is the answer? 1 by 3. So the answer is reflection coefficient at y equals to lambda by 4 is 1 by 3. Now there is another way of finding it out. What is that way? Let's just say I calculate the impedance here. What I am doing? I am calculating the impedance at lambda by 4. What that would be? What I am doing? Impedance at y equals to lambda by 4. This is a very important conclusion. What will be the impedance? Z0 square by ZL. Z0 square by ZL. What I am getting? 200. Right? Now, at this point, what is my impedance? Here, at this point, what is the impedance? 200. 200 ohm. Now, if I consider this point as load, then what will be my reflection coefficient? My reflection coefficient at lambda by 4. So what I'm going to apply? I'm going to apply the formula ZL minus Z0 upon ZL plus Z0. But now ZL I'm going to put 200. Basically ZL minus Z0 upon ZL plus Z0. So what answer you will get? 1 by 3 only. So there are two ways. One way is that you can find the resistance at that point. What you can do? You can find the resistance at that point. If I find out the resistance at that point, you can consider that as a load. And then you can find the reflection coefficient. Or what you can do? You can find at the load, at the actual load, and then you walk away. But one thing is for sure, that on the complete transmission line, the value of reflection coefficient will be, the magnitude of reflection coefficient will be constant, only the phase will change. Here the phase was 180 degree. Here the phase was 180 degree. You will keep on walking this line, the phase will keep on changing. 180, 170, 160, 90. It will keep on changing 0, then minus 90, minus 45, minus 90. In that manner it will keep on going. But on the complete transmission line, the value will be 1 by 3 only. Is that okay for you or not? Right? Try this question. I am telling you, when this came, it was like one of the best question, and you can go and check the solutions. Even now in the textbook as well, in a lot of textbook, like a lot of calculation is involved. People think that this will be solved with a lot of calculation, but let's solve it without doing any calculation, just by the pure concept, whatever that we have studied, right? So what the user is doing here, a standing wave ratio of at standing wave ratio on 50 ohm lossless transmission line, that means Z0 is equals to 50 ohm. When it was terminated with ZL, then standing wave ratio was found to be 2. Now the distance between successive voltage minima is 30 centimeter. What does that mean? The distance between successive voltage minima is 30 centimeter. So that distance is lambda. So what is that distance is lambda by 2. So what is the value of lambda? 60 centimeter. And the first minima is located at 10 centimeter from load. So first what is occurring? Voltage minima is occurring or voltage maxima is occurring? You let me know. You let me know first voltage maxima is occurring or voltage minima is occurring. What they are saying? That first minima is occurring at 10 centimeter. They are giving the minima location at 10 centimeter. So if I say that, let's just say first voltage maxima is occurring. I am assuming that first voltage maxima is occurring. This is what I am assuming. So if first voltage maxima is occurring, then where will the voltage maxima occur? That what is the distance of minima minus lambda by 4? Say yes or no. If here you are having minima, then maxima will be lambda by 4 away. So I am assuming that first my voltage maxima is occurring. So if my first voltage maxima is occurring, then what would be the location of first voltage maxima? That would be the location of first minima minus lambda by 4. What is lambda by 4? Lambda by 4 will be 15 centimeter. So you are saying that your first maxima will occur at minus 5 centimeter. Is that possible? No. Is that possible? Not possible. What does that mean? That first your voltage minima will occur. They can give any value here. They did not say that first voltage minima is occurring. They are saying that anything can occur. Anything can occur. Like first maxima can occur, minima can occur. I am just giving the location of first voltage minima, that is 10 centimeter. If this was mentioned as 20 centimeter, if this was mentioned at 20 centimeter, then the scenes would have been different. First voltage maxima would have occurred if it was 20 centimeter, but it is 10 centimeter. If it was 20 centimeter, then you would have calculated this, it would have come 5 centimeter. So the graph would have been something like this, that first your maxima will occur, then minima, then maxima, then minima. But now what is the scene? Now if I draw the standing wave pattern, then this is how it will go. That first my minima will occur. And that in that manner. And what is this distance? This distance is 10 centimeter. Now can I draw the circle now? Can you draw the circle? Can you on the circle, can you let me know what will be there? We will read the question, but for this particular graph, can you draw the circle? Yes, you can draw the circle. This circle you have done. Now let me know where will be your y equals to 0. You understood that first your voltage minima is occurring. That means certainly you are somewhere here, but you will be here or you will be here. Think about it. What is the value of lambda? 30 centimeter, no, 60 centimeter. So what will be your lambda by 2? 30 centimeter. What will be your lambda by 4? That will be 15 centimeter. Right? What will be lambda by 4? Lambda by 4 will be, did I calculate it correctly? Yeah, lambda by 4 will be 15 centimeter. Okay. Now what they are saying, you need to cover the distance of 10 centimeter to reach to the minima. This is my minima. This is my minima. I need to cover the distance of 10 centimeter. How much is this distance? How much is this distance? What is this complete distance? This complete distance is 30 centimeter, right? So how much is this distance? 7.5, right? Lambda, the distance between successive voltage minima, lambda by 2 was 30 centimeter only. So lambda was 60 centimeter. That means the complete distance is 30 centimeter. This complete distance, this complete circle is 30 centimeter. So how much will be this distance? 7.5. Say yes or no. And how much distance you need to travel to reach to the minima? To reach to the minima, you need to travel 10 centimeter. So that means certainly you need to be here, no? Are you getting this point? If you are here, then to reach to the minima, I will have to travel lesser distance. But I need to travel the distance of 10 centimeter. That means certainly my load would be somewhere here. So this would be my value. This would be my value. So I am at this particular point. Are you understanding this point? Right? Because you need to travel the distance of 10 centimeter. So this is another 2.5 centimeter. So here you are. This is your ZL. This is your ZL. Now what they are saying, and first minima, ZL can be replaced by an equivalent length LM and terminating resistance RM of the same line. What they are saying, ZL can be replaced with equivalent length LM and terminating resistance RM of the same line. What does that mean? That when you walk on this line, when I walk on this line, I will encounter two kind of resistance. What two kind of resistance? R maxima and R minima. So what you are doing, you are picking those resistance. You are picking those resistance and then you are extending your line by a LM length, and at the load you are using either R maxima or R minima. So when you use R maxima, then how much distance you need to walk such that you reach at ZL, and when you use R minima, then how much distance you need to walk such that you reach LM. Is that such that you reach ZL? Is that point clear to you or not? This is what they are asking. There is a transmission line, there is a load. So this is the condition of this transmission line. Now what you are doing, when you walk on the transmission line, you get two kind of resistance, R max and R min. What is the value of R max and R min? Can you calculate? Yes, I can calculate. Because what they have given? Standing wave ratio they have given, no? They have given the standing wave ratio, that is 2. Right? So what will be the value of R max? R max will be S into Z naught. That is 2 into 50. That is 100 ohm. And what is R mean? Z naught by S, 50 by 2, that will be 25 ohm. So what they are saying, if you work on the transmission line, you will encounter two kind of resistances. Those are 100 ohm and 25 ohm. If I connect 100 ohm here, if I connect 100 ohm here, at the load if I connect 100 ohm, then how much distance I need to walk such that my impedance here becomes ZL. And if I connect 50, if I connect 25 ohm here, then how much distance I need to walk such that the impedance become ZL here. So again, I will have to draw the circle again. Now this transmission line at this transmission line and this transmission line. Now you let me know both will have same kind of reflection coefficient or different reflection coefficient. What I am asking, this transmission line have a reflection coefficient, magnitude of reflection coefficient at load something. What is that you can find from here as well? That would be 1 by 3. This would be 1 by 3. So they are having the reflection coefficient at load that is equals to 1 by 3. Will they have the same reflection coefficient at load? This is my question. Yes. Why is that so? Because what you are doing, you are picking a resistance which is there in between the transmission line only, and then you are using that as a load. What I am saying, what if I would have walked for a particular distance and I would have got R max here? Okay, I would have walked for a particular distance and I would have got R max. I would have got R max, and if I have calculated the reflection coefficient here, what would be the magnitude of that reflection coefficient? That would be 1 by 3 only. Are you getting this point? Are you understanding this point? Are you understanding why I picked this question? Because what I am saying, on this transmission line, if I have walked for a particular distance, then after that distance I would have got R max. And at R max, if I have calculated the reflection coefficient, then the magnitude would have been same, angle could be something different, but the magnitude would have been same. And what formula I would have applied? The formula I would have applied is that R max minus Z naught upon R max plus Z naught. Say yes or no. If I apply this formula, if I had applied this formula, ZL minus Z naught upon ZL plus Z naught, I was getting the same answer. There are two methods, right? There are two methods of solving this problem. When I came back, I get 1 by 3. If I have worked on this transmission line, I would have got at R max. Then I would have got the reflection magnitude of reflection coefficient to be same that I was getting at load. And formula that I would have applied is R max minus Z naught upon R max plus Z naught. Now let me know what formula I will apply to get the reflection coefficient here. That would be R max minus Z naught upon R max plus Z naught. Is that formula same? This formula and this formula, is that formula same? Yes. That means magnitude of reflection coefficient will be same. So on a transmission line, if I walk on this particular transmission, what is the conclusion of this now? This is a very, very good question. What is the conclusion? That on this transmission line, if I walk, then whatever the impedance I get here, let's just say I am getting a random impedance that is ZA. This random impedance I am getting ZA. Now what do I do? I extend this transmission line. I extend this transmission line, and at the load I connect this ZA. At the load I connect this ZA. And now if I ask you what is the reflection coefficient here, so that same reflection coefficient will be the same that you are getting here as well. Why it is happening? Because of this analogy that I told you, that if you walk, then this is the answer you are getting. But what is the other way? The other way is, at this particular distance, at lambda by 4, you find the equivalent resistance. What is the equivalent resistance? Here at lambda by 4, the equivalent resistance was 200. So if you find the equivalent resistance and then you calculate the reflection coefficient considering that equivalent resistance as load, you will get the same answer. Here what we are doing, again I am explaining what we are doing. I am walking for a particular distance, so I am reaching at R max, and when I calculate the reflection coefficient at R max, I will apply the formula R max minus Z naught upon R max plus Z naught. So this will be my reflection coefficient at R max in this transmission line. Now what I am doing, I am extending this line and connecting R max or R min at the load. If I connect R max at the load, then what will be the formula I will apply? R max minus R naught upon R max plus R naught. So that means the reflection coefficient remains the same. For circuit 1 and for circuit 2, reflection coefficient remains the same. And what is the reason behind that? Magnitude of reflection coefficient remains the same. For circuit 1 and circuit 2, magnitude of reflection coefficient remains the same. Did you understand the reason behind that? Look, in whole YouTube you can find you are not going to learn all these concepts. Okay, I'm not only self praising it, but these require a lot of concentration. So then only you understand these concepts. A lot of people have given the solution, but they do not even take this thing into action. They just said that reflection coefficient will be same. Why? What is the reason behind that? Why the reflection coefficient will be same? The magnitude of reflection coefficient will be same. So what does that mean? That now this circle will be taken for the other transmission line as well. This we are drawing for transmission line 1. This circle I have drawn for transmission line 1. If this magnitude was changing, if the value of mode of gamma was changing, then the radius of circle would change, no? Because what do? First I plot my mode of gamma, then with that radius I draw the circle. But now my mode of gamma is the same. What is my mode of gamma L? My mode of gamma L is 1 by 3. If Rm is connected to Rmax, so what will happen now? What will happen is that where I will start my journey from? I will start my journey from where will be Rmax? Here will be Rmax. I will start my journey from here. Where will be Rmin? Here will be Rmin, but I don't care. So now in the next graph, in the transmission line 2, this is the curve I will get. And for that, what will be the reflection coefficient at load? Since I am using Rmax, so this will be the reflection coefficient at load. Because I am using Rmax, so I will be starting with maxima. Now where do I need to go? I need to walk. I need to walk in clockwise direction, and I need to walk such that I reach this point. And where is my ZL? This is my ZL. I need to walk, and I need to walk such that I reach ZL. Here will be my ZL. So what is this distance? This distance is 2.5 centimeter, right? And what is the total distance? This total distance. What is this total distance? The total distance is 7.5 centimeter. That means I am here. When I started analyzing this transmission line, I started from here. Now this is my y equals to 0. For me, this is my y equals to 0. Now I will walk on this transmission line. Then how much distance I need to cover such that I reach to ZL? I need to cover 7.5 minus 2.5. That means I need to cover 5 centimeter distance. So that means if you have connected 100 ohm resistance at the load, then you need to cover 5 centimeter distance to reach this point. Understood? Okay. So this was the first part. Now second part. What will be the second part? The second part will be if my Rm is equals to Rmin. So there is no doubt that the reflection coefficient will be the same only. That means the circle will be the same. Circle will be the same means the radius of the circle will also be the same. Everything will be ditto same. The radius will also be same. The circle is exactly the same. I know on this circle I will be having ZL here. But where I will be starting my journey from? I will be starting my journey from R minimum. Because I have connected R minimum. What does that mean that if I have connected R minimum? So this is what it means. That I have connected R minimum. Okay. And you know this is 7. And now where I will walk? I will start walking. This is my y equals to 0. Now I will start walking, and how I need to walk? I need to walk clockwise. And here I will reach. So how much distance I will have to cover? 7.5 plus 7.5, and what is this distance? 5 centimeter. And what was this total distance? 15 centimeter. So if Rm was equals to R minimum, and what was the value of R minimum? 25 ohm, right? R minimum was 25 ohm. Then you need to walk for 20 centimeter. And if Rm was equals to R max, and that was equals to 100 ohm, then you need to work for 20 centimeter. Yeah, then you need to work for 5 centimeter. So this is the answer. A great question and a great way to solve it. Important point was why the circle are same. Even if you don't think in this in the examination that sir why circle are same, so like the worst possible case, what would have occurred to you? That you are using a resistive element. That means you will start your journey from here. So R minimum could be there, R maximum could be there. You will find the value of R minimum, R maximum, then you will say what is this distance, then what is this distance. You would be able to do the answer in the examination. But as an educator, it's my duty to tell that why the circle did not change. Because if I change the load, then gamma value should change, no? Because value reflection coefficient is ZL minus Z0 upon ZL plus Z0. So if ZL is changing, then gamma value should change. But this ZL you are getting from the transmission line itself. This ZL RM of the same line. That means if you work on the line, then whatever the RM you get, only two kind of RM you will get. Those RM you are using here. So if you are using the resistance of the same line, then your magnitude of reflection coefficient will not change no matter whatever the length of transmission line is there. Very interesting point. Like the educators, the professor of IITs thought of it. They have been teaching the transmission line for a very long time, so they thought of it. Then they framed the question. But we, as an educator of GATE, we failed to see the beauty of this question. We just solved it applying the equation and all those things, but they expected this answer that someone will solve in this manner, right? So I hope now that point is clear, that what all are the beauty behind all these things and why I took this session. That was also very important. Well and good. Now the next question, this is just a formula based. Now these kind of simple question can also be asked. So what they are asking, so there will be some incident power, no, right? And then there will be some reflected power. There will be load, right? Load in the transmission line. Just formula I will tell, because who knows, this may be asked. So some power will be incident, some power will be reflected back, and some power will be transmitted. So reflected power is 1 minus mode of gamma square of incident power, and transmitted power is gamma square of incident power. Okay, will you be able to remember? This is easy to remember, right? And then you can remember that incident power will be equals to reflected power plus transmitted power. So what they are asking, find the ratio of reflected power to the incident power. Since it is power, so it will be 1 minus mode of gamma square. So that will be 1 minus 0.5 square. 0.25, that would be 0.75. That's the answer. Okay. So these kind of questions they can ask in the examination. So this was just a formula based question that I wanted to teach, and rest all the things have been studied, and now you are much clear that what I feel is that if they want to frame a good question and like this will be there, if they think about EMFT, then this will be the first topic that they will think about to frame the question. This is what I feel. Okay, so you can be confident now, even if you haven't studied EMFT. Now you have spent roughly around 3 to 4 hours on EMFT and you are confident enough, like you will be much confident than any guy who would have studied from anywhere. Believe me. Okay, you will be much confident in EMFT, at least in these topics. Well and good. Okay then, thank you very much. And do comment down how did you find this video. Hi everyone, welcome to PrepFusion. So this is the part 3 of our transmission line. We have already seen part 1 and part 2. So what kind of series we are running? We are running the series for GATE 2025 students. Even if you haven't studied your transmission line at all, even if you don't know a single thing about transmission line or a single thing about EMFT, still you will be able to understand these 3 particular videos, and there is very high chance that from these videos only the final examination questions will come. Okay, so there is very high chance I am expecting that from these 3 videos, from these 3 topics, 4 marks of question can come from EMFT in the final examination, because in EMFT the most important topic is transmission line, and in the transmission line the most important topics are these 3. First one we saw impedances, second we saw standing wave pattern, and third we are going to see the equivalent circuit of transmission line. Okay, so just hold on till the end of the video, you will understand every single thing. And yeah, one more thing, like before watching this video you need to watch those previous 2 videos that you will find on the channel itself, or today I will try to make a playlist as well. So in that playlist you can find it out. I will give the name of the playlist as GATE 2025 one shot. This name I can give. Okay, GATE 2025 one shot. So there you will find those 2 videos about EMFT. We are also running for control system as well. We are also running for analog electronics as well, right? So yeah, let's get started with our topic now. We need to see the equivalent circuit of transmission line. So what we have seen on transmission line, what did we show? That sir, this kind of wire would be there, 2 wire would be there, and both are conductors. This is also conductor, and this is also conductor. And in between there will be a dielectric. In between the wires there will be a dielectric having epsilon r constant, dielectric constant of epsilon r. right? At the load, I can connect any load, or I can keep it open as well. Like load could be open circuit, short circuit, or a random ZL. Here I could have connected a random ZL. The value of ZL could be anything: inductive, complex inductive, capacitive, complex capacitive, resistive, open circuit, short circuit. It could be anything, right? Now answer me one thing. Let's just say if here you are having open circuit load, the line is open circuit, and now if I close the switch, if I close this switch, so will there be any current through the transmission line? Just answer me this question. Or before that, answer me this question. Let's just say this is a question of network analysis. That there is a wire, and I connect a battery here. Okay, and I ask you, what is the current through this wire? What you will say? Sir, it is open circuit. There will be 0 ampere current. Why did you say so? Because in the network theory, whatever the impedance that you see from here, the same impedance you will see from here as well. Say yes or no? So always you will see open circuit impedance. The resistance is infinity, so there will be no current. But in case of transmission line, if you see the first video, here you will see Z equals to infinity. But once you walk across the transmission line, just as you start walking across the transmission line, the impedance will start changing. At every single point, the impedance will change. Even if you cover the distance of 0.0000001 L, still the impedance will change. So at every point, impedance will keep on changing. You will get two kind of resistive element as well that we have seen in the standing wave pattern. So in that manner, resistance will keep on changing. So only at the load there is infinity impedance. That means in the load there will be no current. But certainly in the transmission line there will be current. Because at this particular point, the impedance will be different. At this particular point, the impedance will be different. Right? So if there is some impedance, that means it is a closed path. And if it is a closed path, that means there will be current. So if I say a statement that if my transmission line is having a load of ZL equals to infinity and I apply a voltage source at the input, will I get any current? Yes, you will get the current, even if it is open circuited. Okay, so that was the point I wanted to tell. So even if I keep, here this was conductor. Okay, yeah. So what I was saying, even if I keep it open circuited and just as I close the switch, then what will happen? What did I say? That a voltage wave is generated. Voltage wave is generated and a current wave is also generated. You don't need to remember this V0 plus or I0 plus. And then what happens? They get reflected back, and then we get the concept of a reflection coefficient. That also we saw that with respect to the complete transmission line, reflection coefficient also changes. And since there is forward wave, there is backward wave, both combined will make the standing wave pattern. So this also we have seen. So the bottom line is that there will be current. Now just let me know one thing. If in a wire there is a current, that means wire will certainly have some resistance, no? Conductor will certainly have some resistance unless the conductor is ideal. Let's just say in network theory I am solving this question that this is my wire. There was a resistance, that was this R resistance was there. Then I connected this R resistance through a wire to a battery. This was my battery. So I connected this R resistance through a wire to a battery. So in network theory, what do I say? That this wire will have zero resistance. And the current, just as I close the switch, the current in the resistor will be V by R. But here, this if there is some current flowing, that means there will be some resistance as well. So your conducting wire will have some resistance. Your conducting wire will have some resistance. Now in the inductor, if the current is flowing, so if you remember your higher secondary classes, if the current is flowing, then there will be flux linkage. If there is current, that means there will be magnetic field, right? In a wire, if the current is flowing in this manner, then right hand rule, there will be magnetic field. And if there is magnetic field, there will be flux linkage. If there is B, then there will be phi. And if there is phi equals to Li, that means there will be inductance as well. So basically you can just remember one thing, that if there is current, that means there will be resistance. And if there is resistance, that means certainly with resistance there will be inductor as well. There will be inductance as well. Okay, no one will ask you the reason behind that. Just you need to know that how I am replacing my transmission line with the simple RLC circuit. Okay, now let's just say this is one plate, this is another plate. If there is some current flowing in the plate, so I am assuming that here positive charge is coming, here negative charge is coming. What I am saying, that here positive charge is coming, and let's just say here negative charge is coming. Positive charge, negative charge, in between there is a dielectric. What it will give? capacitance, right? Two plates, in between there is a dielectric, here positive charge, here negative charge. So what it will result in? Capacitance, right? So there will be one capacitance as well. But capacitance, how will you show the capacitance? This is how you will show the capacitance. No, capacitance is there between these two. No, so I will show the capacitance in parallel, right? I will show the capacitance in parallel. So this is how I'm going to show the capacitance. Okay. Now there is a dielectric. This is a dielectric, right? If there was loss in the conductor, that means there was resistance. Look, if you flow some current in the conductor, then there will be some loss. There will be power loss. The conductor will be heating up, right? The conductor will be heating up. So there will be loss. So that power loss is shown by this resistance. Now there is this dielectric as well. No, this dielectric can also be lossy. What do I mean? That let's just say, just I close the switch, this V0 plus was generated. So here V0 plus was generated. Now it will be a traveling wave. Do you remember the graph of traveling wave? So wave will travel. So this was our graph of traveling wave. But what may happen is that just as the wave starts traveling, it may keep on losing its amplitude. The wave is traveling in this medium. Now this medium could be lossy. And if it is a lossy medium, that means the wave will lose its amplitude. Usually they lose the amplitude exponentially. So wave may lose its amplitude exponentially. So if the medium is lossy, then that lossy element also I need to show. So lossy element, how do we show? By resistance. But since it is coming in between, so I will show it by not transconductance, I will show it by conductance. So this is your G. So this R and G both are complete different thing. This R is coming because of the conductor and this G is coming because of the dielectric. Okay, this is associated with the dielectric and this is associated with the conductor. Okay, and what is this G? G is shown by resistance, but it is not actually resistance. It is 1 upon resistance. Basically, this have a unit of Maho. This is what I mean to say, and this have a unit of Ohm. But since it is coming because of the dielectric, that's why I am showing it in parallel. So this is how you show your transmission line. Okay. Now I will use a term that is known as distributive element and lumped element. What do I mean by that? We have studied it in network analysis, but let's just again recall it. So let's just say this is a simple network circuit you are having. This is a simple circuit you are having. Now I tell you that bro, go and get 1 Henry inductance out of the circuit. What I am saying, go and remove the 1 Henry inductance out of the circuit. So what you will do? You will just remove this. If I say go and remove 2 ohm resistance out of the circuit, then you will just remove it. Because in the circuit you can directly see there is 2 ohm, there is 1 Henry. But in the transmission line I can see wires. The R, L, GC are inbuilt there. They are coming because of the current, because of the dielectric, because of the lossy nature. They are inbuilt there. So they are distributive along the transmission line. Along the complete transmission line, this R, L, GC are distributed. So they are always defined with respect to per length. Okay. So here the unit will not be ohm, it will be ohm per meter. Here it will be Maho per meter. What do I mean by that per length? They will say that the length of transmission line is, let's just say, 2 centimeter. Okay. And the resistance of the transmission line is 0.2 ohm per centimeter. That means on the complete transmission line, for 1 centimeter, there is 0.2 ohm resistance. So for 2 centimeter, there will be 0.4 ohm resistance. So on the complete transmission line, there is 0.4 ohm resistance. Same goes for inductance as well. Same goes for conductance as well, and same goes for capacitance as well. Let's take the example of capacitance. So what they can say, there is 3 microfarad capacitance per centimeter on the transmission line, and the length of transmission line is 3 centimeter. That means 9 microfarad capacitance is distributed along the complete transmission line. Are you getting this point? Okay. So they are always defined with respect to per centimeter or per meter or per unit length. Is that okay for you? So now this equivalent circuit that I have made, this equivalent circuit that I have made, that I will make with respect to some small length. What I'm gonna do is that, what I'm gonna do, that on the transmission line I'm gonna take a small length that is delta Z. On the complete length L, I'm gonna take a small length that is delta Z. Now my R will be having a unit of ohm per meter, or meter, or it could be anything, centimeter also it could be, right? So what should I write? I am writing SI unit, so ohm per meter I am writing. Okay, L would be Henry per meter, C would be Farad per meter, and G would be Siemens per meter or Maho per meter. Siemens per meter or Maho per meter. Maho and Siemens both are same thing. Okay. So that means per unit length this much resistance is there, R resistance is there. Per unit length R resistance is there. That means in delta Z length how much resistance would be there? R into delta Z, right? So this I can write as R into delta Z. I am just taking a small portion of delta Z. So there R into delta Z total resistance would be there. L into delta Z total resistance would be there. C into delta Z total capacitance would be there. This was actually inductance, not resistance, sorry. This was inductance. So total L into delta Z inductance would be there, and total G into delta Z conductance would be there. Say yes or no. So that's why it is shown as R into delta Z. What do you mean by R into delta Z? That means R is the total resistance per unit length, and into delta Z, that means you are taking a small portion of delta Z where you see this RLGC. If I take another, let's just say I can take another delta Y portion. I can take on the transmission line only, I can take another delta Y portion. So there what I will see? R into delta Y, L into delta Y, C into delta Y, and G into delta Y. Is that clear to you? Is this slide clear to you? So basically in this, what is the conclusion now? So in this transmission line you will see RLGC. Why R is coming? Because of the current in the conductor. Okay. Why L is coming? If there is current, there will be magnetic field and there will be flux linkage. And if there is flux linkage, that means L will come into action. Why C is coming? Positive charge, negative charge, in between there is an electric. That means C would come. Why G is coming? Because of the loss. Because V0 plus I0 plus that is generated. If that travels through the medium, the dielectric medium that you are having, that can have some loss. So because of that loss, G is coming. So one thing I'm going to write down here, that this R and G are not related to each other. There is no relation between R and G. Is that okay for you? Because this R is because of the conductor and G is because of the dielectric. Is that okay for you? Say yes or no. Right? So on this slide, we can keep all these things. Now we will see a question in GATE 123, which was solved by everyone wrong. You can go and check the solutions of GATE 123. It was solved wrong by everyone. What is the reason behind that? Okay. So equivalent circuit of a transmission line you need to tell, and it was a MSQ. So how will I draw the equivalent circuit? So first let me draw a transmission line. So what is the way? That there is a transmission line which is of length L, but what I am going to do is that on the transmission line I am going to take a small length that is delta Z. Okay. Now in this small length, what do I get? R into delta Z, L into delta Z, C into delta Z, and G into delta Z. Now next as well, what I can do here is that I can take another some different length. No, here I can take some another different length that would be delta Y. So here what I will get? Again I will get R into delta Y. Then what I will get? Again I will get L into delta Y, then C into delta Y, and G into delta Y, right? C into delta Y and G into delta Y. Now how you can get this particular option? First option, let's see the first one. Okay, let's see the first. Let's forget about the first one. First let's see which option is matching with us. So option D is matching with us, right? That sir RLGC, then again LR is there. So RLGC in that manner we can have. Right. So you would mark option D correct. So luckily you are correct here. The point is what you can see here, what they are saying R by 2 delta Z. Here what they are saying L by 2 delta Z. Here what they are saying L by 2 delta Z. And what they are saying R by 2 delta Z. So what they have taken delta Z only, but they have divided R into R by 2 R by 2. Are you getting this point? And L into L by 2 L by 2. Basically the point is delta, I am saying that I am taking my delta Z in this manner. In this manner. This is the delta Z I am taking. But what he is saying that I am taking my delta Z in this manner. So basically there, this is delta Z, this is the delta Z portion, but here I am taking half of resistance only. The point is he is taking, like, this is your delta Z. So what he is doing is that he is taking half part of delta Z and half part of delta Y. This is what he is doing. Basically, he will take a small portion of delta Z or delta Y on the transmission line, right? It is not necessary that they will take the complete this portion, or it is not necessary that they will take complete this portion. What they are saying is that I am taking half portion of delta Z and half portion of delta Y, and then I am giving this as the name of delta Z. So in half portion, what is happening is that this is coming complete, but from here R by 2 is coming, from here L by 2 is coming, from here R by 2 is coming, from here L by 2 is coming. So R by 2 delta Z, L by 2 delta Z, L by 2 delta Z, R by 2 delta Z. So that's why this option was correct. So what is the bottom line? The conclusion is you can take the area, like you can take the small length anywhere, but in the small length there should be one R into delta Z, like one complete R into delta Z, because here R by 2, here R by 2. There should be one complete L into delta Z, there should be one complete G into delta Z, and there should be one complete C into delta Z. Basically you should get them to be 1 1 1 1. So there is R by 2 complete 1 R is there, L by 2 complete 1 L is there, G by 2 C by 2 complete 1 G, sorry, not G by 2, sorry, it is complete 1 G, it is complete 1 C. That's why this option D is correct. It is MSQ. Let's check more options now. What about this one? So here how they have chosen? They have chosen the length to be something like this, right? So here what you can see, half C by 2, half C by 2. Both will come into parallel, it will make 1 C. G by 2, it will make 1 G. 1 R is there, 1 L is there. This is also correct. What about this one? And sir, how will you get this one? Our RLGC was this only, no? No. They have taken RLGC to be something like this, and then they gave this as delta Z. So 1 C, 1 G, 1 R, 1 L. GC both in parallel, RL both in series. So 1 1 1 1. So this is also correct. Why this is wrong? How you can get this thing first? Look, this is correct. Just 1 second. Yeah, this was correct. How you can get this particular circuitry? C, RL and G. This is how you can get it. C, RL and G. This is how I can get it. Look, C is there, RL is there, and G is there. But what is the catch here? Complete G should be there, complete C should be there, complete R should be there, and complete L should be there. L is 1, R is 1, G is G by 2, and C is C by 2. That's why this is wrong. Are you able to understand the point now? So what you are going to do in the examination, you will make complete RLGC. Okay, you will make RLGC. Then you can see that, sir, if I take this portion, then I can get this particular circuitry. If I take this portion, then I can get this particular circuitry, sir. If I take this much of portion, then sir I can get third option, and then fourth option also I can get. But the thing is, in the complete delta Z length, basically this is your complete delta Z length. This is also your complete delta Z length. So in the complete delta Z length, I should get 1 R, 1 L, 1 C, and 1 G. That's it. And this is how I will match the options. This was asked in GATE 2023. And surprisingly, the same kind of questions was asked in 2015 as well. But no one noticed it, and they gave it wrong. Still, you can see the textbook as well. The explanation is not given correctly. Answer was given BCD, and even in the solution as well, still the answer was given, like some are saying ABC would be correct, some are saying ABCD whole would be correct. BCD would be correct, and region also you know now. Okay, the region also you understand. The same question was asked in 2015 as well, but there it was not MSQ. So luckily we got it correct. What they asked? They said that this is a conductor. In between the material that you are using, that is Teflon. The material that you are using, that is Teflon. And the Teflon is having tan loss equals to 0. Okay, loss tangent is 0. So those who have studied EM wave, then they would know what do they mean by this. Loss tangent is 0. So if in the examination you see this kind of expression, tan neta is equals to 0. So what does that mean? You will say that there is no loss. What does this mean? No loss. In the examination, if you see tan neta is equals to 0, that means there is no loss. If there is no loss, that means this Teflon is having no loss. What does that mean? That if here V0 plus was generated, then this V0 plus will not lose its amplitude. It will just keep on traveling with V0 plus only. I0 plus is generated. So this I0 plus will not lose its amplitude. It will travel with I0 plus only. So this is the meaning of no loss. Okay. So if there is no loss, then let me know which value will be 0. R will be 0, L will be 0, G will be infinity, or G will be 0, C will be 0, C will be infinity. Just let me know this thing. If there is no loss, what does that mean? That your G would be infinity. That means G would not come into action. What is our equivalent circuit? This is our equivalent circuit. R, L, G and C. Right? How this R is coming into action? Because of the conductor. They did not say anything about the conductor. That means you will consider the loss. That means there will be R. Why this L is coming into action? L is coming into action because of a magnetic field flux linkage. That's why there is L. So you will take this also into action. Why this C is coming into action? Is there any role of loss? For defining C, is there any role of loss? What do I mean? That there is this conducting plate, there is another conducting plate. Even if there is air, or even if there is water, even if there is any medium which is lossy or lossless, still there will be capacitance. Because the necessary condition for the capacitance is there should be two plates which are far apart by a certain distance, and there could be any material, whether it could be lossy or lossless. Capacitance don't care about that. So what was this? This was coming because of the loss. This G was coming because of the loss. So now if loss is not there, that means G is not there. So that means this G should be removed. And in parallel, if you remove a impedance, in parallel, if I am removing a resistance, what does that mean? That this should be infinity. Sorry, this should be infinity. Yeah, this should be infinity. So I said that G should be infinity. That is, I'm sorry for that. G should be 0. If G is 0, that means this resistance would be infinity. And if there is a resistance that is infinity, that means it will be open circuited. Basically, G was what? G was Maho. So if 0 Maho means infinity ohm. 0 Maho means infinity ohm. Right? So infinity ohm means open circuit. Open circuit means G would be gone. Open circuit means G would be gone. So there will be one R, there will be one L, and there will be one C. Luckily, there was only one option where there was no G. There was only one option where there was no G. In all the options, G was present. So all other options were wrong and this was correct. But now if they ask this kind of problem, then they will frame these options, because now they can ask MSQ. So they will frame these options. What they will do? They will just remove this G. Rest all will remain as it is. They will just remove this G. They will just remove it. Rest all remains as it is. So all three options are correct. B, C, D. Are you getting this point? And how this could be correct? They remove this G, and in place of C by 2, they write down C into delta Z. So this is also correct then. So now what is the point of this 25-minute discussion? Why R is coming, why L is coming, why G is coming, why C is coming, you should be knowing about that, right? If you are knowing about that, then it is pretty good. You will be able to solve the problems. Okay. And what if they say conductor is ideal? What if they say that conductor is ideal? Ideal conductor means they will say that the sigma here is infinity. Why I'm introducing all these terms? Because like you will be getting confused. This video is mainly for those guys who are studying it for the first time, they wouldn't even know what is sigma. Sigma is actually conductivity. In network analysis, you would have studied J equals to sigma E. So that sigma I am writing down here. If sigma is conductivity, if sigma is infinity, that means this R will be 0. So they can write down in the examination that it is an ideal conductor, or what is the other term? Ideal conductor, or what do we call it? Perfect conductor. Okay, ideal conductor, or they can say perfect conductor. Perfect conductor means sigma is equals to infinity, and if sigma is equals to infinity, that means this R will be 0. So there will be no loss. So the equivalent circuit will only be LC, 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 LC. Okay, so this also they can ask, but they have asked about lossless material, Teflon. They said that Teflon is lossless. I guess in the examination, in the language as well, it was written that it is lossless. Lossless means there is no loss, and if there is no loss, that means G will not come into action. So why RLGC are coming? How do we represent it? I hope all these things are clear. Okay, all these are very, very clear. So if this kind of question is coming in the examination, then you would be able to solve it. Now, based on the material that you are using, based on the material that you are using here, based on that, you can define your transmission line into three kind of parts: distortionless, lossless, and lossy transmission line. And in lossy, they will only ask the case of low loss. So all these things you don't need to remember. Here I'm just gonna tell you a problem solving technique. Those who have studied it comprehensively, they would know what is the meaning of lossless. They would know. Now you also know what is the meaning of lossless, right? What is the meaning of lossless? Lossless means there will be no loss in the V0 plus amplitude. V0 plus will be same. I0 plus will be same. Now you might not be knowing the meaning of distortionless. Distortion means basically if this is my V0 plus waveform, okay, so always it should be like this only. Basically this transition should be smooth. I should get this kind of waveform. It's not like that first the transition is like this, then transition is like this, then transition is this. Here again the amplitude remains same. Amplitude remains same, but still this width is changing, no? So that I don't want. So that is known as distortionless. And what is lossy? Lossy means the amplitude will keep on decaying. Lossy means G is present. So here we started with V0 plus, then amplitude will keep on decaying. Okay. So these are the three kind of medium could be there. Three kind of medium could be there. Okay for you. But you don't need to keep stress on this part. We will just develop three formula here, and based on that three formula, at least 10 PYQs you would be able to solve from transmission line. On those formula, only 10 PYQs are asked. On those three formula. So this is very, very important. Okay. So let's get started. So in the examination, any line could be written. You don't even need to think about it. They can write down, sir, it is distortionless line. They can write down, it could be lossy line. They will just write down lossy line it is. If they are asking any question on lossy lines, that means 100% it will be on the low loss case. 100% I am saying. 100%. Because if they want to frame a numerical, it has to be low loss case. Okay. So they will just say in the examination what they will say. They will just say that the line is lossy. So in the mind you would know that, okay, whatever that I have studied, based on that I can solve the problem. They can say that line is distortionless. They can say that line is lossless. So if this is the condition, if these are the lines that are given, then there is one condition. What is that? That R by L would be equals to, okay, not R by L, we will write down L by R. L by R would be equals to C by G. I will tell you a way to remember this thing, okay? A very simple way I will tell you. So the thing is, if in the examination any kind of transmission line is given, for any kind of transmission line you can apply this particular relation, that L by R is equals to C by G. How will you remember? For RL circuit, what is the time constant? For RL circuit, what is the time constant? L by R. How do you remember it? How do I write time constant? This is how I write time constant. How do I write L? This is how I write L. Both look similar, right? Tau and L both look similar. So it would be L by R. It would not be R by L. Basically, the confusion would be, sir, okay, sir, what is the time constant? L by R or R by L? So what you will do? Okay, tau. Tau looks like this and L looks like this. So that means tau and L should be in front of each other. So tau is equals to L by R. Okay, so this is how I remember. So what is the time constant for LR circuit? That is L by R. L by R should be equals to the time constant of RC circuit. What is the time constant of RC circuit? that is R into C. So R into C, but here in place of R, what is there? G. So divided by G, because G is Maho. Basically, time constant is Farad into Ohm. But here, what is the scene? L by R, which is Henry upon Ohm. There is no issue with that. But here, what will be the scene? C by G would be coming. Why C by G would be coming? Because with C, what do you get? G you get. And G is 1 by Ohm. So if you need 1 by Ohm, so C by G you need to do. So L by R is equals to C by G. It is not tough to remember. Will you be able to remember in the examination that any kind of transmission line is given? They will ask you attenuation constant, phase constant, propagation constant, and characteristic impedance. Before that, we can apply this condition that our L by R is equals to C by G. Say yes or no. From here, we can get other relation, like basically, if you solve this thing, what do you get? LG equals to CR, LGTV, LGTV or LGBTQ. This word also you can remember, or LGTV you can remember, is equals to CR, class representative. Class representative. Or you can remember LGBTQ is equals to class representative. In that way you can remember LG is equals to CR. Just I am telling you a way. Okay. Just I am telling you certain ways. So LGTV is equals to CR. In that manner you can remember. Okay. So LG is equals to CR. Or from here what do you get? R by L is equals to G by C. R by L is equals to G by C. This is also a way to remember. R by L is equals to G by C. Not a way to remember, just I inverted it. So these things you can get from this particular expression. So any way you need to remember that if transmission line is given, then my LG would be equals to CR, or R by L is equals to G by C, or L by R is equals to C by G. The best way is the time constant thing. This is how I remember. Time constant L by R is equals to RC C by G. That's it. Okay. Now, there is one certain thing for lossless transmission line. If they are saying the transmission line is lossless, what do they mean? That conductor is also lossless and the material that you are using, that is also lossless. If they are saying the transmission line is lossless, what do they mean by that? The conductor that you are using, this is also lossless and this thing is also lossless. What does that mean? That your R should be equals to G should be equals to 0. Say yes or no. For lossless transmission line, R should be equals to G should be equals to 0. Say yes or no. Why it should be equals to 0? Because if R is 0, that means there is no loss in the conductor, only L will be into action. And if G is 0, that means here resistance would be infinity. And if resistance is infinity, that means it will be open circuited. So here it will be replaced with only C. So LC. So LC circuit you will get. LC, 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 in that manner you will get. If the line is lossless. And they are saying lossless line, that means they are talking about the medium as well and they are talking about the conductor as well. So R and G both are equal to 0. Now if R and G both are equal to 0, so do we satisfy this condition? R by L is equal to G by C. Yes. R 0 by L, G 0 by C. 0 equals to 0. So it is not necessary that always R and G would be equal to 0. It is not necessary. It is necessary only for the lossless line. So what is the conclusion till now? That any line would be given in the examination. What we will do? That sir, L by R is equal to C by G. This is the first thing I will do. Second, I will check that if it is mentioned lossless, and if it is mentioned lossless, that means I would know that R equals to G equals to 0. If lossless is not mentioned, then this is the condition I am having. If lossless is mentioned, then R equals to G equals to 0. We will solve the problem. It will become very easy for you. Then they can ask these formula. What they can ask? Attenuation constant. So what is the value of attenuation constant? Alpha. Attenuation constant is shown by alpha. So alpha is equals to under root Rahul Gandhi. Okay. Under root RG. Alpha is equals to under root RG. Attenuation constant. Basically, here what was generated? V0 plus was generated. So now if it travels a distance, let's just say it travels a distance. So how your V0 plus will be reducing? E to the power minus alpha z. This is how your V0 plus will be reducing. Exponentially it will be reducing. The magnitude, the peak value, that was V0 plus. Peak value was V0 plus. But if it keeps on traveling with respect to the distance, it will keep on decreasing its amplitude. So e to the power minus alpha z. This is how it will keep on decreasing its amplitude. If what will be the formula for that? Alpha equals to under root RG. If the line is lossless, that means whatever the V0 plus was generated, the same V0 plus will keep on traveling. Say yes or no. If the line is lossless, whatever the V naught plus was generated, the same V naught plus will keep on traveling if the line is lossless. That means alpha should be 0. And are we getting the same thing? For lossless line, what is the condition? R equals to G equals to 0. If I put 0 into 0, under root 0, that would be 0 only. So for lossless transmission line, alpha is also equals to 0. So R equals to G equals to 0 is equals to alpha. So for lossless transmission line, attenuation constant is 0. But what you will remember? You will remember only this thing, that formula of attenuation constant is equals to under root Rahul Gandhi. Okay. Let's write down the formula of characteristics impedance, because this is more important. Characteristics impedance, that is Z naught. So that I told you that for every transmission line there is some characteristic impedance Z naught. So that also depends on this RLGC parameter. So that formula you will write down as under root L by C. Under root L by C. So that is the second formula. Now someone like will say that, sir, in the examination I can get confused. It is under root C by L or under root L by C. So you will not get confused. Why so? Because when you write down the impedance provided by the inductor, how do you write down? XL equals to J omega L. And for capacitor, what do we write? 1 by J omega C. So L will always come in the numerator and C will always come in the denominator. So Z naught equals to under root L by C. So this thing you would have noticed if you have studied from PrepFusion, that whenever I ask anyone to remember any certain thing, I will certainly tell you the trick behind that. There is not a single formula in the whole electronics which I ask you to remember without telling any trick. Always I will tell you the trick. Here also there are tricks. There is concept as well. If I am telling you the concept behind that, then also it is fine. Otherwise I will tell you the trick. And that trick you will not forget even after 20 years. Okay. This time constant thing you are not going to forget. Actually this came from the concept only. The time constant should be equal. The speed of charging and speed of discharging both should be equal. That's why this condition came. L by R equals to C by G. So although this is not a comprehensive word, so I'm not going to discuss all these things here, but you are getting this point, right? L by R equals to C by G. Then for lossless transmission line, there will be no loss. That means R should be equals to G, G should be equals to 0. What is the formula of attenuation constant? Alpha equals to under root Rahul Gandhi, RG. Okay. Formula of Z naught, under root L by C. Now confusion would be, sir, under root C by L or L by C. So J omega L divided by 1 by J omega C. So under root L by C. Okay. Now phase constant beta. So for phase constant beta, in the initial lecture we wrote down this formula, right? So 2 pi by lambda. So this formula is always true. This formula is also true. 2 pi by lambda is also true. Always it is true. Now lambda could be replaced as Vp by F, right? Lambda could be replaced as Vp by F. So what do we get? What is 2 pi F? Can I write down omega divided by Vp? So this is also another formula of beta. Although you don't need to remember it, so I'm not going to put it in the boxes. You just remember this formula, beta equals to 2 pi by lambda. So here it is, beta is depending on omega, Vp, all these things. But I need to make beta dependent on this RLGC. Okay. So that formula is omega under root LC. Omega under root LC. Okay. And what is this propagation constant? Propagation constant is gamma equals to alpha plus J beta. This is your propagation constant. Alpha plus J beta. So from this slide, what you need to remember, that for any kind of transmission line, L by R equals to C by G. If lossless is mentioned, that means R equals to G equals to 0. What is the formula of attenuation constant? Alpha is equals to under root Rahul Gandhi, RG. And if R and G are equals to 0, that means alpha is equals to 0. What is the formula of phase constant? That is beta. Beta is 2 pi by lambda, that is always true. But if I want to make it related to LC, then I will write down beta equals to omega under root LC. So this formula I am asking you to remember, beta equals to under root LC. Beta equals to omega under root LC. Then attenuation propagation constant is equals to alpha plus J beta only, and characteristics impedance Z naught equals to under root L by C. So we will apply all these formula and we will see the problems. There is high chances that from these formula only the question can be asked in the examination, and certainly you will be able to solve. So let's solve some PYQs only. Propagation constant gamma is given. You need to find out the value of RLGC, and omega value is also given. Characteristic impedance Z naught is also given. So let's see one thing. Alpha value is given, that is 2, right? And beta value is given, that is 5. Z naught is given, that is 50. So in the examination you will write down whatever that is given. And omega is given, that is 10 to the power 6 radian per sec. Okay, let's see one thing. Alpha equals to under root Rg, right? And Z naught equals to under root L by C. A very interesting formula I'm gonna get from here. If I do, what I can do here is that, what do I know? That sir, my L by R should be equals to C by G. Say yes or no, right? So can I replace my G? G can be replaced as RC by L. G can be replaced as RC by L. So R under root C by L. Alpha is equals to R into under root C by L, right? So what I am getting? Alpha equals to R into under root C by L. Alpha equals to R by Z naught can I write down? Because 1 by Z naught would be under root C by L. So can I write down R divided by Z naught? So what I am getting? Alpha into Z naught is equals to R. Like 2-3 times question has been asked on this formula only. Alpha into Z naught equals to R. They will give the value of alpha, they will give the value of Z naught, they will ask the value of R. So what will be the value of R? Here this is meter inverse actually. This is radian per meter. Although you don't need to remember all these units, and Z naught is 50 ohm. So if I need to find the value of R, that would be alpha into Z naught. You don't need to remember it. You just need to remember these formula. You just need to remember one thing, that there is a relation between alpha and Z naught to get the value of R. This relation, this is the only thing you need to remember. In the examination, you might get confused, sir, alpha into R is equals to Z naught, or sir, R into Z naught is equals to alpha. These kind of confusion can come into examination. So forget about this final expression. If you are not able to remember this expression, then also it is fine. In the examination, we can derive it. But what we need to remember, we need to remember this formula. Okay, just write it down in your rough notebook. Only once you will be able to remember it, and there is very high chance the question can come from this particular topic. That's why I am dealing this topic here. So alpha R equals to alpha into Z naught. So alpha is 2 into Z naught. So what will be the answer? 100 ohm? No, 100 ohm per meter. Okay, that will be the answer. 100 ohm per meter. So that is the value of R. Okay, I will add a page and take a break. You can then find the value of LGC. These are very easy. LGC value also you can find. Okay. Okay, yeah. So let's get started. What we need to find now? R we have already found out. That is 100 ohm per meter. We need to find out the value of. Let's find out. Let's see what all things are given. Z naught is equals to given under root L by C. Okay, and beta would be equals to omega under root LC. So what I can see here is that if I multiply beta into Z naught, what do I get? Omega into, basically beta into Z naught I am doing, right? Under root L by C. This and this is getting cancelled. Omega into L. Certainly you are not going to remember all these things, right? Beta into Z naught is equals to omega into L. So what we are getting? L is equals to beta. Value of beta is 5 into Z naught. Z naught is 50 divided by omega, that is under root 6. So what we are getting? 250 microhenry. So that is the value of L, right? Now can I find the value of C? Yes, from here I can find the value of C. So 50 square divided by 250 micro divided by C. So what I am getting? 250 micro divided by 2500. So I am doing the correct calculation, right? Beta 50, 50, 250, 250 micro, 250 micro Henry it is. Okay, so it is coming out to be 100 nanofarad, right? Because this will be 10 to the power 6 and this is your 10. 10 microfarad is coming out to be. Wait a second, what I am doing? This is 10 to the power minus 6. 10 to the power minus 6. 250 get cancelled, it will be 10. So 10 to the power minus 7, that means 100 nanofarad per meter. Here also there is an error, per meter. So C is 100 nanofarad per meter. Okay. What I need to find? Alpha equals to Rahul Gandhi under root Rg. So alpha square would be equals to, alpha square by R would be equals to G. So G is equals to alpha square, that is 4 divided by R. R is 100, right? So that would be 40 millisiemens per meter, right? So that's the next answer. what else I can see, that whether L by R is equals to C by G, is that condition being satisfied or not? What is the value of L? 250 micro divided by R, that is 100 ohm, is equals to C 100 nano. 100 nano means 10 to the power minus 7 divided by G, that is 4 into 10 to the power minus 3. So this is actually 10 to the power minus 6, and this 0 0 get cancelled. So this become 25 into 10 to the power minus 7. This is actually 25 into 10 to the power minus 7. What I am doing, I am just simplifying it, and I am just checking whether I am getting the correct answer or not. It was 250 because I know that this condition should be satisfied. So 250 micro divided by R. What is the value of R? R is 100 ohm, right? 100 ohm. So if I solve it, I guess 2.5, what I get, 2.5 into 10 to the power minus 6. 2.5 into 10 to the power minus 6. Do I get the same thing here? 10 to the power minus 4, so 100 by 4. 25 into 10 to the power minus 6. I am somewhere messing it up. In the calculation, there is some error from my side. So I need to see that error. What is the error there from my side in the calculation? Yeah, it was a dumb mistake actually. This was 10 to the power minus 2, no? So yeah, that would be satisfied. Basically, this condition is also being satisfied. L by R equals to G by C. The error I was doing here, it was 4 into 10 to the power minus 2, not 4 into 10 to the power minus 3. So if you solve this condition will also be satisfied. Okay. So just I wanted to tell that there are n number of ways of finding it out. So this will be the maximum question. From this question only you are able to see that all kind of parameters you are able to find. Or it might happen that RLDC value are given, they could have asked you to find the value of alpha beta. So conclusion is this slide only. Okay, let's see one more. This value is given. Attenuation constant alpha they are asking. Alpha they are asking. So let's just say you don't remember any formula. So what you are going to do? So alpha formula is equals to under root Rg. So this I need. Alpha equals to under root Rahul Gandhi I remember. Z naught equals to under root L by C I remember. And one more thing I remember, that is, sir, L by R is equals to C by G. Time constant equated. So from this equation, what I will get? Alpha into Z naught equals to R. So from there, my value of alpha would come out to be R by Z naught. So 0.05 divided by Z naught, that is 50. Okay. 5 into 10 to the power minus 2. 5 into 10, that would be 10 to the power minus 3 per meter. Right. 5 into 10 to the power minus 2 divided by 5 into 10. Yeah. Okay, then 5 into 10 to the power minus 2 divided by 5 into 10. Okay, 10 to the power minus 3 per meter. So that would be the answer. Right. So from this complete lecture, what is the conclusion? The conclusion is, first conclusion is RLGC, R, L, G, C. R and L both are associated with the conductor, and these are associated with the medium that is there. G is coming because of the loss in medium. Conductor is there, in between there is a medium, that's why C is coming. G is coming. Delta Z I need to write. Delta Z I need to write. R into delta Z, L into delta Z. That means in unit length, one R should be there, one L should be there, one G should be there, one C should be there. Then for any transmission line, L by R should be equals to C by G. Time constant equated. Okay. For lossless, what will be the condition? R equals to G would be equals to alpha. This is only for lossless. Then there is something called attenuation constant, that is equals to under root Rahul Gandhi. There is something called phase constant, that is equals to omega under root LC. There is something called Z naught intrinsic impedance, that is equals to under root L by C. And there is something called propagation constant, that is equals to alpha plus J beta. That's it. This is the complete conclusion that we have studied in this particular chapter. And it might happen that one question can be coming from here. So this is the conclusion of the complete 50-minute discussion. Okay. So that's it from my side in transmission line. Within first lecture was of roughly around 1 hour. Second was of 2 hour 30 minutes. And this also you would be able to complete within 40 minutes, I guess. So I guess in 4.5 hours you can come, or 5 hours, let's take the maximum one. 5 hours. In 5 hours, you can complete this much part for sure. Whatever that I have taught you till now, in 5 hours, these 3 lectures you can complete, and certainly there is very high chance that question will be framed from this particular topic in the final examination. And without even any prior knowledge of EMFT, you are able to understand all these points. And certainly, believe me, guys, you will be able to solve the problems. In the standing wave pattern, that with the way we have studied standing wave pattern, even if those guys who have studied the comprehensive course in 150 hours or 200 hours as well, they might not be able to solve the problem, because the standing wave pattern we have seen in one circle only. The complete transmission line is coming on just one circle, and if we are able to analyze this circle, then all the questions we can answer. Okay, so I hope you enjoyed this video on transmission line. Although we have covered the comprehensive course, so if you are someone who is looking for GATE 126, who will be coming back for GATE 126 examination, then EMFT course has been uploaded on YouTube itself. You can go and check that course out. Okay, EMFT course is on YouTube itself. But yeah, so you can cover it comprehensively if you are someone for GATE 126. But some guys were saying for GATE 125, they were saying that's a waveguide revision. Look, the thing here is, in waveguide, I cannot break down the topic like transmission line. Look, waveguide is waveguide only. Like there are n number of formulas. There are a lot of formula in the waveguide, right? So I cannot see, I cannot tell that, sir, even if you haven't studied it right from the beginning, still you can study it, because there will be a lot of formula like that. And if there are a lot of formulas, so I cannot expect aspirant to remember those formula. But if you want to revise it, then just go and watch these lectures quick. You can watch this lecture very quickly. These lectures are over roughly around 10 hours. But within 2 hours, you can complete it. Like introduction to a waveguide. So there I will be telling you that how a waveguide is propagating in a rectangular box. So that thing I will tell you there. So within 10 minutes, you will be able to watch this video. You will be able to revise as well. And certainly I can tell you, in these videos only, you will get at least 10 to 12 new and very interesting thing. And that will make your subject very interesting. I can guarantee this thing from wherever you have studied. So for the revision, you can study the comprehensive lectures as well. You just need to skip that part which you already know. Okay, so in waveguide, I did not think of bringing any different video. Why is that so? Because from here only you can cover the whole part, no? Right? And you were asking about oblique incidence. So in oblique incidence only you can watch all these videos. Here I have given the proper assumption, that which assumption you need to take into action, why we take that much assumption into action, and how do we develop that formula, why do we develop that formula. So here you will not find any needless derivation like beta cos theta t, those beta cos theta I, then I write down the formula in a very complex way. This thing is not there. You have seen our lectures. In our lectures, the more important part is how do we understand it in a practical way. It's not that practical that we are making our food using all these things, using all these concepts. We are not making our food. We are just understanding it in a visualization, that how it would be looking like. Right? Are you getting this point? So in oblique incidence as well, I have given enough visualization that you would be able to see the wave, how the wave is coming, where the electric field is dancing, where the magnetic field is dancing, and why there is a certain formula for that. So certainly you can go and check out these videos. And if you just want to revise it in a very quick manner, then I solved this PYQ of GATE 2013. Okay. So this is a 30-minute video. Here I have given the concept as well. So you can watch this video as well. Here, this particular PYQ has been solved, a lot of times this is not solved correctly. So that PYQ also I have solved. So you can watch this video as well. So if you watch just these videos, then your oblique incidence will be completely revised, and it will not take more than 2 hours. Within one day you can revise from here as well. Within one day you can revise from here as well. It will not take more than 2 hours if you have already studied the topic. You just need to see what all new things I am teaching and how I am making it interesting. Certainly you will find it interesting. If you feel like that, sir, my oblique incidence is, I do not find interest at all, I do not even understand it, just watch these videos comprehensively. You will be able to understand, believe me. Okay. And a lot of new things, a lot of assumption that we take while deriving the formula, those I have also written down. And you will never feel like that, sir, why we are going into derivation, nothing like that. We are not going into needless derivation. Wherever it is required, there we are going. Okay. And for antenna part, you can refer these lectures. Antenna is also uploaded there. So for antenna part as well, you can refer these lectures. At least in antenna, you cover these two, antenna parameters and Friis equation. These two are very, very important. From these two videos, questions can be asked. But if you have studied antenna from here, then only you can cover. Like if you know what is Hurgent dipole antenna, if you know what is linear dipole antenna, then you can cover these two videos. Okay, so from antenna you can cover this part. Is that okay for you? So I'm not gonna bring more videos on EMFT. Okay, I'm not gonna bring more videos on EMFT only for your GATE 2025 examination. For GATE 2026 we will bring more videos, but for 2025, those who never studied EMFT, they don't need to study all these things, antenna and all these things. This was only for those guys who are asking for revision. Okay, but those who never studied EMFT, they can cover this much part of transmission line that I have taught just now. This much part you can cover. After this, this is of no use for you. This thing of no use for you. This is of no use for you. Those guys who are studying it for the first time. Those who have already studied it, they want revision, then they can watch these videos. Okay. And yeah, one more error I did in the previous video. There was this error from my side in the previous video. There I wrote down this thing that P in will be coming. P in will be the power incident. This will be the power reflected, and this will be the power transmitted. So formula for power reflected will be mode of gamma square into Pi, and formula for power transmitted would be 1 minus mode of gamma square into Pi. Okay, it was written opposite. So basically this will be your power transmitted and this will be your power reflected. So here what do I need to find? Here I am finding power transmitted. So this is the power transmitted. Power transmitted is equals to this thing. So what will be the power reflected? That will be 0.25 into Pi. Basically for power reflected, I just need to take the mode of gamma square. So mode of gamma is 0.5. So my power reflected would be mode of 0.5 square into Pi. So that would be 0.25 into Pi. So that was an error that I did in the previous video, so that I am rectifying now. Okay. So yeah, that's it. That's it from my side for GATE 2025. Now I don't think there is any other need of bringing more videos for GATE 2025 now. Now whatever that you have studied, just revise that and have full confidence on yourself and do well in the examination. And for GATE 2026, if you are someone targeting for GATE 2026, then first thing is that why you are watching this video if you are targeting for GATE 2026. But if you feel like that I will write down the GATE 2026 examination in a good manner, then you can come and get our course. Here you can apply the code Titans15. So we are giving 15% off on all the subject wise courses, full courses as well. So whatever the subject wise courses you want to purchase, that you can purchase, or if you want to purchase the full courses as well, then you can purchase the full courses as well. You will get 15% off. You need to apply the code Titans15. Okay, and there you will find who is teaching all the subjects. So I can tell that in EC, apart from control systems and mathematics, all the subjects will be taught by me. In ECE, apart from control and mathematics, all the subjects will be taught by me. And in electrical core will be taught by Anish sir, and control system and mathematics will also be taught by Anish sir. Rest all subjects will be on me. Okay. Yeah. Thank you very much. I hope you enjoyed learning EMFT from me. You can comment down if you enjoyed it. Yeah. Thank you very much.